Hello everyone, and welcome to your first interview problem for the tree section of the course. This one's called binary search tree check. The problem statement's actually quite simple. All it is given a binary tree, check whether it's a binary search tree or not. So again, you can refer to your lectures or even just a quick Google search on what the difference between a binary tree and a binary search tree is. As far as this solution, there's no actual test or solution cell in the interview problem notebook, and that's because of the nature of the question. Having a testing cell would basically give away the answer. In this case, just worry about your code making sense logically. A quick hint, you may want to think about tree traversals and how that would be affected if it was a binary search tree or not. You can go ahead and fill out your solution below. One quick note, this is a classic interview problem, so feel free to just Google search validate BST for more information on this problem after you've had a go at it. And one more thing I wanted to point out is just when you're writing your function, as far as how to go about essentially simulating the tree, you can just, if I hop over to a Jupyter notebook, do something like this. You can say def your solution, and let's say it takes in a tree. As far as logically speaking, you can just do assumptions like this, tree dot right child, or whatever you want to call it to say what the right branch of that subtree is. So you can say dot right, etc., tree dot left, and then tree dot value or val, etc. So the reason why I'm not being very specific on how I want you to format the input of your solution is because in an interview setting, they're going to basically expect you to almost pseudocode this out, but with the right syntax. So they're not usually going to give you a complete structure for what the tree looks like or how to check the nodes. You can just go ahead and assume on your own the various methods you would be able to call off that tree. And you can go ahead and look back at the implementation lectures to see what methods we had. Okay, as far as the actual problem here, it's just write a function that would be able to take in a binary tree and check whether it's a binary search tree or not. Again, we're just looking for your code to make sense logically. Maybe think about tree traversals, but just fill out some code below that would look a function something like this, and then in this case, it would return some sort of Boolean true or false, right? Depending if it was a binary search tree or not. All right, with that all being said, best of luck, and in the next lecture, we'll go over the solution to this problem. Thanks, and I'll see you there. Hello everyone, and welcome to the solution to the binary search tree check interview problem. Just to reiterate the problem statement, given a binary tree, you had to check whether it was a binary search tree or not. So if we just zoom in here, it's a little too much, so we can take a look at the solution. I'll just be walking through the solution notebook. I won't actually code anything out live because there's quite a bit of code, but actually one of the solutions is really simple. So the simple solution is to know that if a tree is a binary search tree, then traversing the tree in order should lead to the sorted order of the values in the tree. So we can actually perform an in-order traversal and then check whether the node values are sorted or not. So if you go back to tree traversal lecture, you should be able to check out the function we had for the in-order traversal of a tree. So here that is just straight from that lecture. In this case, what I did was create a list called tree vals, and I appended the values of the tree as we traversed in order, and then went ahead and did a sort check. And what this sort check function does, it takes that list of tree values and then just checks if the tree values list is the same as the sorted version of the tree values list. And so with that function here, I can check if the in-order traversal of the tree actually was the sorted values, and then I know it's a binary search tree. Another classic solution is to keep track of the minimum and maximum values a node can take as you go through the tree. And at each node, you're going to check whether its values between the min and max values it's allowed to take. The root can take any value between negative infinity and positive infinity. At any node, its left child should be smaller than or equal to its own value, and similarly, the right child should be larger than or equal to that own value. So remember, this was the BST property. You can go ahead and review the binary search tree lectures, but this is essentially just checking each node for that BST property. And then, so during recursion, what you're going to do is send the current value as the new max to the left child and send the min as it is without changing it. And to the right child, what you're going to do is send the current value as the new min and send the max without changing it. So here's an example of that sort of logic coded out. So you have this class node here. In this case, we have key, value, and then left and right as none. As I mentioned before, you can use basically any node class you want, something that just makes sense to you, because in an interview setting, they're probably just going to expect you to write out your own methods here. And in this case, I just have the function tree max, tree min, and then I have this verify function, which if I zoom out a bit, you can see it in its full scope. And I just have some examples here. If we go ahead and just go back up here, what's happening here on tree max is if we're saying if not node, just return a float of negative infinity. And what this allows us to do, if I just copy this and go to a try.jupyter, empty cell, this just allows you to have negative infinity in a notebook, or excuse me, in Python. But coming back to this, if it's not a node, that it does not end up being true, you just return negative infinity. And then otherwise you have max left and max right variables, and that's equal to the recursive call on the left and right nodes, and you just return, again, key, max left, max right. And you're doing a similar recursive call here, except it's the minimum now on the left and right of that node. And basically, throughout this verify function, all we're doing is just making sure that BST property is true. So we're making sure that that node left into the tree max function is less than or equal to the node key, and that at the right it's greater than or equal to, and you also verify the node left and node right through recursive calls. Basically just keep recursively verifying each node in that fashion. So to give an example of what this would look like, we have 10, 5, and 30. So 5 is less than 10 and 30 is greater than 10, since they're the left and right nodes respectively. So that will print true since that's correct. Here we have 10 as our root. The right of that is 20, so that's still good. Left of that is 5, so that's still good. But what happens is we have left right equal to 15, and since 15 isn't in the correct position, it's going to print false, since 15 is to the left of 10, and it shouldn't have been on the right there. Okay, so you can go ahead and check out this code yourself, and go ahead and put in examples here into this node code so you can understand what verify is doing and these recursive calls on the min and max checks. But really, the key to understanding this problem in the second portion is going to be the BST check. And really, in an interview setting, you're most likely probably going to be asked to implement this solution instead of the sorting trick here about the in-order traversal. Okay, with that being said, definitely review this one because it's a classic interview problem. Feel free to just Google search validate BST in case you want more information on this problem as well. Okay, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview question for the tree section of the course. This one's called tree level order prints. So you're given a binary tree of integers, and what we want you to do is print it in level order. The output will contain space between the numbers in the same level and a new line between different levels. So for example, imagine you're given this tree, where the root is 1, left is 2, and the right of the root is 3, and then you have 4, 5, 6. So you have 3 levels to this tree. Your output, given a tree that looks like this, should look like this: 1, 2, 3, 4, 5, 6. So your function, if you were given something that looked like this for a node class, let's say left, right, and val, should be able to take in a tree, just take in whatever tree, and then you can go ahead and be creative. As I mentioned in the previous interview problem, you can go ahead and call right, left, val, or whatever node properties you want off that tree. But what we want you to do is print out the levels of the tree as such. Okay, so this is more of a traversal problem again. You might want to take your time with it, think about what we learned about tree traversals and how you would print this out, and go through this tree essentially in levels as you're printing it out. Okay, with that being said, again, just given a binary tree of integers, print it in level order. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the tree level order print solution lecture. The problem statement was this. Given a binary tree of integers, print it in level order. The output will contain space between the numbers in the same level and the new line between different levels. So for example, if the tree looks something like this, 1 with a couple of branches, 2, 3, and then another level, 4, 5, 6, you should be able to take in that tree and then print something out like this, 1, 2, 3, and 4, 5, 6. In the Jupyter Notebook, there's a written explanation you can go ahead and check out, but we're actually just going to jump straight to the code, take advantage of some deck-like structures that are already built into Python from the collections module, and then we'll go ahead and just explain our solution out. Let's go ahead and jump to a notebook. Alright, here I am at the notebook. I already have the node class set up. This is just from the answer solution notebook, but we have left, right, and then val, classic node, class. Okay, let's go ahead and start with our function to print this in level order. We'll just call this level order print, and it will accept a tree. And right off the bat, we'll say if not tree, just return, because we know we no longer need to iterate over that. Okay, something I'm going to do is take advantage of the dex data structure, which you can actually just import from collections. So I'm going to say import collections here. And the collections module has the stacks, queues, and decks built into Python. So I'm going to say nodes is equal to collections.deck. And in this case, we pass it just that tree as the single item in a list to set up our nodes as a deck. Okay, I'm also going to set up two variables, one called current count, set it equal to 1, and another one called next count, set it equal to 0. And I'm going to say, while the length of that deck we just did, nodes, is not equal to 0, we're going to do the following. We're going to say that current node is a new variable and set that equal to nodes.popLeft. And let me go ahead and say nodes here. And what this pop left allows us to do is, since we have a deck, remember a deck we can remove from both ends. So this allows me to use this pop left method on that deck. You can go ahead and check it out just by pressing tab later on. So let me just go ahead and put a new cell here so we can just explore this a little more in case there's any confusion. And I will set d equal to collections.deck. I'm going to pass it in a list of 1, 2, 3. And then if I say d dot and then I press tab, these are all the methods or attributes I have available for me. So I can say pop left, and I can also say append left versus just a normal append, which just goes to the right. And then pop will just also go to the right. So pop and append, the normal ones always go from the right end of that deck, but I can also append left and pop left, which I can't do with a normal list. All right, you can go ahead and review the deck lecture in case there's any confusion on that, but it's basically a list where I can pop and append things from both ends, unlike a queue. All right, so I'm going to pop left and set that equal to my current node, and then since I'm doing that, I'm going to set current count. I'm going to subtract 1 from it. And then what I'm just going to do is print the current node dot value. And then I'm going to say if the current node dot left, and I'm going to say nodes append current node dot left. And then I add 1 to the next count. And we'll go ahead and go through the overall code in just a second. But I'm going to say if current node.right, and remember how we use this .left and .right check just to see if it's basically, this is essentially if not none check, because if there's nothing there, it's just going to equal none. In this case, I'll say nodes append current node right. Very similar to what we were just doing. Current node dot right. And I will say next count, in this case, plus equals 1. And I will also say if current count is equal to 0, then we just finished printing that current level. So I'm going to go ahead and say print a new line. And then I'm going to reset the current count. I'm going to do some tuple unpacking here in order to do this as next count and current count. And this is just to make sure I don't have to set up a temporary variable for this sort of switch here. So that's a nice little feature of Python tuple unpacking. And let me make sure, looks like I have an error here in line 13. Let me go ahead and remove that. Sorry, I didn't catch that. That should have been a 0. So while the length of nodes is not equal to 0, my apologies, I'm going to say this. Let's go ahead and zoom out so we can get a whole picture of the code. I'm going to take in the tree, check if there's none there, otherwise I'm just going to return. Set up a variable called nodes. It's a dec of that given tree. And then I'm going to set my current count equal to 1 and my next count equal to 0. So while length of nodes is not equal to 0, meaning he'll still have stuff in that nodes dec, I set my current node equal to the left popped out, and the current count is going to be subtracted from 1, or have 1 subtracted from it. Then I'm just going to print the current node value so I can check it. Then I'm going to say if current node dot left nodes dot append the current node left next count plus equals 1. Similar check for the current node right. And then finally, if my current count is equal to 0, I can just print a new line and reset my current and next count. Let's actually make sure this all is working before we finalize this solution. So what I'm going to do is just go ahead and set up a tree, cell root equals node 1, and then we'll go ahead and say root.left and root.right are 2 more nodes, 2, 3. So when we print this out, we should see 1 space 2, 3. And you can try this out with a larger tree if you want. But now I'm just going to call level order print on the root. And you notice here, we didn't exactly get the spacing right. So why is that? That's because of the print statement up here. In Python 2, what I would have to do is put in a comma in order to keep printing on the same line there. So that's essentially just a print formatting issue. In Python 3, you may have to adjust this. What you could do as well is just get a new list and call it something like line2print equals empty list, and then just go ahead and print out that list and have this line be essentially an append, and then print it later on, right before you print that new line. It's up to you. That's essentially not what the question's getting at. That's just a print formatting issue. So don't worry too much about that, as long as your logic of how you're checking for the current nodes, both left and right, and then essentially adding to this count and being able to print new lines is correct. That's really the key to this. The time complexity of the solution is linear, order n, because that's the number of nodes in the tree, so it's optimal. We'll have to be able to check each node because we need to print it at least once. Alright, so again, basically what's just going on is to print the new line in the correct place, we're just counting the number of nodes at each level. And we're going to have 2 counts, namely the current level count and the next level count. That current level count indicates how many nodes should be printed at this level before printing a new line. And then we just take away from that count every time we pop an element. Once the current level count reaches 0, we just print a new line. The next level count contains the number of nodes in the next level, which will become the current level count after printing the new line, which is what this line right here is doing. Okay, then after that we just count the number of nodes in the next level by counting the number of children of the nodes in the current level. Alright, you can go ahead and check out the full explanation in the Jupyter Notebook. There's a couple of mentions to something called breadth first search and also depth first search, and we'll discuss those later on in the graph section of this course. Okay, That being said, it's a pretty common interview problem, so make sure you know it well. And there's various ways of actually solving it. So go ahead and feel free, like you have some flexibility on your actual solution. Okay, that being said, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your last interview problem for the tree section of the course. This problem is called Trim a Binary Search Tree. Here's the problem statement. Given the root of a binary search tree and two numbers, min and max, trim the tree such that all the numbers in the new tree are between the min and max, inclusive. The resulting tree should still be a valid binary search tree. So for example, imagine you got this tree as the input. You were given the root of the tree, and the methods and attributes of that root contained all the subtrees on it. But you have the root, 8, and you have some other children and branches on it. And if you were given the minimum value of 5 and a maximum value of 13, you would essentially trim the tree so it would look like this. So now you only have values between 5 and 13 in the tree. So we should remove all the nodes whose value is not between the min and the max. I want you to feel free to reference the lecture on the binary search tree for the node class, but what's really more important here, as I've mentioned in other lectures, is the logic of your function. In which case, your function should be in the form of this. You should be able to take in a tree node. You can either just have this as the root or the tree itself, and then a minimum value and a max value. And you can just assume methods such as left, right, and value. Okay, so again, there's no solution cell here because the nature of the code should just really be more logical, and any sort of official test would essentially give away the answer structure. Just focus your answer to fill out the logic of the solution using the methods described above. Okay, with that being said, again, this is a pretty common problem. You can just basically Google trim a binary search tree if you want more information on it. But in the next lecture, we'll go ahead and go over the solution. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the solution lecture for the Trim a Binary Search Tree interview problem. Just to go over the interview problem again one more time, the problem statement was, given the root of a binary search tree and two numbers, min and max, trim the tree such that all the numbers in the new tree are between the min and max, inclusive. The resulting tree should still be a valid binary search tree. So remember that BST property that we were talking about in the binary search tree lecture. So for example, if we get this tree as input, this one right here, and we wanted to get a min value as 5 and a max value as 13, then your resulting binary search tree should look something like this. And notice how the branches go correctly, for 7 is greater than 6, so it goes to the right, 13 is greater than 10, it goes to the right. So you removed all the nodes whose value was not in between the min and max, and it's still a valid binary search tree. So I'm at the solution notebook. So there's an explanation of the solution right here, as well as some code for the solution and a discussion on the complexity. What we're going to do is just jump straight to the live code this out, and explain it along the way. So let's go ahead and jump to the Jupyter Notebook. Okay, here we are at the Jupyter Notebook, and let's go ahead and begin. First thing I'm going to do is say def, say trim, we'll say binary search tree, BST, we'll take in the tree, the min value, let's go ahead and call it min val so it matches the solution code, and max val. And we can go ahead and maybe zoom in one more. Okay. First thing we're going to just do is say if not tree, return. Meaning if we come finally to a none node, we just return. Alright, so what are we going to do here to solve this problem? We're actually going to use some recursive calls. We're going to do a post-order traversal of the tree. Go ahead and review the traversal lecture in case you want more information on the post-order. But what we're basically going to do is process the left children first, then the right children, and finally the node itself. So we form the new tree bottom up, starting from the leaves towards the root. As a result, while processing the node itself, both its left and right subtrees are valid trimmed binary search trees. They may be null as well, or none. And so what we're going to do at each node is we're going to return a reference based on its value, which will then be assigned to its parent's left or right child pointer, depending on whether the current node is left or right child of the parent. Let's go ahead and see what this looks like. So what I'm going to say is tree.left is equal to, and here's the recursive call, trim BST, we pass in the left, and again the min val and the max val. And we're going to do the same thing for the right. So trim BST, say tree.left, or excuse me, tree.right, min val, max val. Okay, then we're going to say if min val is less than or equal to tree.val, or it's less than or equal to max.val, we just return the tree since we know it's good. And this is where we basically are taking in the BST property. So we're saying if tree.val is less than or equal to min val, then return tree.right. And then finally, we'll say if tree.val is greater than max val, return tree.left. And that's all there is to it. So let's go ahead and discuss this in a little more detail. So at each node, what we're doing is we'll return a reference based on its value, as I mentioned, which will then be assigned to its parent's left or right child pointer, depending on whether the current node is the left or right child of the parent. If current node's value is between min and max, so that's these checks right here, min and max, then there's no action need to be taken, so it's good. We just return the reference to the node itself. So if that value is in between the min and max, we know we're good there, so we just return the tree itself, or that node itself. If the current node's value is less than minimum, then we return the reference to its right subtree and discard the left subtree. So if it's less than the min val, we return the right subtree. And we can do that because remember, we know it's a binary search tree. So everything to the left can be discarded since we already know everything to the left is going to be lower than that minimum. And then you can use the same logic here. If the tree value is greater than the max value, you can just return tree left because you know everything on the right is already too big because it's a binary search tree. And so this is really all the interview problem is trying to get at. The fact that you can think of these three properties here. First, you just check if the value is in between the min value and the max value. If so, then you're good, return the tree. And the reason you're returning that node or that tree is because you're doing a recursive call. So you're going to eventually keep doing this and you'll take care of all the branches, which is why you have these two recursive calls for left and right. Then, and this is the key, this is what your interviewer will be looking for, is the fact that you know if the tree.val is less than the minimum value, you just return the entire right tree and you discard the entire left. Because it's a binary search tree, you know everything to the left can already be discarded because of this line. And then similarly, you can do the same thing here. Okay. So again, they're really just searching for your understanding of the binary search tree property. The complexity of this algorithm is order n, where n is the number of nodes in the tree, because we basically perform a post-order traversal of the tree, visiting each and every node once. This is optimal because we should visit every node at least once. This is a very nice question here that both demonstrates the effectiveness of recursion on trees, this, and your understanding of BST. So to really understand the solution to this problem completely, go ahead and review post-order traversal and review BST property in trees. So you can go ahead and revisit those lectures. As far as your code itself, it doesn't have to look exactly like this as far as the tree.left or how you call those specific methods on tree.value in case you're putting in root or node. But the actual logic should be the same. This line, and this line, and then two recursive calls here. Could be one depending on how your function's set up. Okay, that's it for the solution. You can check out the Jupyter Notebook with a written out explanation of everything we're doing here and an explanation on the complexity of the algorithm. Other than that, good job, and I'll see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to the Search Overview lecture. So this entire section consists of searching and sorting. those algorithms and how they work in Python. For the first half of the section, we'll discuss search methods, and then in the second half of the section, we'll discuss sorting. So right now, we're just talking about search. So in this half of the section, we'll discuss sequential search, we'll do an implementation of sequential search, talk about binary search, as well as an implementation of that, and then we'll talk about hashing and hash tables. So, a quick note, in Python, we can use the in operator to search for elements in a list. So for example, quick screenshot here at the bottom, you can check if 15 is in that list, which is not, so it returns a Boolean false. And then you can also check if 3 is in that list, which it is, so it returns a Boolean true. So what we want to really know is, how does that underlying process actually work, and what's the best way to search for things algorithmically? What's actually happening under the hood when you say something like 15 in this list? So what we're going to do is go ahead and get started by learning about sequential search and binary search and hashing, and see how those topics relate to actually searching for items or elements in a list or array. Okay, thanks everyone, and I'll see you at the next lecture where we're going to discuss sequential search. Hello everyone, and welcome to the sequential search lecture. So for sequential search, we're going to discuss the theory of sequential search. Later on, we'll see an implementation of sequential search, and we'll also do an analysis for big O on both unordered lists and then ordered lists. Okay, so sequential search is just a basic searching technique. You sequentially go through the data structure, comparing elements as you go along. So for example, here at the bottom we have an unordered list, and we're searching for the element 50. So we just keep going along the list until we either go throughout the whole list or we find the element. In this case, 50 was not present, but we still had to check every element in the array. Here's a good question though. What if the array was ordered? That means if the array was actually in a sorted order. So if the list is ordered, we know we only have to search until we reach an element which is a match, or we reach an element which is greater than our search target. So, for example, searching for 50, we can stop here since we know it's a sorted list once we reach 54, an element which is greater than our search target. So let's do a quick analysis. For an unordered list, in the case where the item is present, our best case for big O is 1. That means we hit it on the very first try. Worst case is that it's the very last element of the list, n. So we have to go through n elements of that list to find it. So that means the average case is just going to be n over 2. What about if the item is not present? That means in both the best case and the worst case, you would have to search through every single item in the array, or that list. So that means your average case is going to be n. However, on an ordered list, if the item is present or not present, then you're going to have 1 and n as your best case and worst case. So just to pass over those column names, best case, worst case, average case. So your best case, if the item is present and not present on an ordered list, is 1. Your worst case is just going to be n, and then your average case is n over 2. So what we're going to do is some basic implementations of a sequential search, and we'll do both ordered and unordered implementations. So we have an implementation for accepting an ordered array and an implementation for accepting unordered arrays. And we'll see how those differ. Okay, so hopefully that was a pretty basic concept, just a sequential search. You go through the array, keep going through that list looking for the elements, and then if you find it, you find it. If you don't find it, however, you have to go through every single element in that array. If you know it's an ordered list, though, you only have to keep going until you find either the element itself that you're searching for, or an element that's bigger than the element you're searching for. Okay, so let's go ahead and implement this in the next lecture. Thanks, and I'll see you there. Hello everyone, and welcome to the implementation of sequential search lecture. So again, you can check out the previous video lecture for a full breakdown, but in this notebook all we're going to do is go ahead and implement sequential search for an unordered list and then adapt it to an ordered list. So let's go ahead and implement this. I'm going to go ahead and jump to a empty Jupyter notebook and start writing out my function for a sequential search. So first thing I'm going to do is just go ahead and say def to start off our function, and we'll call this seq search. You can call it whatever you want. And it's going to take in two arguments, the array or that list that we actually are searching through, and then the element or item we want to find. I'll call them ARR and ELE respectively. So this is just going to work on unordered lists. So I'm going to go ahead and start at position 0. I'll create a variable called POS for position, start it at 0. And I'm going to create another variable called found. This one's just going to be a Boolean, and it's going to start off as false, and it's going to become true if we ever find the element in our list. So what we can just do is say while the position is less than the length of our array and not found, meaning we haven't found it yet, I can just say if the value of the array at that position is equal to the element, then we found it. So I can just say found is then true. Else, what we're going to do is just keep moving one down. So I'm just going to say that the position, add 1 to it. And this is the same as just saying POS equals POS plus 1. All right. And then once you're done with that while loop, you can just return the found element. So it's a pretty simple idea. Let's go ahead and make sure it works. I'll say 1, 2, 3, 4, 5. And then call sequential search, pass in the array, and let's say I'm going to search for 6. So you notice it'll return false, meaning we never found it. Let's go ahead and search for 3, and it returns true. Let's check it on the edges just to make sure it's working. 1 is true, perfect, and 5 is true. All right, so hopefully that should have been pretty logical. You're just going through every single element, so n items in that array, checking if it matches up to your target, and then changing that Boolean variable. But remember from the previous lecture, we said if we know a list is ordered, we only have to check until we have found the element or an element that can be greater than it. So what we're going to do is edit our code a bit so it's a little more efficient given that we know it's ordered. So I'm going to go ahead and recall this ordered sequential search. And again, we start at position 0. We still have the target, that found variable, which will become true if the element's in the list. But I'm also going to start a new variable called stopped. And I'll set that equal to false. That's basically going to be a stopped marker. And in this case, I'm going to say, while position is less than the length of the array, meaning we're still going through the array, and not found, we haven't found it yet, and not stopped. And that's going to come into play when we reach an element that's greater than our target element. Given that we know, we can even write it as a doc string here, input array must be ordered. Let's say ordered / sorted. Okay, so we have that as a check. So again, we're going to go see if we have a match. Else, what we're going to do is two things. We're going to say if the array value at that position, that element, is greater than the element itself, we'll just say stopped is equal to true, meaning we've already passed the limit, so we reached an element that was greater than our target element, so we're not going to continue going. Otherwise, we're going to move on. So then we'll actually say else and shift this code into that block. Okay, so we can go ahead and test this out. We're going to just say this is already a sorted array. Let's add a couple more items to it. So now it's 1 through 10. I'm going to do a sequential search, and that's true. Let's say 12, and that's false. So you can mess around with this. It should work because we basically just added this check here and the stopped variable. All right, so hopefully for you, sequential search, both the implementation and the theory around it, it's actually pretty basic. You're just going through that array and doing the most logical thing. You're checking every element, if it's an unordered list, if you know the list is sorted or ordered beforehand, and let me change that to must, sorry about that. So if it's ordered or sorted beforehand, you can just go ahead and add a stopped variable for it. Okay, that's all there is to it, and I will see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to the lecture on binary search. So, we're going to go over binary search. In the next lecture, we'll do an implementation of binary search, and we'll also discuss the iterative and recursive versions of binary search. So, in the last lecture, we talked about implementing sequential search and how we had different implementations for ordering or ordered lists and unordered lists. So we can actually take greater advantage of the ordered list. So if we know a list is already ordered, instead of searching the list in sequence, we can do a binary search, which will start by examining the middle item. So, a binary search will start by examining that middle item. If that item is the one we are searching for, we're done. If the item we're searching for is greater than that middle item, we know that the entire lower half of that list, as well as the middle item, can then just be eliminated from further consideration. So we can already drop that off of our overall search. Then the item, if it's in the list, must be in the upper half. So we just keep repeating that process with the upper half. Start at the middle item of that upper half, compare it against what we're looking for, and again, we either find it or split the list in half, therefore eliminating another large part of our possible search space. For example, let's look at the previous array we looked at a couple lectures ago and search for 54 again. Instead of starting at the beginning here at 17, like a sequential search, what we're going to do is start right in the middle. Then we'll check this number against the target value, which is 54. Since this number is less than 54, it's 44, we know that everything in the lower half of the list can now just be discarded. Then, using the upper half of the list, we just continue on. So we jump to the middle here, which is 65. Since it's greater than, we can start and keep doing this, basically splitting that list in half, which is why it's called binary search, and continually go until we find the actual element that we're looking for. So, binary search uses divide and conquer. We divide the problem into smaller pieces, solve the smaller pieces in some way, and then reassemble the whole problem to get the result. So you'll hear that term divide and conquer quite a bit when you're studying data structures and algorithms. Let's do a binary search analysis. Each comparison eliminates about half of the remaining items from consideration. Then we want to know, what is the maximum number of comparisons this algorithm will require to check the entire list? In this case, it depends on the number of comparisons and approximate number of items left. So if you have to make just one comparison, then you have about n over 2, approximate number of items left. With 2, you get n over 4, 3, n over 8, etc., all the way until you get to I comparisons, just a general term. For n items, then you're doing n over 2i, 2 to the power of I, approximate number of items left. Alright, so up next, we'll see how to implement two versions of that binary search, and you can check out the Jupyter notebook related to this lecture for more information on binary search. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of binary search lecture. So here's your example notebook. It's called Implementation of Binary Search, and you have two versions, an iterative version and then a recursive version. So we're going to go ahead and go through both of them here, code them out, explain what we're doing along the way, and then you have the reference of the notebook in case you want to go back and check it out. Let's get started. I went ahead and started a new notebook here. I'm going to start off with my first function, just called binary search. It's going to take in an array and an element. Let's go ahead and zoom in here. Then I'm going to say my first and last index values are going to be variables. I'll say first equals 0 and last equals the length of the array minus 1, because indexing starts at 0, and then I'll say found is equal false. And we'll just use found as a marker just like we did for sequential search, whether or not if we found it or not. The target element, that is. Then I'm going to say while first is less than or equal to last and not found, meaning we haven't found our target element yet, we'll go ahead and make a middle marker. In that case, we'll call mid a new variable, and that's just going to be first plus last divided by 2. And then what I'm going to say is check if there's a match found. If there's not, I'm going to set up new midpoints. Meaning I'm going to go ahead and say if at that mid location we found the element, I'll just say found equals true, and that's the end of the analysis there. Otherwise, else, I'm going to go ahead and say if the element is less than that value, then my last equals mid minus 1. Else, my first variable is going to be equal to mid plus 1. So all this loop is doing here, or this block of code, is just basically deciding if you're going to use that lower half of the list or the right half of the list. This is the case for lower, this is the case for the right half. And after that while loop is done executing, meaning we've either gone through all the possible elements through our binary search, or we just actually found it and it equals true, at the end we just return found. Okay, let's go ahead and run this, make sure we have no errors. I'm going to go ahead and make an array. And keep in mind the array must already be sorted. We're taking further advantage of the fact that we have a sorted array. This won't work on an unsorted array. Then let's go ahead and call binary search on the array, and we'll look for, let's say, 4. Okay, perfect. It's in there. Let's look for 10 just to make sure. And now let's look for an item that's not there, 13. False. Okay, great. So our normal version of binary search implementation is working. Let's go through it one more time just to make sure we understand what's going on. We set up a function to take in the array and the target element you're looking for. We set up two variables, first and last, which are basically index markers. Then we set found is equal to false. And then we're going to continually go until first is less than or equal to last, and we haven't found the element yet. We set a variable called middle, which is just first plus last divided by 2, to get that middle index of that list, or the sublist. And then we say, if at that middle index we have found the element, then it equals true. Otherwise, if the element is less than, the target element that is less than the element at that middle, we're going to set last equal to mid minus 1, meaning we've chosen that lower half of the list. Otherwise, we'll set first equal to mid plus 1, meaning we've chosen that higher right half of the list. Once we've done through this while loop, we'll just return the found boolean. Either we found it, so we set it equal to true, or it was never changed and we never found it, meaning it was equal to false. All right, so let's go ahead and implement a recursive version of binary search. So what we're going to do here is start off by, let's just go ahead and clear out these cells. And I'm going to go ahead and say REC for recursive, BIN for binary, and then search. It takes in an array and an element. Remember, for recursive algorithms, we need to start off with a base case. In this case, we'll say if the length of the array is equal to 0, return false. So what we're going to be continually doing is basically recursively calling our binary search function, but if we finally got an array that's equal to 0, as we keep splitting it, then we know we never found the element. So that's our base case. Let's go over the recursive case. So we set a mid, that middle variable, equal to the array, the length of the array divided by 2. And similarly to the last implementation, we say if the array at that middle index is equal to the element, then we just return true, we found it. Otherwise, we'll say else. We're going to call this again on the second half, or call it on the first half. So what I'll say is, if the element is less than the value at that middle array, I'm going to return a recursive call here. I'm going to say rec binary search, and I'm going to call it on that second half of the array. Otherwise, else, I'll return a recursive call on the array from mid plus 1 all the way to the end. And this is really similar. This is just a recursive version of choosing which half of the list to continually go on. So if we scroll, oh, we don't have it anymore. But if you remember from the previous, let me just hop over to the Jupyter Notebook so I can show you. We had essentially this set of midpoints where we went either for the lower half of the list or the higher half using this comparison where we set up our last and first variables. We're doing the same thing here except for a recursive call where we use index slicing to pass in which half of the list we want to recursively continue on. Okay, let's go ahead and make sure we have no errors here and that it worked out. I'll call it on that same array. Let's just go ahead and print that array, make sure it's sorted. Okay, we're good. Call it on that array, and I'll search for the item 3. Great, it's in there. And if I search for 13, we get false because it's not in there. So, looks like it's all working out. Go ahead and review the Jupyter Notebook where it has comments at every step. Put in print statements if anything's not making sense for you. But again, hopefully this should have been a pretty basic idea of just binary search. You're splitting that list in half, continually checking if that middle point indexed element is equal to the element you're looking for. If not, you just split it in half again, depending on whether this is true or not. Your target is less than the array value at that middle index. Okay, that's it for the implementation of binary search in 2 versions. Make sure you really understand binary search, just the logic behind it, because you're going to see that concept again and again throughout various interview questions. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on hashing. In this lecture, we'll cover hashing, hash tables, hash functions, something called collision resolution, and in the next lecture, we'll actually implement our own hash table class using Python. Something to keep in mind is that there's going to be a lot of topics presented throughout this lecture, so make sure you set out enough time to fully understand the topics presented here and take notes on them. Okay, so we've seen how we can improve search by knowing about structures beforehand. If you remember back to sequential search or binary search, we're able to improve our search big O by knowing if an array was already sorted when we were going to search for an object. We can actually build a data structure that can be searched in constant time, order 1. This concept is referred to as hashing. Alright, so what is hashing and what's a hash table? A hash table is a collection of items which are stored in such a way as to make it easier to find them later. Each position of the hash table, known as slots, can hold an item and is named by an integer value starting at 0. So, for example, we will have a slot named 0, a slot named 1, a slot named 2, and so on. Initially, the hash table contains no items, so every slot is empty. We can implement a hash table by using a list, with each element initialized to the special Python value none. So, for example, here's a figure of what an empty hash table with size m equals 11 would look like. So we have from 0 to 10 essentially indexes of our list, and they're all filled with none. So the mapping between an item and the slot where that item belongs in the hash table is called the hash function. And this is the real key to how a hash table works. The hash function will take any item in the collection and return an integer in the range of slot names, between 0 and m-1. So, what we want to think about is how should we use hash functions to map items to slots. One hash function we can use is known as the remainder method. When presented with an item, the hash function is the item divided by the table size, and this is then its slot number. Let's go ahead and see an example of how this works. So assume that we have a set of integer items, let's say 54, 26, 93, 17, 77, and 31. We've pre-assigned an empty hash table of m equals 11. That was that figure we saw earlier of just essentially an empty list. So what our remainder hash function is then, is it's a function that takes in the item and returns the item divided by 11, its remainder, so that mod function, or that mod percentage sign you can use in Python, which just returns the remainder of a division. Let's go ahead and see the results as a table. So, 54 mod 11 returns 10. 26 mod 11 returns 4. 93 mod 11 returns 5. 17, 6, 77, 0, and then 31, etc. 9. So we're doing 54 mod 11 to get the hash value, meaning 54 divided by 11 is going to be 44 remainder 10. That means we're now ready to occupy 6 out of those 11 slots, and this is referred to as the load factor, and it's sometimes denoted by this equation. The load factor is equal to the number of items divided by table size. And in this example, the load factor is 6 number of items divided by a table size of 11. That means our hash table now looks like this after it was loaded with those items. So again, we just use that hash function, in this case the remainder method, to assign slots, those number slots, to the elements or items we wanted to put into it. So for example, let's take a look here at 77. 77 was the element that we wanted to put into a specific slot in our hash table. So 77 divided by 11 is 7 with remainder 0. That remainder is the slot that we put it in. When we want to search for an item, all we have to do is simply use the hash function to compute the slot name for the item and then check the hash table to see if it's present or not. That allows the searching operation to be done at big O1, since a constant amount of time is required to compute the hash value and then index the hash table at that location. Then you might be thinking, what if you have two items that would result in the same location? We discussed about 77 mod 11 being 0, but if you had another item such as 44, that would also be the same slot number, 0. This is known as a collision, sometimes also known as a clash. We're actually going to learn how to deal with them a little later on in this lecture. What we're going to do is learn more about hash functions in general first, before we talk about collision resolution. Now let's discuss hash functions a little more formally. A hash function that maps each item into a unique slot is referred to as a perfect hash function. That means our goal is to create a hash function that minimizes the number of those collisions. It's easy to compute and evenly distributes the items in the hash table. Let's discuss a few techniques to do this. There's another hash function called the folding method. And the folding method for constructing hash functions begins by dividing the item into equal sized pieces. The last piece may not be of equal size. These pieces are then added together to give the resulting hash function, or hash value, excuse me. So let's go through a more complicated example. Let's say our item is the phone number 436-555-4601. What we would do is take the digits and divide them into groups of 2. So 43, 65, 55, 46, and then 01. Then, after adding all these numbers together, we get 210. If we assume our hash table has 11 slots, like in the previous case, then we need to perform the extra step of dividing by 11 and keeping the remainder. That means 210 mod 11 is 1. So the phone number, 436-555-4601, then hashes to slot 1. Another hash function method is called the mid-square method. For the mid-square method, we first square the item and then extract some portion of the resulting digits. For example, if the item were 44, we would first compute 44 squared, which in this case is 1936, and then extract the middle two digits, 93, and perform the remainder step to get 93 mod 11 equals 5. Here we have a simple comparison table of various items, and then what their slot numbers would be if you use just the remainder method, or if you use something like the mid-square method. Okay, so let's discuss non-integer elements. We can also create hash functions for character-based items such as strings. The word cat can be thought of as a sequence of ordinal values. And if you're not familiar with ordinal values, in this case just think of them as a way of converting that string into numbers. You can go ahead and do a Wikipedia search for ordinal values if you want a fuller breakdown of this. But in this case, if you just want to use Python, you can actually call in the built-in function, ord, pass in the particular letter of that string, and it will give you an output of the ordinal value that relates to that string or that element of the string. In this case, passing in cat, C-A-T, would result in 99, 97, and 116, which you can then sum up to get 312, and you can perform the remainder hash function on that, and 312 mod 11 equals 4. Okay, now we've discussed hash functions in a little more detail, let's go ahead and talk about collision resolution. One method for resolving collisions looks into the hash table and tries to find another open slot to hold the item that caused the collision. So, for instance, we could start at the original hash value position and then move in a sequential manner through the slots until we encounter the first slot that is empty. This collision resolution process is referred to as open addressing, in that it tries to find the next open slot or address in the hash table. By systematically visiting each slot one at a time, we are performing an open addressing technique called linear probing. So let's take a look at an example of this. Consider the following table. Here we have 77 in slot 0 because 77 mod 11 is equal to 0. But what if we also had to add 44, 55, and 20? So with linear probing, we basically just keep moving down until we find an empty slot. Meaning we've inserted 44, instead of at 0 we moved down, checked that 1 was empty, and filled it in. 55, we tried 0, it didn't fit because it wasn't empty. Then we moved over to 1, again it wasn't empty, so we filled it in at 2. And we did a similar thing for 20. So, one way to deal with clustering is to skip slots, thereby more evenly distributing the items that have caused collisions. So if you notice back here, on one slide back, we'll eventually have to keep clustering things towards the beginning of our hash table. But if we want to deal with clustering, we can actually skip a certain number of slots, thereby evenly distributing those items. So the more general name for this process of looking for another slot after a collision is called rehashing. And the variation of the linear probing idea is called quadratic probing. Instead of using a constant skip value, in the last case it was just 1, we use a rehash function that increments the hash value by 1, 3, 5, 7, 9, and so on. Okay. Another note is that this means if the first hash value is h, the successive values are h plus 1, h plus 4, h plus 9, h plus 16, and so on. An alternative method for handling the collision problem is to allow each slot to hold a reference to a collection or chain of items. Chaining allows many items to exist at the same location in the hash table. Then, when collisions happen, the item is still placed in the proper slot of the hash table. So this is what chaining would look like. Instead of going around and probing for a new empty slot, you would just basically chain off the original slot. So numbers such as 44 and 55 would chain off that 0 slot number. And as more and more items hash to the same location, it should be noted that the difficulty of searching for the item in the collection increases. Alright, so we've covered a lot. We've covered hashing, hash tables, various hash functions, and collision resolution methods. Up next, we're going to implement our own hash table class. Before you check that out, I would recommend that you check out the resources section of this lecture, which has the PowerPoint and these slides we covered. Go ahead and walk through them, check with your notes, and make sure you fully understand the basics of hashing and hash tables and hash functions. Alright, thanks everyone, and I'll see you at the next lecture, Implementation of a Hash Table. Hello everyone, and welcome to the Implementation of a Hash Table lecture. In this lecture, we will be implementing our own hash table to complete our understanding of hash tables and hash functions. Make sure to review the video lecture before this to fully understand this implementation. Also, keep in mind that Python already has a built-in dictionary object that serves as a hash table. You would never actually need to implement your own hash table in Python. So, let's talk about map. The idea of a dictionary used as a hash table to get and retrieve items using keys is often referred to as mapping. In our implementation, we will have the following methods. So we'll have our hash table class, and that's going to create a new empty map. It returns an empty map collection. Then we'll have a put method. It'll add a new key value pair to the map, just like a default Python dictionary. If the key is already in the map, then it replaces the old value with the new value. We'll also have a get method. Given a key, return the value stored in the map, or none otherwise. We'll also have a del, which will delete the key value pair from the map using a statement of the form delete map key. We'll also have len, which will return the number of key value pairs stored, and we'll have in, the map and return true for a statement of the form key in map if the given key is in the map, false otherwise. And we'll explain that one a little more in detail when we actually get to it. So you have your Jupyter notebook here. All the code that we're going to be going over is available for you here, called class hash table, and you can check it out yourself. Note, it's a lot of code, but we're going to go through it and live code it out right now. So let's go ahead and get started. Alright, I started a new Jupyter notebook, and I'm going to go ahead and create class hash table, and it's going to be an object. And let's start by initializing some attributes. So I'm going to say def underscore underscore init underscore underscore pass in self. And the only thing I'm going to pass in for an attribute that we declare at first is just the size. I'll say self.size equals size. And then I'll create another attribute called slots. In this case, we're just going to have them be equal to none times self.size, where none is essentially an item or a list with an empty item. So let me just show you real quick what I mean by that. So this is a list with a none item. So when we multiply it by self.size, imagine we said self.size was going to be 4, then it's going to give you a list with 4 nuns in it. So that should look really familiar from the previous lecture. Remember that initial hash table we just had as a list of nuns. And then we'll say self.data is equal to none multiplied by self.size. Okay, first method we're going to work on is put. And put is going to take in self, so we know what we're referencing, and then key and the data. So note for right now, we're only going to use integer keys just for ease of use with the hash function. Alright, so first thing we're going to do is just get the hash value. So I'll say hash value is equal to self.hash function, which is going to take in key and then the length self.slots. So we actually haven't developed the hash function yet, but I'll go ahead and mark it off right now. Hash function, and it's going to take self, key, and size. Right now we'll just have it as pass, but this is essentially going to be the actual hash function. So we'll get to that once we're done putting in the put method, but this is essentially just going to be the remainder method, that very first hash function we saw. Okay, So moving along, what we're going to do is after we get our hash value, meaning we insert the key, the number, the size, we'll get a hash value back. Then we'll check if the slot's empty. So if self.slots at the hash value is equal to none, then we know it's empty, so we can say self.slots hash value is equal to the key, and then self.data at the hash value is equal to that data we wanted to input here. All right, so that's the most basic situation you have where it's already none, it's empty, and your hash function lined up with an empty slot, so you fill in the key and the data. Let's go ahead and actually fill out this hash function now. We'll have it be the remainder method. So that means it's just going to return the key mod size. All right. Something to begin to note, as we've discussed before, if we have a collision case here where the hash value does not equal none, we'll have to take that into account. In this case, we'll need to basically create a rehash, so finding next possible positions. For that case, let's go ahead and create a method called rehash. It'll take in the old hash value, the size of the array, and it's going to find the next possible position by just saying return the old hash plus 1 modded by the size. So this is essentially just moving along, trying to find the next empty slot. So now that we have rehash done, we can continue to fill out our put method. So if the slot is empty, we fill it in with our key and data. Else, if that's not the case, so if the key already exists, we'll just replace the old value. So we can say if self.slots hash value is already equal to the key, meaning it's already in there, then we'll just say self.data at the hash value is equal to data. All right. So otherwise, what we're going to do is try to find the next available slot. So I'm going to say else, say next slot equals self.rehash hash value with the length of self.slots. So that matches up to what our rehash function over here, this method, was taking. So then what we're going to do is try to get to the next slot. So we'll say while self.slots, in this case we'll just call it next slot, that variable we just made, is not equal to none, and self.slots of the next slot does not actually equal the key. What we can do is just say that the next slot is equal to self.rehash, take in the next slot, and the length of the current slots, which is self.slots. Okay, so that's to get the next slot, and then we'll set the new key if none. So that means if self.slots, so that list that we're keeping track of slots, next slot is equal to none, then we just replace the value. So we'll say self.slots next slot equals key, and then self.data at the next slot is equal to data. Otherwise, we just replace the old value. We'll say else self.data next slot is equal to data. All right, let's go ahead and zoom out a bit, make sure we fully understand what's going on, because that was quite a bit of information and quite a bit of coding. So here we have right now our entire push function, and this is supposed to be on a new line right here. Okay, let's go ahead and just rerun over what's going on and make sure it compares correctly to what we have here in our official Jupyter notebook. So first thing we're doing is just initializing our hash table. We put in a size, and then we create slots and data. These are just two arrays of none with self.size, and we're using just a Python list as we showed earlier. Then we have our put method. That's going to put in a piece of data to the correct key. So where do we actually put this data? We use the hash value, which we got from the hash function. In this case, for the hash function, we just use the key and the length of self.slots, the actual slots we specified earlier, because we're using the remainder method over here. So after that, we just say if a slot is empty right here, so if self.slots hash value equals none, meaning it's empty, we just fill in the key and the data itself. Otherwise, if the key already exists, we go ahead and replace the old value. And then in that case, otherwise, meaning it doesn't exist, we actually have to find the next available slot. Meaning we have to say next slot equals self.rehash with that hash value. We get to the next slot over here, so we continually go while, and then we set the new key if none. So this is us setting the new key. Otherwise, we just replace the old value. Okay, so we found out that if we needed to use a rehash to find the next possible position, we just continue along taking the old hash function, adding 1, and then again just doing a simple remainder method. Let's now focus on getting items given a key. I'll go ahead and zoom in for this while we focus on the get method. So I'll say def get, and in this case it's just going to take in a key, just like we would for a normal dictionary. And it's going to return items, basically get items, which are our data, by taking in a key and returning the data that's matched up with that key. We're going to set up a couple variables for our search. We're going to say start slot is equal to self.hash function, which takes in the key and then the length of self.slots. We'll start off with data being none. At the end, we'll actually return data. We'll have stop equals false, just a boolean to tell us when to stop. We'll say found is equal to false. And we'll set a position marker called just equal to start slot. Okay, so right now we have start slot, and this is just telling us what slot do we start off on in our search based off the hash function. And because of our rehash method where we're adding, if it's not a hit at the hash function, what we can end up doing is just continuing on until we actually find it. So until we discern that it's not empty or found and haven't stopped yet, meaning while self.slots at that position, which is the start slot, does not equal none, and not found, meaning our Boolean variable that data hasn't been found, and not stop, meaning we haven't stopped yet, then we'll just do a check. We'll say if self.slots at that position is equal to the key, then we found it. So we can say found is equal to true, and we just set the data equal to that value, which is self.data position. Else, we'll say position equals self.rehash at the position, length of self.slots, And we'll do an additional check here. We'll say if position is equal to start slot, then we know to stop. We just say stop equals true. And then finally, we just return the data. Let's go ahead and zoom out and make sure we break this down completely. So we're trying to get a value or some data based off its key. So we set up our variables for our search, the slot we're going to start in, the data, which is none right now, whether or not we've stopped, whether or not we've found it, and the position starts off at start slot. And essentially we keep going until we discern that it's not empty or found, haven't stopped yet. So while the self.slots at that index of position does not equal none, and I need to change this to an actual keyword, none, and not found and not stop, then if self.slots position equals to key, then found equals true, and we just go ahead and return that data. Otherwise, we have to use rehash to continue going. All right, let's go ahead and add two more methods. And these are going to be def underscore get item. And these are just special methods for use with Python indexing. Self key. And we're just going to return self.get key. And the other thing we're going to do is say def set item underscore self key data. And in this case, we're just going to put it. We'll say self.put key data. And what this allows us to do, these are just special methods in Python that allow you to use that bracket notation. All right, so we wrote quite a bit of code here. I mean, it's a lot of code, but we also just basically create our own hash table using lists as our base. Let's go ahead and make sure it worked out. And I won't be surprised if we get an error, but hopefully we don't. Let's see if we were able to implement it correctly. So I'll make my hash table. I'll give it a size of 5. And let's go ahead and put on our first key. So I'll say h of 1 is equal to 1. Then we'll say h of 2 is equal to 2. And let's say h of 3 is equal to 3, the string 3. And let's zoom in on that since we're not coding a whole lot of stuff out anymore. So we create our hash table, assign some keys and some data. Let's see if we can actually retrieve it. All right, so it looks like that's working out. So 1, 2, and let's check finally 3. Looks like that's all working out. So even though this is a rudimentary implementation, we can play around with it by implementing different hash functions. So what I would recommend to you is to implement different hash functions. Meaning if you're able to take this existing code and mess around with hash function and rehash to try to implement the other hash functions we talked about throughout this lecture that weren't just remainder methods. Remember we had those middle numbers and also those square methods, as well as some ordinal value methods. Go ahead and try those out and play around with it. That way you can really build your understanding of hash tables and hash functions. Again, realistically, you're probably not going to be making your own hash table objects and classes because you already have things such as Python dictionaries, or in other languages you already have hash tables that you don't need to build out yourself. Okay, again, you have the Jupyter Notebook available to you. It has all the code so you can copy along, paste it, read it at your own pace, since I know we went through quite a bit. And just to note, it also has comments everywhere explaining every code block for you. So really go over this code slowly, make sure you understand it, and have fun with it. Mess around, make your own hash functions, and check it out. Okay, so that's it for the hash table implementation. I know it was a lot, so make sure you take your time and go over the Jupyter notebooks that are available to you. And in the next lecture, we're going to begin to discuss sorting algorithms. All right, thanks everyone. and I'll see you at the next lecture. Hello everyone, and welcome to the sorting half of this section of the course. So we've already discussed how to search for items, and now we're going to discuss how to sort data structures, specifically in Python, but these algorithms are used in all languages. So, in this section, we're going to be discussing 6 main algorithms used commonly in computer science for sorting. And it's going to consist of explanations on how the algorithms work, and we're also going to be implementing these algorithms in Python. Specifically, we'll be discussing about the bubble, selection, insertion, shell, merge, and quicksort. So to put this in a little bit of context, a common interview question consists of being asked to implement a sorting algorithm. In real life, you'll probably never have to implement your own sorting algorithms, since the best ones are already built into the programming language of your choice. So in this lecture, we're going to focus on the context of being asked how to implement a sorting algorithm in an interview setting. The lectures are going to focus on 3 things: a verbal explanation, a visual explanation, and a full implementation of the sorting algorithm discussed in that lecture. Alright, with all that being said, let's go ahead and get started. Our first algorithm for sorting we're going to learn about is bubble sort. I'll see you at the next lecture. Hello everyone, and welcome to this side lecture on visualizing sorting algorithms. So in this lecture, we're just going to give you some resources and websites that you can use to visualize the sorting algorithms that we're going to be discussing throughout the rest of this section. Keep in mind, we will give you the resources and specific links for each sorting algorithm as the lecture on that algorithm comes up. So you'll be reminded on these links and have resources constantly throughout this section of the course. But what I want to do here is go ahead and show you the websites in particular, how to use them, and how to best take advantage of them for your learning. So let's go ahead and jump to the browser. Okay, so the first website I want you to be aware of is www.sorting-algorithms.com. This is a great website for visualizing sorting algorithms, as well as seeing the pseudocode and basic algorithm definition. So for instance, if you want to learn more about the insertion algorithm, you could click here on the specific algorithm name. It'll go ahead and tell you about the pseudocode for the algorithm, tell you its properties, give you a brief discussion on the algorithm. But if you want to actually visualize it, what you can do is you have 4 different options on the type of data you have, and you can go ahead and click them, and it will begin to actually visualize the algorithm. So this is really useful and a great website. Let's go ahead and check out another one. The next website we want to check out is called visualalgo.net. That's visualgo.net. Again, this is a great website. You can have here the lists of algorithms you want to check out. If you go down to the left corner over here, you can go ahead and say create if you want to create your own personal list. And you can click here, sort, when you're ready to actually implement the sorting algorithm. What's really great about this website is if you go over here on the right, you'll notice there's 2 tabs. You can go ahead and open them up, and they will actually show you the pseudocode as you go along, and it'll tell you what line of the pseudocode you're on. So this is a really great website for learning the algorithms. Just keep in mind that there's differences in how you can actually implement the algorithm. So some algorithms will implement the sorting from the left side, others from the right side, others will check if it's greater than, some will check if it's less than. So although the basic concept of the algorithm is the same, sometimes the way it's implemented is slightly different than the way we do it in the lectures. But just keep that in mind. You can also change the speed of the algorithm here, over at the bottom left corner, and you can pause and play through each of the steps. Lastly, Wikipedia. If you just do a Wikipedia search on the algorithm, it should usually have some sort of visualization that's static, as well as a visualization that's animated. And all the information, performance, etc. about the algorithm is available for you on the Wikipedia website. Okay, so those are the main resources I wanted you to be aware of: www.sorting-algorithms.com, visualalgo.net, that's visualgo.net, and then Wikipedia pages. You'll always have links to these visualization websites in the notebooks. With that being said, let's go ahead and get started. Thanks everyone. Hello everyone, and welcome to the lecture on bubble sort. So in this lecture we'll learn how the bubble sort algorithm works, and we'll also see some visualizations of it. After this lecture, we'll implement bubble sort in Python. So let's go ahead and get started. So as I mentioned, we'll have an explanation, a visualization, and afterwards an implementation, all on bubble sort. So the bubble sort, how it works is it makes multiple passes through a list. It then compares adjacent items and exchanges those that are out of order. So each pass through the list places the next largest value in its proper place. And in essence, each item bubbles up to the location where it belongs. That's how this algorithm gets its name. So let's go ahead and see a quick figure that explains this. So here what we're looking at is just a drawing of a first pass of a bubble sort. So the shaded items, and you can see them here kind of along a diagonal, are the ones being compared to see if they're out of order. So if we have a list of n items, then there's going to be n minus 1 pairs of items that need to be compared on the first pass. And it's important to note that once the largest value in the list is part of a pair, it will continually be moved along until the pass is complete. So we can take a look here and see that in comparing 54 versus 26, there's an exchange since 54 is greater than 26. Then we move on to the next pair, 54 versus 93. No exchange, 93 is bigger than 54. We keep going down and doing the exchanges as needed when we compare the two elements to check which one's greater than the other, and then we do a swap. So you can see certain elements are kind of bubbling to the top if they happen to be greater than the other element that's it's being compared to. So eventually 93 is in place, that element number 93 is in place after the first pass. So at the start of the second pass, the largest value is now in place. There are n minus 1 items left to sort, meaning that there will be n minus 2 pairs. Since each pass places the next largest value in place, the total number of passes necessary will be n minus 1. Then after completing the n minus 1 passes, the smallest item must be in the correct position with no further processing required. Alright, so what we're going to do now is go ahead and check out some visualizations. So let's go ahead and jump to the notebook where there are some useful links for you to check out. So if you go to the sorting and searching folder, here I am on NBViewer at nbviewer.ipython.org. Under the Python for Algorithms, Data Structures, and Interviews, there's a sorting and searching folder, and you can click on implementation of bubble sort right here. It'll take you to this notebook, which also has a quick explanation, but more importantly, it has resources for review and an implementation that we're going to be looking at in the next lecture. But if you click on each of these resources, you'll get the following. You'll get a link to Wikipedia, and Wikipedia has pretty nice resources for learning about the various sorting algorithms. And it also has little animations here for you to check out, performance information, so I encourage you to check those out, or look at the Big O cheat sheet from the Big O section of the course. It has an explanation, step-by-step examples, so you can see here a first pass example similar to what we just saw. And then it also has pseudocode implementation. The second link that you're going to see is from a website called visualalgo.net. This is really one of the key resources for you to learn sorting really well. So what it does is it has a list of sorting algorithms. It also visualizes other algorithms, which we'll get to later, but it's really useful for visualizing sorting algorithms. So you can go ahead and click that link, visualalgo.net/sorting. It'll take you to a page that looks like this. You'll get a little walkthrough at first. You can click next here. You can do bubble, select, insert, merge, quick, rquick, count, and radix sorting algorithms. Select which one you want to do. And you can either create your own new list that you can define or let the computer generate a random list. And then to sort the elements, you click sort and then go. And then you'll view the visualization here. And what's really nice about this, and this is probably the best part, is that as the action is being carried out, each step's described here in this little status panel. And you can follow some pseudocode here, which traces the algorithm. And the pseudocode looks really similar to what Python does. And you can control the animation with the player controls here at the bottom. Alright, so just to show you a quick run through, we click here, we can go ahead and click sort, and click go. And you'll notice it didn't run, and that's because up here you have to click exploration mode. So I was on tutorial mode. Go ahead and click exploration mode. then click Go, and you'll start to see the swaps taking place. And you can control the speed here or go back a step, rewind, etc. So you have a status and it's going through the pseudocode here. So that's really useful. So I really encourage you to make the most of this resource. This is probably the best way to learn them if you're a visual learner, especially for sorting algorithms. Really the best way is to watch the animation a couple times, really learn it well, understand what's happening, and then implement the code yourself. Okay, so I encourage you to check out this visualalgo.net resource. What we're going to do now is pause this and check out the other links. Another one that's on that list is www.sorting-algorithms.com/bubblesort. It has all sorting algorithms and all kinds of initial conditions. Here, it has an algorithm for you to follow, basic pseudocode, has the properties, what kind of big O it has, a little bit of discussion on it, and 4 examples on different types of lists. So it has random lists, nearly sorted lists, a reverse list, and a few unique lists. So if you click on them, they'll start going through the animation of being sorted. So you can actually click on all these, and you'll see how the algorithm is taking place visually. Okay, finally, we have this bubble sort animation here using JavaScript. And this is the one I'm going to use just to quickly go over again what we're actually doing when we're performing a bubble sort. So keep in mind that what we're going to do on this first pass is keep comparing and doing what are known as sometimes swaps, this exchange operation. So between 6 and 8, 8's already bigger, so we're not going to do a swap. Between 8 and 1 here, we will do a swap. 8 and 15, no swap, so now we're comparing 15 and 9. This is going to be a swap. 15 and 20, no exchange here, so we move on to 20. So notice basically this in-between line is what we're moving down. So we're going to be moving down this whole list on this first pass here. And you can kind of go faster on your own or hold it down and notice the patterns here. How eventually, towards the end of the list, you're getting the sorted items. So they're bubbling up to the top here. And if you just hold this down, you can see it in a little faster. Okay, so go ahead and check out those visualizations so you really understand what's actually happening here. But the basic idea of bubble sort is you're bubbling up throughout the list and doing exchanges along the way so that eventually you've sorted the entire list. In the next lecture, to make this really clear, we're going to implement our own bubble sorting algorithm in Python. Alright guys, I'll see you at the next lecture. Hello everyone, and welcome to the implementation of a bubble sort lecture. So as a quick reminder, the bubble sort makes multiple passes through a list. It compares adjacent items and exchanges those that are out of order. Each pass through the list places the next largest value in its proper place. So in essence, each item is bubbling up to the location where it belongs. So as always, here's the notebook. You have resources for review, including visualizations, and we're going to go ahead and program out our own implementation in Python and explain as we go along. So go ahead and open up a new Jupyter notebook. Let's go ahead and zoom in here real quick, and let's get started. So first thing we're going to do is go ahead and start writing out our function. In this case, we'll just call it bubble underscore sort, and we'll take in an array ARR. Now again, in Python, this is just going to be a normal list, but we'll treat it with the term ARR just so we can generalize it to an array. So what we're going to do is say for n in range, and this is where it's going to get a bit tricky, but we're basically going to arrange it backwards, and I'll show you what I mean by that in just a second. We're going to say length r minus 1 to 0 in steps of -1. So let me go ahead and show you what that looks like. I'm going to go ahead and say pass here, and then let's go ahead and say r is just 1, 2, 3, 4, 5. And if I just go ahead and print this out, you'll basically arrange everything backwards except for the very last element, since we're going from -1. So just keep that in mind as we go along, what this is actually going to do. If you're using Python 3, in order to see this result, you would have had to have called list on this, since range is just a generator in Python 3. Okay, so let's go ahead and keep on moving. So the next thing we're going to do is then say for k in range of n. So as we go along with that list, remember we had that 1, 2, 3, 4, 5. In this case, we're going to go all the way from k0 to n. So to understand this logic, what we're going to say is if the array at that value point, basically that index, is greater than k plus 1, let me fix those brackets there, k plus 1. So we're basically checking here if we're going to come to a point where we need to switch. So I'm going to say make a temporary variable equal to r of that k, that index, and then say r of k is equal to r of k plus 1, and then say r of k plus 1 is equal to that temporary variable. And that's really all there is to it for this implementation of the bubble sort. Okay, so let's go ahead and test out our solution, make sure it runs well, and then we'll break down step by step one more time what we're doing. So I'm going to go ahead and say create an array, and we'll say 5, say 3, 7, and 2. So that's already unsorted. We're going to call bubble sort on that array, that list, and then print out that array again. Okay, perfect. So it was sorted. Notice that I don't have a return function on a return keyword on this function, so it didn't actually automatically return it. If you wanted to, you could have added, in line with this for loop, return ARR in order to not have to redo and print that array. Okay, so let's go ahead and go one more time what's going on in this function. So I'm saying for n in range, and remember we are actually just saying everything in reverse order. So let's go ahead and show that one more time. So range of length of ARR minus 1, 0, minus 1. So if this is our example array, what we should see out is 3, 2, 1. So that's going to help us see what actual index we should be doing when we come to the k. So I'm going to go ahead and say print k and print n here. So if we run this on a very short array, these print statements might help us visualize what's actually happening. So if I say bubble sort r, you can go ahead and see the print statements and the actual arrays we're checking at that point in time. So I'm going to go ahead and say this is the n, comma, and then here I'm going to say this is the k index check, comma. All right, so you notice what's happening here is at every n, we're going to go ahead and do index checks from 0 up to that n. And this is where the bubbling is occurring. And remember from the diagram, we only have to bubble less and less as we continue on, depending on which side we're going from, and this side from the left. So go ahead and check this out. Definitely use print statements in case you're still confused about the steps themselves. But all we're doing here is saying from n at 3, since we have a length of 4, go ahead and do index checks at 0, 1, and 2. Once we've done all the way up to n, we'll go ahead and do to n equals 2, then we'll do 0 and 1, and then keep subtracting. And as far as the actual index checks, what's going on, we're just checking at the two adjacent elements in this array if one's greater than the other. If it is, we just go ahead and do a swap with these 3 lines here. We're using a temporary variable so we don't accidentally overwrite anything in that list or array. Okay, so that's it for the implementation of bubble sort. Hopefully you can see it's quite simple. As far as this line and this line, different methods may operate these 2 lines differently. So depending if you're running from the right of the list or the left of the list, you may bubble up in a different manner. But as far as our implementation, this actually makes sense. And this comparison is going to be very, very similar no matter which way you go. All right, Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to this lecture on selection sort. So in this lecture, we'll get an explanation of selection sort and get a look at some visualizations of selection sort. And in the next lecture, we'll actually implement it using Python. So the selection sort improves on the bubble sort by making only one exchange for every pass through the list. And in order to do this, a selection sort looks for the largest value as it makes a pass, and after completing the pass, places it in its proper location. So, as with the bubble sort, after that first pass, the largest item is in the correct place. And then after the second pass, the next largest is in the correct place. So this process continues and then only requires n-1 passes for a list or array of n items, since that final item will be placed after that n-1 ist or if pass. So let's go ahead and see a figure that shows the entire sorting process. So on each pass, the largest remaining item is selected and then placed into its proper location. So in this implementation, we're looking at the largest. In other implementations for selection sort, you can also look at the minimum. So depending on how you actually want to program your algorithm, you could either keep track of the largest elements or the minimum elements, the smallest ones. So in this case, if we decide to track the largest element, we look at our array, notice that 93 is the largest, so we place it at the end. Then, the next largest is 77, so we place it n-1 to the end. Then 55 is the largest, so we place it where it goes. 54 is then the next largest, place it behind 55. 44 is largest, but it actually stays in place. It's already at its correct location right after 54. And this process keeps happening until your list is sorted. So you're basically keeping track of, in this case, your largest element, and then pushing it all the way to the end, and you also have a tracker for where it should go in the array. Okay. And you're able to do this now in n-1 passes. You could have also kept track of the minimum and done this in the reverse. Instead of placing items or elements at the end of the array, you place them at the beginning. So you would start with, in this case, 17 as the minimum and push it all the way to the left. And then get 20 and then push it all the way to the left, etc., etc. So in the visualizations we're going to see, we're going to think about it that way, how you would implement this using a minimum tracker. Okay, so let's go ahead and look at some visualizations. So I've jumped to the Jupyter Notebook under the Sorting and Searching folder. It's called Implementation of Selection Sort. This is a notebook we're actually going to see in the next lecture when we implement this code for a selection sort. Here are some resources for review. And in this case, we can go ahead and check out the visual algo or the selection sort animation. Let's go ahead and do the selection sort animation. So if we get started on that first step, we're going to grab the minimum element, which was 1, and then place it at index 0. And now we're going to go along and look for that next element that's a minimum, and it was 2, so it gets switched with that index 1. Now we're at index 2, and we have element 14. So we're looking for the next smallest number, which in this case will be at index 4, which is 3. And then we're going to do the swap that way. Now we're at index 3 with elements 12, and we're looking for the next item to put in, which will be 4, so we do the swap that way. So notice where 12 ended up here. So now we have at index 4, 14. Next element's going to be 5 here at index 11. And you can do the swap that way. Next, index 6, where's going to be the next item? It's going to be at 7, so you'll notice 10 here. We'll end up here at this index. And you can basically keep running this and do the swaps yourself. And there you go. Now you have an entire sorted array. So this was using the swapping with the minimum. So if you want to see this almost like in slower motion, I encourage you to come and check out visualalgo.net. So I almost do that as a homework assignment so you can really get a visual. So let's go ahead and sort this. Actually, it's already sorted, so let's go ahead and create a new one. Random, go. Okay. And then we'll go sort, go and take a look at what's happening here. So we're going to check if all these numbers here are smaller than the current minimum. So our current minimum is 3. So we started on the left, we're looking for a current minimum. There it is, it's 2. So we're going to push it as the new minimum. Check the other numbers if they're smaller than the current minimum. None of them are not, so swap 2 with 3 here. So notice how that swap took place. So now our current minimum is 38, and it's going to keep getting reset against all the numbers, so we keep going along. And now we're looking for that next minimum, which will actually end up being 3, the number we just swapped. Here now 3 is the current minimum. And you can follow along here with the pseudocode and the status bar, which is actually telling you what's going on. And then the swap occurs. So if we push the speed a little faster, you'll notice the swap's taking place. So it's checking against the minimums and then pushing them to where they belong. All right, so unlike the bubble sort, it's not doing that pair of swapping. You'll notice it's doing way fewer swaps. In that bubble sort, it was doing swaps all along. And here, we're just checking for the new minimums versus the current minimums. In the previous example that I showed you in that presentation, we were actually looking for the largest. So I want you to be aware that you could implement this both ways, either by checking for the minimums or for the largest, and then pushing things either to the left or to the right and doing those swaps, depending on whether you're checking for maximums or minimums. All right, so that list is sorted. Let's go ahead and implement this so we get a better understanding of how selection sort works. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture for implementation of selection sort. So let's get a brief overview again of what selection sort is. The selection sort improves on the bubble sort by making only one exchange for every pass through the list. In order to do this, what the selection sort is going to do is look for the largest value as it makes a pass, and after completing the pass, place it in its proper location. As with a bubble sort, after the first pass, the largest item is in the correct place. After the second pass, the next largest is in the place. So this process continues and requires n-1 passes to sort n items, since that final item is actually going to be in place after you do the n-1 passes. So let's go ahead and see how we can implement this, our own selection sort function, in Python. You have resources for review in the notebook, as well as the code itself. So let's go ahead and check it out. So I've jumped to a new notebook, and I'm going to say, to start off my function, I'm going to say def selection underscore sort, and I'm going to pass in some array. In this case, it's going to be a Python list ARR. So for every slot in the array, remember we were talking about fill slots and slots in the theory lecture, I'm going to say fill slot in range, and we're going to do the exact same thing we did for the bubble sort as far as selecting that range. So remember, it looks something like this, and it basically helps you index in a reverse manner. And remember, for this selection sort now, we're keeping track of the max. So what I'm going to do is make a variable called position of max. And I'm going to set it equal to 0 so that it's at the first index essentially. And then I'm going to say for every set of 0 to that fill slot plus 1. So in this case, for, and I'll say location in range 1 to fill slots plus 1. And the reason we're starting at 1 here is because we already have the position of max at 0. So let's go ahead and set the maximum's location. So I'm going to say if at that location of the array, if it's greater than at the position of max, go ahead and basically reset that position of max to position of max is equal to location. Okay, and then for the switching, what we're actually going to do is do it in relation to this for loop. So I'm going to say temp equals at fill slots. So this is really similar to what we were doing in the bubble sort. And then set at fill slot equal to position of max at the index. And then I'm going to say array at the position of max equals temp. So this is essentially just a switch here. Okay, let's go ahead and run this and make sure it all works out. So let's go ahead and make an array. Just make a random array. We'll say 5, 8, 3, 10, and 1. So clearly it's not sorted. And what we're going to do is call selection sort on that array, and then go ahead and show the array. And notice that I have to ask for this show here because I don't have a return statement in this actual function. So let's go ahead and see it. All right, great. So it was sorted out, so we know our function's working. Let's go ahead and walk through it one more time. So what I'm saying is for every fill slot in range, length of the array -1 in a negative step fashion. So let's go ahead and make sure we understand this. So I'm going to go ahead and show that one more time. So here we have an array of 5 elements. So what this range does, as far as the indexing, is go 4, 3, 2, 1. Essentially backwards through that array, right? So then I'm saying position of max equals 0. And then for the location index in range, from 1, since we're already considering position of max equals 0, all the way to that fill slot plus 1. So for instance, the first one is going to be up to 1 to 5. I'll say if at that location, that element of the array is greater than at the position of the max, reset the position of max location. Once that's done, if we have that as true, we'll go ahead and start doing the switch. So I'll say a temporary variable is equal to at the fill slot location, then fill slot location element equals the element at the position of max, and then I reset the position of max indexed element to the temporary element. Okay, so that's all there is to it. You can go ahead and check out the notebook for explanations and resources for full explanations. There's the Wikipedia link and visualizing the algorithm explanations, as well as some pseudocode. So you can go ahead and check out also the real code that we just went over, as well as some comments there. And that's basically it. Okay, thanks everyone, and I will see you at the next lecture. Hello everyone, and welcome to the lecture on insertion sort. So as always, we'll be looking at an explanation and some visualizations of this sorting algorithm, and in the next lecture we'll actually implement it in Python. So this insertion sort always maintains a sorted sublist in the lower positions of the list. And we'll see what we mean by that in a figure in just a second. But basically what happens is each new item is inserted back into that previous sublist such that the sorted sublist is one item larger. So you have this little portion of your list, this sublist, that you assume is already sorted, and you're basically passing the other elements from your array or list into that sublist and sorting them as you put them in there. So you begin by assuming that a list with one item, so your element at position 0 or index 0 is already sorted. And then on each pass, one for each item, 1 through n-1, the current item is checked against those already in that sorted sublist. And then as we look back into the already sorted sublist, we shift those items that are greater to the right. And then when we reach a smaller item or the end of the sublist, the current item can be inserted. So let's go ahead and look at a figure of this actually happening. So we assume, as I mentioned here, that your first item is sorted out of a list of 1. So the shaded items here represent that ordered sublist in the algorithm as it makes each pass. So we're assuming 54, that element 54, is a sorted list of one item. And then what we're going to do is go to the first item in the rest of that list, number 26, and then insert it into that sublist. And then we put it before 54, and now you have a sorted sublist of 26 and 54. Then the next item, 93, is inserted into that sublist. Insert 17, we insert 77, and you're inserting them so that the list itself, that little sublist, is being sorted as you go along. So, as I mentioned before, you're beginning by assuming that a list of one item at position 0, in this case that element number 54, is already sorted. And on each pass, one for each item, 1 through n-1, the current item is being checked against those already in that sorted sublist. And then as you look back into that already sorted sublist, you're going to shift those items that are greater to the right. And then when we reach a smaller item or the end of that sublist, that current item can be inserted. So let's go ahead and look at that fifth pass in detail. So when we're inserting number 31, see how that actually works. So you need to insert 31 back into the sorted list. So here we're at number 31, and you see 93 is greater than 31, so you shift 93 one space over to the right. 77 is greater than 31, so you shift it over to the right. 54 is greater than 31, so you shift 54 over to the right. 26 is less than 31, so you insert 31 then into that position. So that's what I mean by reaching that smaller item or at the end of the sublist, and then the current item can be inserted. So as you're looking back into that already sorted sublist, you're shifting those items that are greater to the right. Okay. So let's go ahead and take a look at some other visualizations that you can check out so you can further understand the insertion sort mechanisms. Okay, so here we are at the Jupyter Notebook, and you have your resources for review. So go ahead and check out those resources for any visual or visualizations you want to check out. In this case, I'll show you really quickly what the visual algo looks like here. So I've created this random list. I'm going to go to Sort, click Go, and then check out what our pseudocode is doing. So remember, we're marking that first element as sorted, and then for each unsorted element, we're essentially extracting that element and then checking it out against where it should go, and then inserting it. It jumped a bit here, but inserting it through that mechanism where you're checking which elements are greater than. So as you're already looking back into the already sorted sublist, you shift those items that are greater to the right, and then when you reach a smaller item at the end of that sublist, you can insert that current one you're comparing. So right now, let's take one more look. So the next one we're going to do is 36. So here we have element 36. It's being compared to all these elements. They're being shifted to the right if they're greater than. 38 is going to get shifted to the right. Here you have 15, it's less than 36, so we're going to go ahead and insert 36. 26 is going to be compared to all of these elements. All the ones that are greater than 26 are going to be shifted to the right. Once we find one that is less than 26, we go ahead and stop the shifting and then insert that element. And so if we speed up this process a little bit, we'll see this happen. That is comparing it to all the elements in that little sublist, and look at that sublist, it's marked in yellow here. And then if we speed this up all the way, we'll see the entire sorting process happen. Okay, so I encourage you to go ahead and check out this visualization on your own, make sure you understand that pseudocode, and in the next lecture what we're going to do is actually implement our own insertion sort algorithm in Python. Alright, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of insertion sort lecture. So just a quick reminder, insertion sort builds that final sorted array or list one item at a time. It's much less efficient on large lists than more advanced algorithms such as quicksort, heap sort, or merge sort. So again, here are your resources for review in the accompanying Jupyter Notebook, and here's the function that we're actually going to code out and go ahead and try ourselves. So let's go ahead and jump to the live code and check it out. First thing we're going to do is start off with our function def, and then we're going to go ahead and say insertion sort. So insertion underscore sort, and take in arr, which is going to be our array object. In Python, again, that's just a list. So first thing we're going to do is just go ahead and say for every index in array. So let's say for I in range, and we'll start from 1 to the length of the array. And then what we're going to do is go ahead and set current value and position. So I'll create a variable. I'm going to call it current value, and it's going to be at basically that value at the current position. And I'm going to make another variable called position and just call it I. Now again, I could just be calling these directly throughout the algorithm, but it's nice to have these variable names so we really are super clear about what's going on. So then what we're going to do is have our sorted sublist. So you can go ahead and review the lecture in case you want to remember what that sorted sublist looks like. But basically what we're going to do here, let me scroll down a bit, is say while position is greater than 0 and the value at position -1, so that previous value essentially, is greater than the current value, what we're going to do is set the value at that current position. So position equals array at position -1. So this is basically a switch, right? And then if I say position equals position -1, I'm essentially just changing my position variable. And then I'll set the array value at that position equal to the current value I'm on. Okay, that's essentially it. That's the sorted sublist that we're creating here, and that's the insertion sort. So let's go ahead and run it, make sure it all worked out, and then we'll go again line by line, a quick review of what we've done. So we'll run that, and let's go ahead and take an array. We'll call this just ARR, put in a bunch of numbers in any particular order we want, since they're not going to be sorted yet. 23, 13, let's say 2. Okay, and then we're going to say insertion sort on that array, and then call the array back. Again, notice, just as a reminder, I don't have a return function anywhere in my, I don't have a return keyword anywhere in my array, so I have to manually call it out when I say ARR here. Let's go ahead and make sure it worked. Okay, awesome. We have our sorted array. So let's just go ahead and go line by line one more time, what's actually happening here in our function that we just created. Let me zoom out so we can get the whole picture here. Alright, so looking at this code, let's just remind ourselves that here in this implementation of insertion sort, showing here that there are again n-1 passes to sort n items. So that's why this iteration starts at position 1 and then moves all the way through position n-1. So remember, because of indexing starts at 0, and because of the way range works, this is 1, and this is actually n-1. So as there are, well, this is n, but the actual range that we'll put out is n-1. So let me just go ahead and make sure everyone's clear on that. So if I pass in range from 1 to length of r, and I'll define r as just 1, 2, 3, then you'll notice I get 1, 2. So it goes from 1 to n-1 here. Okay, so we can see that this line right here, this ARR, this array at that position, so the value of the array at that position equals array position -1, that's essentially performing that shift operation that moves a value up one position in the list, making room behind it for the insertion. So remember that this is not a complete exchange as was performed in previous algorithms we've seen. So that means that the maximum number of comparisons for an insertion sort is the sum of the first n-1 integers. So again, that means this is order n squared. However, in the best case, only one comparison needs to be done at each pass. So this would be the case for an already sorted list that you happen to call this insertion sort algorithm on. One note about shifting versus exchanging is also important. In general, a shift operation requires approximately a third of the processing work of an exchange, since only one assignment is performed. So in some benchmark studies, insertion sort will actually show very good performance. So it might be nice for you to check out the Wikipedia link in the notebook and go ahead and learn about the pros and cons of insertion sort in case that's a interview question later on. So it gives you again the algorithm here. You can check it out. Gives you talks about the sorted partial results, those sublists that we were talking about. And it'll also give you information on the best, worst, and average cases with a nice discussion here that you can prepare for your interviews with. Okay, so those are the basics, and that's just the implementation of insertion sort. You can go ahead and check out the previous lecture if you want, again, a background on that theory, but that's really all there is to the implementation. All right, thanks everyone, and I will see you at the next lecture. Hello everyone, and welcome to the shell sort lecture. So in this lecture, we'll have an explanation and visualization of shell sort, and in the next lecture we'll have an implementation in Python of shell sort. So let's discuss what the shell sort algorithm actually does. It's pretty similar to the insertion sort algorithm, but it improves on it by breaking up that original list into a number of smaller sublists instead of just that one singular sublist. And the unique way that these sublists are chosen is the real key to shell sort. So instead of breaking the list into sublists of contiguous items, the shell sort uses an increment that we'll call I. It's sometimes called the gap, and it uses that increment I to create a sublist by choosing all items that are I items apart. So let me go ahead and show you a figure of what I mean by that. So if we look at this figure, this list has 9 items. If we use an increment of 3, then there are 3 sublists, and each of which can be sorted by an insertion sort. And after completing these sorts, we get the list shown here, which I'll show you in the next figure, right here. So, although this list isn't completely sorted, something really interesting happens. By sorting these sublists, we've moved the items closer to where they actually belong. So let me go ahead and show you what a final insertion sort using increment of 1 looks like. So here in this figure right now we have the sublist 1, 2, and 3 sorted. So notice how there's these 9 items. We have I equals 3, so little sublists, 3 of them, 3 items each. And if we sort the sublists at an increment of 3 and go to the final insertion sort here, and this one is just going to be using an increment of 1, so in other words, just a standard insertion sort. And then you can note that by performing those earlier sublist sorts, we've actually reduced the total number of shifting operations necessary to put the list in its final order. So for this case, we actually only need 4 more shifts to complete the process. 1 shift for 20, 2 shifts for that 31 element, and 1 more shift for 54. And then your entire list has finally been sorted. Now I'm going to show you one more figure here, and we'll actually get to what this figure is actually doing later on in the implementation. But I mentioned earlier that the way in which the increments are chosen is one of the unique features of shell sort. So we'll show this later in our implementation, but what you can actually do is start a first case with n over 2 sublists, with n being the number of items in your list or array, and then on the next pass perform n over 4, and etc., and then eventually a single list is sorted with that basic insertion sort. So right now this shows what the first sublist of the example implementation we're going to do in the next lecture looks like. So don't worry about this too much now. We'll actually cover this later on when we actually implement our shell sort. So now let's go ahead and take a quick look at some visualizations that you can check out. So we're here at the Jupyter Notebook for the implementation of shell sort, and you'll see some resources for review. Go ahead and click the last one, the sorting algorithms, sorting-algorithms.com, and you'll see some shell sort visualizations for you to check out. And then keep in mind, remember here, that the gray values are unsorted, black values have been sorted. Okay, and then here's the pseudocode for the algorithm, and then it shows you the properties as well. So if we just check how this shell sort looks on a random, you'll see that you have multiple sublists occurring here due to the implementation, and eventually at the end they do one final pass as an insertion sort. Alright, so when we talk about implementing this, we will talk about the properties a little more and why shell sort is a little better than just a normal first pass of an insertion sort. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of a shell sort lecture. So, just as a review, the shell sort improves on the insertion sort by breaking that original list into a number of smaller sublists. And then each of those sublists is using an insertion sort. So the unique way that these sublists are chosen is the key to the shell sort. Instead of breaking up that list into sublists of continuous items, what the shell sort is going to do is use an increment I which is sometimes called the gap, to create a sublist by choosing all items that are I items apart. Okay, so we've seen those figures that show that idea in the previous lecture. You can go ahead and review them, or you can go ahead and check out the resources for review here in the Jupyter Notebook. But what we're going to do is go ahead and implement our shell sort. And we're actually going to use two functions here. We're going to have our main shell sort function, and then we're going to create another function to do the gap insertion. So that will be this function here. So let's go ahead and get started with our basic shell sort. So I jumped over to a new tab here in the Jupyter Notebook, and I'm going to say, let's say shell underscore sort, and pass in some array. Okay. First thing I'm going to do is go ahead and say sublist count is equal to length of array divided by 2. And then what we're going to do is then say, while we still have sublists, so while sublist count is greater than 0, for, and I'll say for start in range all the way up to the sublist count, this is where I'm going to do that gap insertion. So I'm going to say gap underscore insertion underscore sort, and that's going to take 3 arguments. And this is the new function we're going to develop in just a bit. It's going to take in that array, it's going to take in a start, and then it's going to take in that sublist count. And then once we've done that, after we do that for loop, what we're going to just go ahead and do is say sublist count is equal to sublist count divided by 2. Okay, so now let's go ahead and focus on this gap insertion sort. So we're going to say def gap underscore insertion underscore sort, and again it's going to take in an array that starts, but instead of saying sublist count, what we're going to just go ahead and treat this as is that gap that we discussed earlier. So I'm going to say for I in range, and in this case we're going to have our starting be our start point plus that gap all the way to the length of the array, and we're going to go in steps of the gap. Okay, and then let's go ahead and make a variable called current value and set it equal to whatever that value is at this index of the array. And then let's go ahead and say position equals I. So we're basically doing the same thing as we've done in a few other algorithms, set a current value and a current position. And then using that gap, what we're going to do is say while position is greater than or equal to gap, and the array value at the position minus the gap is greater than that current value. Here's where we're going to do essentially that exchanging. We're going to say position, or that shifting, position minus gap, and then say position then equals position minus gap. So we're switching both those values and those index positions themselves. So we're using the gap there, and then at the end what we have to do is after this while loop, just go ahead and set that current value. So just say the array at that position is just equal to the current value. Alright, so we've made our 2 functions. Before we go ahead and break them down more, let's just make sure that they work out. So I'm going to go ahead and copy from the other notebook this test array and this test call, run them, and it looks like in fact we're good. It actually did sort. So let's go ahead and zoom out and then see if we can break down what's going on here. So first thing we want to notice is how we're actually choosing the increments or those gaps, those sublists here. So in this particular method or implementation, what we're doing here is we're beginning with n over 2 sublists. So if this array has n elements, then our first sublist is going to be n divided by 2. And then on the next pass, what we end up having is n divided by 4, right? Because we're dividing that thing again by 2. So 1/2 times 1/2 is 1 over 4. And then we're taking that length of the array, which is going to be n items of the array, and then dividing it by 4. So on the first pass, you start with n over 2 sublists, next pass, n over 4, and then eventually a single list is sorted with just that basic insertion sort. So what you can do, if you want to visualize this a little more, is actually create a print statement. So you can go ahead and put a print statement after this for loop, and you can go ahead and say print, in this case, let's say after increments of size, and then let's go ahead and just say sublist count here, and then we'll print another a line here. The list is, and then what we're going to do is just put that array value there. So let's make sure that worked out. Okay, so here we have our increments, so let's just go ahead and check the length of that array so we can get an idea of what's going on here. So we have 11, so closest 11 divided by 2 rounds off to 5. So after the increments of size 5, we essentially have this list. Increments of size 2, we have this list. Increments of size 1, we end up getting this list. So you can go ahead and review the previous lecture on the actual shell sort, and how we had those sublists and the insertions, and then those final insertion sorts when we had the increments of 1. Go ahead and check them out. Those figures are really helpful. But essentially remember that with the shell sort, we're just improving on that insertion sort by breaking the original list into a number of smaller sublists, each of which are then sorted using an insertion sort. And the key to this is that unique way that these sublists are chosen in the shell sort. So instead of breaking that list into a bunch of sublists of continuous items, the shell sort uses that increment I, sometimes called that gap, and that creates a sublist by choosing all the items that are I items apart. Okay, so go ahead, write this out yourself, make sure you understand it. I really suggest using print functions to help you keep track of what's going on throughout the functions and your function calls. That's super helpful. So if you're ever not understanding 1 or 2 lines of code, try putting a print statement there and seeing what's actually happening. Go ahead and print out different variables so you can get an idea of what's actually being sorted, where are your sublists, where are your gaps, etc. Okay, with that being said, that's the implementation of the shell sort, and I will see you at the next lecture. Thanks. Hello everyone, and welcome to the lecture on merge sort. So in this lecture, again, we'll have an explanation and some visualizations of merge sort, and in the following lecture, we'll have an implementation of merge sort in Python. So we're going to begin to turn our attention to using divide and conquer strategies as a way to improve the performance of our sorting algorithms. And the first algorithm in this section of divide and conquer is going to be known as the merge sort. So the merge sort is a recursive algorithm that continually splits a list in half. If the list is empty or has one item, it is sorted by definition, so that's the base case. And if the list has more than one item, we split the list and recursively invoke a merge sort on both halves. So once the two halves are sorted, the fundamental operation that's called a merge is performed. And merging is just a process of taking two smaller sorted lists and then combining them together into a single sorted new list. So recursive calls are a little hard to illustrate, but let's go ahead and look at some figures to try to show that as far as a simple example. So here we can see this figure. Your list is being recursively split in half by the merge sort. So we keep splitting the lists in half. And then through a recursive call, when you put them back together, what you're doing is sorting them on the way back. So it's a little hard to show this recursive call here, but this first slide, you're showing the lists being split in half. So it's being continually split in half. And here, you're seeing that recursive merging taking place. So if the list has more than one item, you're going to go ahead and split that list. And then once the two halves are sorted, that fundamental operation called a merge is then performed. So let's go ahead and take a look at some visualizations to get a better understanding of this. Okay, so at the implementation of merge sort lecture, you can go ahead and click the visual algo resource for review. That will take you here. And maybe I'll zoom in, hopefully, well, actually I'll zoom out because the recursive call, what it's going to do is actually highlight what's going to happen. So you go ahead and click merge sort, and let's go ahead and slow it down a bit and go ahead and compute this sort. Okay, so again, you're going to split each element. And in this case, you can see the coloring is basically defining this splitting that's occurring. So in this case, it's actually splitting elements recursively into partitions of size 1. So I'm going to encourage you to check this out on your own, and we can move it a little faster here to see how these kind of splits are occurring as it's merging them in half. So that was your first half there, and now it's doing it against the second half, and then it's merging everything together. All right, so let's go ahead and see it in full one more time. So there are the little recursion calls. So it's kind of starting at the end in a sense, just because the visualization works that way. There you did your first half and your second halves, then they keep getting split in half, and then finally you have that merge. Okay, so go ahead and check that out. And again, there's also a link to the Wikipedia page for merge sort, which has a great explanation as well. So I encourage you to be checking out, the Wikipedia pages for the merge sorts. It's also going to show you here how it's dividing the list into the smallest units, which is just one element, and then it's comparing each element with the adjacent list, and then it's merging the two adjacent lists. All right, so go ahead and check those resources out. In the next lecture, we'll actually be implementing this sorting algorithm in Python. Okay, thank you everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of merge sort lecture. So, again, as a brief overview, merge sort is a recursive algorithm that continually splits a list in half, list or array. If that list is empty or has one item, by definition it's already sorted. That's your base case. If the list has more than one item, we're going to split that list recursively and invoke a merge sort on both halves. Once the two halves are sorted, the fundamental operation called a merge is performed. That merging is the process of taking two smaller sorted lists and then combining them together into a single sorted new list. So here I am at the implementation of merge sort notebook, which is under sorting and searching folder. Here's your resources for review, and then here's the actual function we're going to implement and explain as we go along. So let's go ahead and implement it, make sure it works, and then break it down line by line. So I'm going to go ahead and hop over to a Jupyter notebook here, and I'm going to go ahead and start typing out. So first thing we're going to do is just say def merge underscore sort. And we're going to go ahead and pass in an array or a list, same thing as we've discussed before. And I'm going to say if length of this Python list, which we're treating as an array, is greater than 1, then I'm going to have some code out here. So I'm going to say mid as a variable. So if we already have a length that's more than 1, we know we're dealing with a list. So I'm going to say that middle of that list, that mid mid, is going to be the length of that array divided by 2. And then I'm going to create two halves, the left half of that array and the right half. So I'm going to say left half is equal to array, and I'm going to use some slicing here. I'm going to say left half is everything to the middle, and then the right half is from the middle onwards. All right, so we're using that mid, that variable, as a midpoint so we can split that array. And here, we're actually going to do a recursive call. I'm going to say merge sort on the left half, and then I'm going to call a merge sort on the right half. And I'm just using tab to autocomplete those variables, which is why they're popping up so quickly. All right, so then we're going to go ahead and make basically some index variables as counters. So I'm going to say I equals 0, j equals 0, and k equals 0. All right, and then we're essentially going to have 3 while loops here. one to check basically that midpoint, and then another one for the left and right half. So let's go ahead and program these out. So I'll say while I is less than the length of the left half, and j is less than the length of the right half, what we're going to do is say if the left half at that index is less than the right half of that index of j, then we're going to say the array at the k index, that value, is equal to left half of I. And then we're just going to say I equals I plus 1. And then let's go ahead and zoom in on this loop here. Then I'm going to say else the array value at that index k is equal to the right half of j. And then we're going to add a value to j. We're just going to say j equals j plus 1. And then outside of that, we're just going to say k plus 1. And just as a reminder, this is the same thing as saying k equals k plus 1. Okay, so that's our first while loop. And something to note here is that these additional while loops are really just operating for merging two smaller sorted lists into a larger sorted list. So notice that the merge operation places the items back into the original list, which in this case is ARR for us. So it places the items back into that original list, ARR, that array, one at a time by repeatedly taking the smallest item from the sorted list. Okay, so let's go ahead and continue on with the rest of the code we need for actually merging these two sorted lists. So as far as the actual sorting, that's happening here at the recursive call. But we have two more while lists for continuing this merging of these two sorted sublists. And they just have to do with the left and right half. So we're just going to say while I is less than the length of the left half, then our value at k is just equal to left half value at I. I'm going to say add counts to those index markers. And then we're going to do the same similar thing for the right half. So then while j is less than the length of the right half, that value at k is equal to right half at j. And then similarly, we're just going to say j plus 1, j plus equals 1, and then k equals k plus 1 there. Okay, so I know that's actually quite a bit of code that we just did. So before we break it down line by line, we're just going to go ahead and make sure it actually worked out for us. So let's go ahead and make an array of some random numbers that are unsorted. Okay, and then let's call merge sort on that array, and then check the array. Okay, great. Looks like it worked, and looks like it was all sorted. So now let's go back again and check this out line by line, really make sure we understand what's going on here for the merge sort, and we remember that it's basically a recursive call on this sorting algorithm. So first off, we basically having the base case, right? And we're checking here and doing the recursive calls. So we're saying if the length of the array is still greater than 1, which means we haven't reached that base case of just one element in that list, we calculate the mid and then split that list into left and right halves. And then we call merge sort on left half and right half. So you can imagine as you keep calling this recursive algorithm, if you remember back to the figures of the previous lecture, you keep splitting that list in half. All right. And then once those two halves are sorted, we basically have that fundamental operation called a merge. And the merging is just the process of taking those two smaller sorted lists and combining them together into a single sorted new list. So we basically have three different index trackers, where the k index tracker is going to relate to our final array. and then the I tracker is for the left half, and the J tracker is for that right half. So each three of these while calls here is just to make sure that the index is actually still within the left and right half of the list, which is why they're just less than calls. So we have our I index for that left half, and here we're just checking, okay, are we still in that left half? And then J is just checking, are we still in that right half? So then we're just checking at that particular index of I and J as we continue on, because remember, we're adding them essentially equally for any if or else cases. We're saying which one's less than or greater than. So if it's less than, then we just set the value at that current K equal to the left half, and then we add to the I value there. Once we've done that, we go ahead and add to the K value. If this wasn't the case, then we actually set the value equal to the right half, and then add 1 to the right half index marker. Then we have while I is less than the length of the left half, we continue on with a similar process, add I plus 1, K plus 1, and then the similar thing for right half. If it's still inside right half, go ahead and set that current value, the right half of J, J plus equals 1, K plus equals 1. You're just constantly adding counts and making sure you're still within that left half and right half markers. So these three while loops are just doing the actual merging of the sorted sublists. So let's just break down this code one more time as a complete whole picture. I'm kind of zoomed out a bit. But basically what we have here is our merge sort function. It begins by asking that base case question. If the length of the list is less than or equal to 1, then we've actually already have a sorted list and no more processing is necessary. If on the other hand the length is greater than 1, then we use the Python slice operation, which is what we're doing here, to extract the left and the right halves, which is this variable and this variable. And it's important to note that the list may not have an even number of items. That actually doesn't matter, as the lengths will differ by at most 1 if it's an odd number of elements. So then once that merge sort function is invoked on the left half and the right half, these two lines here, it's assumed that they are sorted. And what's actually happening for the rest of the function, the rest of these lines, they're responsible for merging the two smaller sorted lists into a larger sorted list. So notice that that merge operation places the items back into the original list. So we're actually placing them back into ARR, that original array that we took in here at the top. So it's placing them back one at a time by just repeatedly taking the smallest item from the sorted list. So you notice here we're always checking for the smallest item when we're doing these merging operations. So one more useful tip as far as really understanding what's going on is definitely adding print statements. So you could even just say here in line with that if we go ahead and go back, we can actually just say print, and we can say merging, and then let's go ahead and say just that array. Let's make sure that rhymes or works. And here we can see the actual arrays we're merging. So this is a really nice visualization, and hopefully you can see how it matches up with that original diagram that we saw in the last lecture. So we're merging 11 and 2. So these guys have already been merge sorted all the way until they only have one element left in their index. So let's zoom in a little more so you can really see this. So we're merging 11 and 2, we're checking which one is less, and now we have a sorted. Now we're going to the right half, taking 5 and 4, merging them and sorting them. And then we're going to go ahead and merge these two guys, so now we have them sorted. And you can see how we have the recursive calls on these arrays, or these sublists. And you can see how we're combining them and merging them. So go ahead and walk through this. What I would recommend is that you actually replace this array with the same array we used in the previous diagram, so you can actually match up your code to the diagrams and figures we saw in the last lecture. Okay, so that's it for the merge sort. Probably the most tricky or confusing part is making sure the merging itself is actually checking correctly on these three while loops. But the actual idea of it and the recursive call should be pretty simple and straightforward, especially if you've already done the recursion section. This sort of method of sorting just kind of makes sense that you would keep splitting that list in half, more and more and more, and then just slowly sort them and merge them as you go back up. Okay, that's it for the merge sort. You can go ahead and check out the Jupyter Notebook in case you want more resources for review, more explanations, and check out the previous lecture if you want those actual diagrams. All right, thanks everyone, and I will see you at the next lecture. Hello everyone, and welcome to the lecture on quicksort. So in this lecture, we'll get an explanation of quicksort, look at some visualizations of quicksort, and in the next lecture, what we're going to do is a full implementation in Python of the quicksort algorithm. So, to formally describe the quicksort, what the quicksort uses is divide and conquer to gain the same advantages as the merge sort while not using additional storage. As a trade-off, however, it is possible that the list may not be divided in half. So when this happens, we're going to see that performance is actually diminished. So, a quicksort, what it's going to do is it first selects a value, which is called the pivot value. The role of the pivot value is to assist with splitting the list. The actual position where the pivot value belongs in the final sorted list, commonly called that split point, is going to be used to divide the list for subsequent calls to the quicksort. So let's go ahead and try to look at a diagram to explain this. So here we have this array, which has 54, 26, 93, 17, etc. And 54 right here, this first element, is going to be our first pivot value. So the partition process is what's going to happen next. It will find the split point and at the same time move other items to the appropriate side of the list, either less than or greater than that pivot value. So 54 is our first pivot value. So what we're going to do is we have all the steps marked down throughout this large diagram here. So we're going to look at each of these and go through it step by step. So let's go ahead and jump to the top first. Okay, so here are the top 3 steps out of that array and sorting it using quicksort. So we have 54, our pivot value, and then what we're going to have is a left mark and a right mark. And these are actually going to converge on the split point as they go closer in to the middle. So we have that pivot value, and we have the left mark at 26. So since 26 is less than 54, that left mark moves to the right. Then, since 93 is greater than 54, we stop. Then the right mark is going to say 20 is less than 54. Stop. And this is what's going to happen here. So we have that pivot value. We noticed that we were able to stop on all the way to the right since we had a number that was less than that pivot value. And all the way to the left, we have a number that's greater than that pivot value. So the next step is to actually exchange these two values here. So now the left mark's at 20 and the right mark has 93. Then we continue moving the left mark and the right mark. So notice the left mark kept moving. 17 was less than 54, so it moved one more. 77 is greater than 54, so the left mark stopped. And then this guy went to 55 on the right mark. 55 is greater, so then it moved to 44, which is less than 54. So now they're both stopped. The left mark has a number that's greater than the pivot value. The right mark has a number that's less than it. So we're going to do another. And so now what you'll notice is the right mark having moved over to 31 and the left mark having moved over to 77, the right mark is now less than the left mark. So we found our what we call that split point. So what we do now is exchange 54, that pivot value, and 31, that right mark. So note that we're going until the right mark and the left mark cross. So to continue this, let's go ahead and take a look at some visualizations to try to get a better understanding of this quicksort algorithm. Okay everyone, so now we're here at the implementation of quicksort notebook under the sorting and searching folder. And if you scroll down a bit for resources for review, you'll have the Wikipedia page, the visual algo, and then another animation page. So if we go ahead and click on the Wikipedia link, it'll take us here to the Wikipedia for quicksort. And you'll note that there's a bit of an animation here, as well as a lot more information about quicksort. Another diagram here, similar to the one that we were going over. And you can see there it has a left mark and a right mark. Although some people just think of it as one single mark going along. And you can check out the different partition schemes here and implementation issues. So I encourage you, if you're interested in quicksort and more about that algorithm, you can check out a lot more information on the Wikipedia page. As far as visualizing, you can either go to sortingalgorithms.com, sorting-algorithms.com, and check out the quicksort. And you can go ahead and see various visualizations, look at these two marks as they're going. It's similar to what we were doing before. We have that left mark and right mark meeting and then doing those splits along those partition points. Okay, so again, last resource to check out is this visualalgo.net sorting. Go ahead and click quick here, and then you can go ahead and visualize the sorting mechanism. Here they're showing left and right marks a bit by color. So if you notice here, we're checking against 7 as our pivot point. So we're going along, and in this case, there won't be anything that's less than 7. The lowest number here is 7. It was matched, but not less than. So we go out through this entire list, and we actually take 7 as the smallest number, so that iteration is complete. So the pivot's now actually at a sorted position. So our new pivot number is going to be 43. We noted that we had a 23 that was less than 43, and so now we're doing those splits. That's almost the same as when the left and right mark were meeting each other. Okay, so I encourage you to go ahead and check out this on Visual Algo. I'll go ahead and pause this now. And you can see that there's always some pseudo code here, as well as an explanation of what's happening. So this website's super useful. Just make sure you're in exploration mode to be able to explore, and you can create and sort various things as far as the arrays that you're going to be sorting through. Okay, thanks everyone, and I'll see you at the next lecture where we're going to be implementing our own quicksort algorithm in Python. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of quicksort lecture. So, as a reminder, the quicksort algorithm first selects a value, which is called the pivot value. Although there are many different ways to choose the pivot value, what we do is simply use the first item in the list. The role of the pivot value is to assist with the splitting of that list. The actual position where the pivot value belongs in the final sorted list, commonly called that split point, is then used to divide the list for subsequent calls of the quicksort. So again, you have resources for review, and you can check out the previous lecture if you want more coverage on the theory of quicksort. But we're going to go ahead and implement our own quicksort algorithm. So this is probably going to be one of the most involved out of all the coding of the algorithm, so just keep that in mind. We're going to have 3 separate functions in order to make this happen. So let's go ahead and just dive right into the code before we break it down line by line and explain what's actually going on. Alright, so first thing we're going to do is just go ahead and start our function. So we're going to say def and say quick underscore sort. And then let's go ahead and pass in an array. And what I'm going to say right now is just pass, and I'm going to make the skeleton of all the functions we're going to use. Next one we're going to use is called quicksort helper. So this original quicksort function is going to just do, it's going to invoke a recursive function called quicksort helper, which let's go ahead and do it. We'll just say quick underscore sorts help, and that will take in an array and then a first and last marker. And we'll say pass right now. And then finally, the last one we're going to say is partition. This will also take the array, first and last, whoops, and then we'll say pass. All right, so we have the quicksort function, and then it's going to invoke a recursive function, quicksort help, which begins with the same base case as that merge sort. So if the length of the list is less than or equal to 1, it's already sorted. If it's greater than, we can be partitioning and recursively sorting that array. So that's what the partition function is going to do, and it's going to implement that process we described in the previous lecture. So let's go ahead and get started. So we have quicksort, and all it's going to do is, like I mentioned, just going to call quick sorts help, and it's going to take in that array. We'll start off at 0 and then go to length of the array minus 1. And the reason for that being is the way we set up our n values when we do partition. So quicksort help, we're just going to say if first is less than last, we're going to set up a variable called split point. And then that's going to be returned from the partition call. And again, partition is just going to take in the array, first and last. And then similar to the merge sort, here we're going to call quick sort help twice. On the array, first, and then all the way to the split point, -1. And then we're going to call it again quick underscore sort underscore help on the array. And then from the split point, +1 all the way to the last element. So this should look really familiar from the merge sort implementation, where we had that recursive call, one on that first left half, then the other one on that right half. So now let's take advantage of this and fill out our partition function to really start doing the merging and that quick sorting. So let's go ahead and create our pivot value. We'll say pivot value as a variable and just have it be that first element. As I mentioned, there's different ways of choosing the pivot value. For this simple implementation, we're just going to use that first element. So then let's go ahead and make those marks. So hopefully you remember from those figures, we had that left mark and that right mark. And just like we did in the last lecture, theoretically, at least, I'll set left mark equal to that first +1, and then right mark just equal to last. And then what I'm going to do is set up a while loop. And in order to make this a little more readable, I'll set a variable called done and have it be equal to false. That way my while loop can read something like this, while not done. So that will allow us to have a really nice readable while loop. And then I'll say while that left mark is less than or equal to the right mark, and the array value at the left mark is less than or equal to the pivot value, then I'll just say left mark is equal to left mark +1, which I can just write like this. And then I'll say another while loop, while the value at the right mark in our original array is greater than or equal to the pivot value, and the right mark is greater than or equal to the left mark, then the right mark is going to be subtracted, have 1 subtracted from the right mark. So remember from that last lecture how we move them closer to each other. So left mark starts moving to the right, and then that right mark starts moving to the left, as long as these two conditions end up being true. And then finally, if we say if right mark is less than the left mark, so remember that was that crossing point, then they're done. So we'll say done equals true. Otherwise, they're not done yet, so I'll say else, and this is where we basically do that switching. We'll say create a temporary variable of the left mark value, and then set left mark equal to the right mark, and then set the right mark equal to the temp. So that's basically just the way we're switching those values once they cross over. All right, and then what we're going to do is outside of these while loops, or essentially outside of this while not done, we have to do one last switch here. We'll say temp is equal to the value at first, and then that value at first is then going to be equal to the right mark, or the value at the right mark. And then the right mark value is just equal to, temp here. And then we can just return the right mark, since we'll be calling partition here, which is basically just returning that split point. So partition is just going to be returning that split point after doing these operations. All right, I know that was a lot of code, so let's go ahead and check it out, make sure it all worked, and then we'll break it down further. So I'm going to say an array. Let's go ahead and just copy and paste this from that Jupyter notebook we already have. Make sure this all worked out. Okay, looks like it's sorted and looks like we're good to go. So let's go ahead and break down what's going on here in our implementation of quicksort. So remember, the first thing we had to do in quicksort was select the value, which is called that pivot value, which is what we have here while we're making the partition. We're selecting that pivot value, and in this case, we're selecting the first item in this list. And the role of the pivot value is to assist with splitting the list. So the actual position where that pivot value belongs in the sorted list, commonly called that split point, which is what we end up returning from a partition function, that's going to be used to divide the list for subsequent calls of quicksort, which is what we're doing here. Okay, so we have our first pivot value, which is going to be that first element. So then this partition process is what's going to happen next. We have our left markers and our right markers, and what this partition process is going to do, it's going to find that split point and at the same time move other items to be on the appropriate side of the list, either less than or greater than that pivot value, which is what we're doing with these checks here and here. So as I mentioned, that partitioning begins by locating those two position markers, that left mark and the right mark, at the beginning and end of the remaining items in the list. And the goal of this partition process is to move items that are on the wrong side with respect to that pivot value, while also converging to that split point, which is why we slowly start to move the left mark to the right and that right mark to the left. And then specifically, we begin this process by just incrementing left mark here, the incrementation, until we locate a value that is greater than the pivot value, which is what we're doing here. Okay, so then we decrease the right mark until we find a value that is less than the pivot value, which is what we're doing here. So basically, once it breaks, what we're doing here, once it breaks and is greater than the pivot value. So at this point, then we've discovered two items that are out of place with respect to that eventual split point. And then we just exchange those two items, which is what we're doing here, and repeat the process again. So at the point where the right mark becomes less than the left mark, that's when we stop, which is our done statement here. And then we know that the position of the right mark is now the split point, and that pivot value can be exchanged with the contents of that split point, and the pivot value is now in place. And in addition to all this, all the items to the left of the split point are now less than the pivot value, and all the items to the right of the split point are greater than the pivot value. So the list can now be divided at the split point, and the quicksort can be invoked recursively on the two halves. In this case, we used quicksort help on those two halves here. Okay, so that's the basics of matching up what we theoretically talked about in the previous lecture to an actual implementation of the algorithm. I would really suggest that you use print statements wherever you feel uncomfortable or confused about our implementation here to print out what's actually going on. And when you're doing that, go ahead and switch this array to the same numbers that we used in the previous lecture, so you can actually see your array be printed out in the same way that we have the figure in the previous lecture on those slides. And that's going to be a really useful way for you to build out your understanding of the algorithm, print out, follow along, and really understand how the partition and quicksort process is actually working. And if you still need more help, again, if you go to the Jupyter Notebook, there's resources for review, such as the Wikipedia page, visual algorithm, etc. All right, so that's the implementation of quicksort. Thank you, everyone, and I will see you at the next lecture. Hello, everyone, and welcome to the sorting and searching interview problems. So we've gone over the theory, now let's talk about the interview problems themselves. So in this section, most common interview questions related to sorting are just implementation questions. In this section, you're actually just going to be asked to implement each of the sorting algorithms we've already gone over. Then check the relevant implementation lecture for the solution. So this section is going to be a little bit different than the other interview problem sections we've done, where there's no direct solution video after the interview problem. Just go ahead and check the relevant implementation lecture for that algorithm. We'll go over this again individually for each of the interview problems. The reminder, that is. A special note on the binary search algorithm: this section's interview problems are just going to ask you to implement it. But keep in mind that future mock interview questions towards the end of the course we'll ask you questions where using a binary search is critical to finding the answer. So really know binary search well. With that being said, best of luck on all the questions. Remember, we're just going to be implementing the sorting algorithms for the interview problems for this section of the course. Okay, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. This interview problem is to implement a binary search. So go ahead, open up a Jupyter notebook, and begin implementing a binary search. You can check the implementation of a binary search lecture for the solution and explanation for implementation. Okay, that's it. Best of luck. Hello everyone, and welcome to your next interview problem. For this interview problem, I want you to implement a bubble sort. So go ahead, open up a Jupyter notebook, and you can begin to implement a bubble sort. Go ahead and check the implementation of a bubble sort lecture for the solution and explanation of the sorting algorithm. Alright, thanks everyone, and best of luck. Hello everyone, and welcome to your next interview problem. For this interview problem, go ahead and implement a selection sort. So, open up a Jupyter notebook and begin to implement it. Check the implementation of a selection sort lecture for the solution and explanation of the algorithm. Alright, that's it. Best of luck. Hello everyone, and welcome to your next interview problem. So, for this interview problem, I want you to implement an insertion sort. You can go ahead and check the implementation of an insertion sort lecture for the solution and explanation of the algorithm. Alright, that's it, and best of luck. Hello everyone, and welcome to your interview problem. For this interview problem, I want you to implement a shell sort. Go ahead and check the implementation of a shell sort lecture in case you need the solution and an explanation of the algorithm. Alright, that's it. Best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview problem. For this interview problem, I want you to implement a merge sort. You can go ahead and check the implementation of a merge sort lecture for the solution and explanation of the algorithm. Alright, that's it. Best of luck, and I'll see you at the next lecture. Thank you. Hello everyone, and welcome to the last interview problem for the sorting and searching section of this course. So, for this problem, I want you to implement a quick sort. You can go ahead and check the implementation of a quick sort lecture for the solution and explanation of the algorithm. Okay, that's it for the searching and sorting section of the course. Up next, we're going to practice riddles, how to approach riddles and brain teasers, and then a series of interview problems based off of riddles and brain teaser type questions. Okay, thank you very much, and I'll see you at the next section of the course. Hello everyone, and welcome to the Introduction to Graphs lecture. In the Graphs section of the course, we're going to learn what a graph is and how to use it. We'll also learn how to implement the graph abstract data type using multiple internal representations, and you're also going to see how graphs can be used to solve a wide variety of problems. So what are graphs? Graphs are actually a more general structure than trees, and we can think of a tree as a special kind of graph. Graphs can be used to represent many real-world things, such as systems of roads, airline flights that connect from city to city, how the internet is connected from website to website, etc. Once we have a good representation for a problem, we can use some standard graph algorithms to solve what otherwise might seem to be a very difficult problem. So, computers can operate well with information presented as a graph. And an example graph may be the course requirements for a computer science major. So a really simple graph would look maybe something like this, where each vertex on this graph is a class, and then you have some edges pointing from vertex to vertex. And we'll go over the vocabulary in just a second. So, we just looked at an example of a graph, and now what we want to do is formally define a graph and its components. And we'll actually already know some of these terms from our discussion of trees earlier. First off is a vertex, which is also called a node. And it's the most fundamental part of a graph. It can have a name, which we will call the key, and a vertex may also have additional information, and we'll call this additional information the payload. Then you have an edge. An edge connects two vertices to show that there's a relationship between them. And edges may be just one way or two way. If the edges in a graph are all one way, we say that the graph is a directed graph. So for example, that class prerequisites graph that you just saw is actually a directed graph since you must take some classes before others. So if we go back to it and check it out, here we have some classes, and if you notice all the edges just go from one node or one vertex to another. There's actually no two-way ones here, meaning this is a directed graph, which makes sense because you have to take a class before going on to the next one. You don't go back and forth between classes. So we talked about nodes or vertices, what a vertex is, talked about edges. Now let's talk about weight. Edges may be weighted to show that there's a cost to go from one vertex to another. So for example, in a graph of roads that connect one city to another, the weight on the edge might represent the distance between two cities. Okay, now let's discuss a formal definition of a graph and how we can actually write it out. We could represent a graph by, for example, G, where G is equal to VE. And for the graph G, V is a set of vertices and E is a set of edges. And we'll see this written out in just a second. Each edge is a tuple, lowercase vw, where that lowercase vw pair is an element of that larger set of vertices. And then you can actually add a third component to the edge tuple to represent a weight. And then a subgraph S is a set of edges, lowercase e and vertices lowercase v, such that lowercase e is a sub part of the set of edges, and lowercase v is a subset of uppercase v, set of vertices. So basically what this is just saying in notation form is that lowercase e and lowercase v are subsets of the larger set of vertices and larger set of edges, which makes sense because it's a subgraph. So let's go ahead and actually look at a more formal graph and then see how we can write this out. So here we have an image of a graph. We have the vertices v0, v1, v2, v3, v4, v5. Notice how we have the edges pointing from one vertex to another, and then we have the weights to them. So if we actually look and draw this out or write this out formally, we'll see here we have a set which stands for all the vertices in the graph, which goes from v0, v1, v2, etc., all the way to v5. So you can use this set notation for each vertex. And then the edges is a set of tuples. And you can see each edge is one vertex, then another vertex, and then the weight. So we look at this edge, it goes from v0 to v1 with a weight of 5. And you can see how this set notation actually starts to make sense and how a computer would be able to process this. Now let's talk about a path. Path is actually just a simple concept. In a graph, it's just a sequence of vertices that are connected by edges. And this is how you would formally define a path, but let's go ahead and see it in comparison to that picture we just saw. Here, the path from v3 to v1 is a sequence of vertices v3, v4, v0, and v1. And then it has a set of edges right here, these three tuples. So if we actually go from v3 to v1, we'll see, since the edges are basically a directed graph, right, they're only going one way, we have to go from v3 to v4 to v0 to v1. And that means we have three edges. This one that's weighted 7, this one that's weighted 1, and this one that's weighted 5. Finally, we can talk about a cycle. A cycle in a directed graph is a path that starts and ends at the same vertex. So a graph with no cycles is called an acyclic graph. A directed graph with no cycles is called a directed acyclic graph, or DAG. And later on, we'll see that we can solve several important problems if the problem can be represented as a DAG, or DAG. So, quick example of what a cycle would look like. In this case, v5 to v2 to v3 to v5, this little triangle, is a cycle, since we started and ended at the same vertex. Alright, so what did we do in this lecture? We saw what a definition of a graph is, both just informally and formally. We learned about some important graph vocabulary terms. And up next, we're going to learn how to represent and implement a graph. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture discussing what an adjacency matrix is and what an adjacency list is. So we're going to learn how to represent graphs in this lecture. And as I mentioned, we're going to learn how to represent them as an adjacency matrix and an adjacency list. And in the next lecture, we'll actually implement an adjacency list in Python. So let's discuss what a adjacency matrix is first. It's one of the easiest ways to implement a graph, and we just use a two-dimensional matrix. In the matrix implementation, each of the rows and columns represent a single vertex in the graph. The value that is stored in the cell at that intersection of row V and column W indicates if there's an edge from vertex V to vertex W. And then when the two vertices are connected by an edge, we say that they are adjacent. So for example, here you can see a matrix, or an adjacency matrix, and the value in each of these particular cells represents the weight of an edge from that vertex V to vertex W, so that rows to that columns. So for example, here I have vertex 0 in the row and vertex 1 in the column. The edge that connects them has a weight of 5. And then we can go along and see that V2 and V1 are connected with a weight of 4, etc. So that's how we can actually represent a graph in a matrix form, which is useful to know. So the advantage of the adjacency matrix is that it's simple, and for small graphs, it's really easy to see which nodes are connected to the other nodes. However, notice that most of the cells in that matrix were empty. That's because most of the cells are empty because the matrix is sparse. A matrix is not a very efficient way to store sparse data because you have to store all those empty cells. In fact, in Python, you usually have to go out of your way to even create a matrix structure like the one we just saw. What the adjacency matrix is good for, it's a good implementation for a graph when the numbers of edges is large. But what do we mean by large, and how many edges would be needed to fill that matrix? Since there is one row and one column for every vertex in the graph, the number of edges required to fill the matrix is the magnitude of V squared. And a matrix is full when every vertex is connected to another vertex. There are a few real problems that approach this sort of connectivity, and the problems we're going to look at in the future all involve graphs that are sparsely connected. So what we're really going to focus on is the adjacency list. We won't be using the matrix just because we're not going to have any graphs that really have that many edges. So let's discuss what an adjacency list is then, since it's what we're going to be using and it's what we're going to be implementing in the next lecture. An adjacency list is a more space-efficient way to implement a sparsely connected graph. In an adjacency list implementation, we keep a master list of all the vertices in the graph object, and then each vertex object in the graph maintains a list of the other vertices that it's connected to. In the next lecture, in our implementation of the vertex class, we're going to use a dictionary rather than a list, where the dictionary keys are the vertices and the values are the weights. So keep that in mind. Let's go ahead and show you an example of what this would actually look like. So for example, here we have our entire graph, and it has 6 vertices. So if we just look at one of them, right now we're just drawing this out as a list, but you can see that essentially each key of that vertex, V0, then has an ID, that V0, and it also has the a set with the adjacent vertices to it and the weights. So for example, V0 has ID V0, has adjacent vertices V1 and V5 with corresponding edge weights of 5 and 2. So you can see here we're actually not storing any empty data. So list is a much more space-efficient way than the matrix we previously saw. So again, that advantage of the adjacency list implementation, it allows us to compactly represent that sparse graph. And the adjacency list also allows us to easily find all the links that are directly connected to a particular vertex. So coming up in the next lecture, we're going to actually do an implementation of an adjacency list in Python. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the implementation of a graph as an adjacency list lecture. In this lecture, we're going to go over Python programming and how to use it to implement a graph as an adjacency list. In order to do this, you can go ahead and check out the notebook that's underneath the graph folder in the repository. And we're going to be implementing 2 classes, a vertex class, and then we'll use that to build out the full graph class. Before we begin building it, let's just go over a few things. What we're going to do is, as I mentioned, create that graph, which holds that master list of vertices, and then the vertex class, which will represent each vertex in the graph. Each vertex is going to use a dictionary to keep track of the vertices to which it's connected to. and the weight of each edge. That dictionary is going to be called connected to. So if you go ahead and scroll down to the code, you can see here we have a self.connected2 empty dictionary object. Then what the constructor is simply going to do is initialize the ID, which is typically just going to be a string, and the connected2 dictionary. The add neighbor method is used to add a connection from the vertex to another. We have a get connections method, which returns all the vertices in the adjacency list, as represented by the connected2 instance variable, that dictionary we created. Then the get weight method just returns the weight of the edge from this vertex, so the vertex passes a parameter. So with that being said, let's go ahead and build out this vertex and explain what we're doing along the way. It's actually a pretty simple class, and then after that, we'll go ahead and go over the details of the graph class. Let's go ahead and jump to a fresh Jupyter notebook and get started. So I'm going to zoom in a bit here so it's a little easier to see. First thing I'm going to do is say class. Let's just call this vertex. And I'm going to go ahead and say init, pass in self and key. And so the ID of the vertex is going to be that key that we pass. And then as I mentioned before, we're going to have a dictionary called connected to, and we'll initialize that as an empty dictionary. So right off the bat, we create the vertex object. We have a key and an empty dictionary connected to. Now we want a method to add neighbors. So we'll say def add neighbor. That's going to take in self, of course, and then it's going to take a variable nbr for that neighbor, and then a weight, which we'll initialize as 0, so if you forget to put in a weight, it has a weight of 0. And then we'll say self.connected to that neighbor, we create that key, and then say it's equal to weight. So what this connected to dictionary is doing is it's taking in the neighbor as the key, which will be a string, and then the weight as the value for that key. Then what we're going to do is say def, let's say get connections, self, and then we're going to return self.connected to, and we'll return all the keys of that dictionary. So that way we can just grab all the connections for that neighbor, for that connected to dictionary, I should say. Then we'll create couple more methods. We'll say get ID, take in self, and that's just going to return self.id. One more method called get weight. That will take in self and a neighbor, and then we'll go ahead and return that weight. So remember that weight is just the value at that key, so we can essentially just copy that and say return self.connected to at neighbor. Then we're going to add a special method. So this one's going to be that string method. So this is what happens when Python needs a string representation. So it's basically going to be what happens when you say print that vertex object. Python's going to look for that string representation there. And I'm going to say return a string of self.id plus, we'll say connected to, and then we'll say plus, and then what I'm going to do is use list comprehension in order to get a list of everything. So I'll say xid for x in self.connected to. And let's go ahead and zoom out a bit so you can see that whole code. So what I'm saying here is just grab every ID for x in that self.connected to dictionary. All right, so that should be it for our vertex class. We'll check up on it later, make sure it works back when we implement the entire graph class. Okay, so up next is the graph class. So in order to implement the graph as an adjacency list, we're going to have the following methods. We're going to have just the graph, which creates a new empty graph. So that's going to be this right here. We'll have add vertex, which adds an instance of vertex to the graph. We'll have add edge, which adds a new directed edge to the graph that connects two vertices. And then we'll also let that same method take in a weight argument if we want to. And that's going to add a new weighted directed edge to the graph. Then we'll have a get vertex and get vertices. This one just gets that particular vertex for that key. And get vertices just returns a list of all the vertices in the graph. And in returns true for a statement of the form vertex in graph if the given vertex is in the graph. False if otherwise. We'll explain that one a little more when we actually get to it. But let's go ahead now and implement this graph class and take advantage of that vertex class we just created. So first thing we're going to do is say class graph. We're going to say initialize it, just take in self. I'm going to say self.vert list, so list that vertices. It's actually going to be an empty dictionary, not an empty list, and we'll show why later. And then we'll say num vertices is equal to 0, and that will basically be a vertex tracker counter. Next up, what we're going to do is say make a method for adding a vertex to this graph. And so that's going to take in self, but remember, the vertex takes in keys. So what we're going to do is go ahead and add a key to that. We'll say self.num vertices is equal to self.num vertices plus 1. And you could also just say here plus 1. It's up to you. We'll go ahead and go with the shorter methods because it's a little cleaner. But basically that means, so I added a vertex, I need to add a number to the number of vertices I have in my graph. And now let's actually do that. So let's add that vertex. I'm going to create basically a temporary object here called new vertex, set it equal to an instance of the vertex class with that key that's been given. And I will say self.vertList at that key is new vertex. And just keep in mind, the reason I'm calling this list is because we're modeling this as an adjacency list, not because this actual object is the list. So keep in mind that vertList is a dictionary, but the reason it's called list is because we're modeling this after an adjacency list. All right. Then lastly, we're just going to say return new vertex. All right, so that's how we add a vertex. We add a number to our count of vertices, set new vertex object equal to vertex key, say self.vertList at that key is equal to that new vertex object, and then just return the new vertex. Next, I want to get a method for, or create a method for getting vertices. So I'll say get vertex. It's going to say self and n, and it's going to say if n in self.vertList, and keep in mind that if I say in a dictionary, it's going to say in the dictionary key. So let me just go ahead and show you an example of that real quick. If I create a dictionary and I say K1 with a value 1, and if I ask 1, or let's say if K1 in D, that dictionary, print in dictionary. But notice if I say this, I don't get anything out because it's not in there. So when you, essentially what I'm trying to say is that when you iterate through a dictionary without specifying dot iter items or iter keys or values or items, etc., it's going to automatically default to the keys. And this is for both Python 2 and Python 3. So when you iterate through a dictionary, by default, if you don't say a specific method, it's going to iterate through those keys. So why is that important? Because that's basically what we're doing here. We're saying if n is in the keys of that vert list, because that vert list has those keys, which are the vertices in that graph. Okay, so if it's in there, I'm going to return self.vertList of n. Else, I'm just going to return none because it wasn't in there. Next up, I want to say add edge. So if I want to add an edge, I'll say def add edge. Let's go ahead and take a space there. Add edge, and this is where it's going to say self f t cost is 0. So as a reminder, what do these actually stand for? This is going to be the from vertex, or vertex I should say. This is t for to vertex, and then cost is that weight. So continuing on with this, I'm going to say if the f, which is the from vertex, is not in self.vertList, meaning we're going to say nv equals, make a variable called nv, set it equal to self.addVertex. And then if the to vertex isn't in there, I'm going to say not in self.vertList. Say nv is equal to self.addVertex at to vertex. And then finally, I'm just going to say self.vertList of f, do the add neighbor method. And let's make sure we spell that correctly, add neighbor. If we scroll back up to our vertex class, we have the add neighbor. So we need to take the neighbor and the weight. So I need to say the neighbor is going to be self.vertList that to vertex. And then that weight is just the cost. So remember, f here is that from vertex, and t here is that to vertex. So here we're checking if they're actually in our vert list. So if they're not, that means kind of we're like adding a new vertex to the graph in order to add that edge. All right, so we're not returning this, we're just setting this inside the actual object. I want to make another method called getVertices, self, and say return self.vertList, and it's just going to go ahead and return the keys. So if I didn't specify keys, I would have accidentally returned the whole dictionary. Now we're going to go ahead and say some special methods here. One is the iter method. So what happens when I actually iterate through this graph object? If I say for blank and graph, in this case, what I want to do is return iter of self.vertList.values. And so what that's essentially doing is it's saying, okay, grab all the values in that vertList dictionary and then make it into an iterable object. So that basically means when I say for object or item in graph, when I actually iterate through it, I'm going to be iterating through the values in that vertList dictionary. And you can check out some more special methods. We're going to add one more called contains. And we'll say self n, and here we'll just return n in self.vertList, and that allows us to use that n in operator. Okay, so I ran that. Let's go ahead and actually check if it ran and make sure we don't have any errors here, because it's quite a bit of code. Might have an error somewhere, but let's go ahead and see if it works. So I'm going to say G is an instance of a graph object. So far so good. And then I'm going to say, let's say for, zoom in here because I zoomed out quite a bit. Let's say for I in range 6, we'll say G dot add vertex of I. So basically just keep adding those numbers. Okay, that worked. So let's go ahead and call the vertex list from it. All right, so we actually have 0 through 5 vertices. So let's go ahead and make sure we can add an edge here. So this is essentially that V0, V1, V2, etc. If you remember back from the presentations in earlier lectures. Let's go ahead and try adding an edge. So I'll say go from vertex 0, so that from vertex 2, which is that T, to the 1 vertex, and give it a weight of 2. So what is this actually doing? If we go back and check here, if I'm saying add edge, I'm saying my from vertex and my to vertex and that weight. Then I can check if the from and to are in there. If not, I add those vertex and then I say self-vert list, add a neighbor to it. So let's go ahead and check it out, make sure it works. Looks like it did. So I'm going to say now, say for vertex in G, and what does that actually mean for vertex in G? That actually allows me to take advantage of the special methods I created. And I'm going to print vertex. I'm going to say print vertex dot get connections. And then I'll print a new line after that. So let's see if this works. All right, looks like it did. So what is this actually doing? It's going to print the vertex and then print all the connections of that vertex and then print a new line. So remember I have 6 vertices in this adjacency list graph, 0 through 5, and there should only be one connection because I only added one edge. And it's actually here. It says 0 is connected to 1, which is exactly what I had here. So it all worked out. I encourage you to play around with this methods, or with these methods, I should say. Build out your graph a little bigger, but really just understand what's actually happening here in relation to that figure of the adjacency list. That's really all there is to it. So just to review what we did, we created a class vertex. We have add neighbors, get connections, and a bunch of other get weights, get IDs, but really the key here is just set it as a dictionary with a key and say it's connected to weight if we need it. So we have that connected to a dictionary and we can add neighbors to it with weights. So that's the vertex class, and then for the graph class, it takes advantage of the vertex class we just made. So it can add vertices to it with a number of vertices tracker, and we again use a vert list. Again, just to really say this, this is a dictionary, and the reason it's called a list is because it's an adjacency list form. But when we're actually dealing with it, we're working with it as a Python dictionary. It just makes it a lot easier to create this class. Then we can add edges, and everything else is essentially just special tools or methods to work with that graph class as far as getting objects from it, or iterating through it, or checking if it's in something in that class. Okay, that's it. I encourage you to check this out. Again, there's a bunch of notes in case you want to check out all the explanations in the Jupyter Notebook. All right, that's it for the implementation of a graph as an adjacency list. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the word ladder problem lecture. In this lecture, we're going to learn about what the word ladder problem is. We're going to see how we can solve that problem with a graph. We're going to see an implementation of a solution in Python, and then we're going to begin thinking about graph traversal. A quick note on the implementation of a solution in Python, we're not actually going to live code anything out, because the main purpose of this lecture and the word ladder problem in general is just to get us thinking about how we can actually traverse through a graph and what kind of problems we can apply a graph to. So what is the word ladder problem? So consider the following puzzle. You have to transform the word fool, F-O-O-L, into the word sage, S-A-G-E. And in the word ladder puzzle, you must make a change occur gradually by only changing one letter at a time. At each step, you must transform one word into another word, and you're not allowed to transform a word into a non-word. So to give you an example, imagine you have fool here, which will transform into pool by only changing one letter. Then we can transform that into pole, and then pole again, pale, sail, and then sage. So at each step, we only change one letter, and we slowly transform fool into the word sage. So that's the basics of the word ladder problem. And what we want to know is that we can actually solve this problem using a graph algorithm. What we can do is represent the relationships between the words as a graph, and then use the graph algorithm known as breadth first search, which is what we want to begin thinking about, to find an efficient path from the starting word to the ending word. So what we want to do is figure out how to turn a large collection of words into a graph. And what we would like is to have an edge from one word to another if the two words are only different by a single letter. Then any path from one word to another is a solution to the word ladder puzzle. So let me show you what I mean by that. Imagine you have here this graph, and here we have fool, and here we have sage. And you'll notice that the actual edges connect one word to another only if they're removed by one letter. And what you should also notice is that this is an unweighted edge on all of them, and it's also an undirected graph. And remember, directed graphs are where edges only point in one direction. In this case, all the edges point in two directions because you can jump from one word to another in both directions. Okay, so the edges are unweighted and it's an undirected graph. So how could you actually build out this graph? There's several approaches. One approach you could do is take the assumption that you already have a list of words that are all the same length. So imagine you had all these words in the list, and they're all the same length, 4 letters. As a starting point, you can create a vertex in the graph for every word in the list. To figure out how to connect the words, you could compare each word in the list with every other. And then when you compare, what you're looking for is see how many letters are different. If the two words in question are different by only one letter, then you just create an edge between them in the graph. So that thinking might work for a very small set of words. It'll be fine. However, if you have a list of thousands of words, roughly speaking, you're going to have a order n squared algorithm because you have to do a comparison from this word to every other word. So it's almost like a nested for loop. So you can actually do a lot better than that. And then what you can do is suppose that you have a huge number of buckets, each of them with a 4-letter word on the outside, except that one of the letters in the label has been replaced by an underscore. So for example, as you can see in this figure, we might have a bucket labeled POP underscore. And as we process each word in our list, what we do is compare the word of each bucket using that underscore as a wildcard. So then both words like Pope and Pops would each match POP underscore. And every time you find the matching bucket, you put the word in that bucket. And once we have all the words in the appropriate buckets, we know that all the words in the bucket must be connected. So that's a way better and more efficient way of actually creating the graph we just saw versus the n squared algorithm we were thinking about, comparing each word to every other single word. This bucket solution with the blank is a lot better. So in Python, you can actually implement that scheme by just using a dictionary. The labels on the buckets we've just described are the keys to our dictionary, and then the value stored for that key is a list of words. Once we have the dictionary built, we can create the graph. We start our graph by creating a vertex for each word in the graph, and then we create edges between all the vertices we find for the words found under the same key in that dictionary, which is essentially that bucket. So let's go ahead and see the implementation in Python. Again, we won't live code anything out. We just want to begin to think about how we can build graphs to solve problems. So let's go ahead and jump to the code. So here we are now at the word ladder example problem notebook. Again, here I'm just actually on GitHub, not NBViewer, because we're not going to code anything out. I'm just going to go ahead and explore the code a bit so we can get a better understanding. So in order to construct the graph, I've just copied and pasted, and you can import this if you want, the vertex class that we created earlier, as well as the graph class. And this is what the build graph essentially code or function would look like in case you want to do this. So again, what you're doing here is the labels on those buckets we've just described earlier are the keys in our dictionary. And the value stored for that key is a list of words. Once we have the dictionary built, we can create the graph. And then you start our graph by creating a vertex for each word in the graph. So then we create edges between all the vertices we find for our words found under the same key. So in this case, we've opened a giant list of words. You said for line in the word file, go ahead and print the line and print the word if you're curious. You can just hashtag those out if there's too many words. Grab the word, and then say for I in range length of word, essentially just insert that underscore there, and then you're setting those as buckets, which are essentially your keys. Then you're saying for the bucket in that key, and then for the word in that bucket, again for word 2 in that bucket, if they don't equal each other, add an edge between word 1 and word 2. Alright, so again, you can check this out. I encourage you to go through it, but really, this is just to get us to think about how we can use a graph to solve real problems, and how we can traverse a graph. So in the next lecture, we're going to dive much deeper into how we can actually traverse a graph and search for something in a graph. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on breadth first search algorithm, or BFS. So in this lecture, we're going to get an overview of that BFS algorithm, and we're going to continue to build off that example of that word ladder problem. So what we want to know now is how can we find the shortest solution to the word ladder problem? We were able to build out that graph efficiently using that buckets method, but now what we want to do is actually find the solution to it as we traverse the graph or go through the graph. The graph algorithm we're going to use is called breadth first search algorithm, or BFS. It's one of the easiest algorithms for searching a graph. It also serves as a prototype for several other important graph algorithms that we're going to study later. Of course, as an extra resource, there's an MIT Algorithms and Data Structures course. It's part of MIT's open courseware, and I encourage you to check it out. Here's the link so you can go to the resource section, download this presentation, or just copy and paste this link into YouTube. And I think you'll be really surprised on how well you can follow along, given that you're going straight into the middle of an MIT Data Structures and Algorithms course. Pretty much you can jump right in. We've covered a lot, and I encourage you to really use this course as an extra resource for understanding algorithms and data structures. Just keep in mind that it's really more on the theory and more basic computer science ideas, while in this course we try to emphasize which ideas are important for interview situations. So just keep that in mind, but it's a really great resource. I definitely encourage you to check it out. They have the whole playlist, and you can also check out additional homework assignments that go along with that on MIT OpenCourseWare. Again, it's a great resource, and you can jump right in. You'll really notice how you can understand already everything that they've been talking about, even though this is basically halfway through their semester. Okay, moving along, let's talk about BFS. So given a graph G and a starting vertex S, what the BFS algorithm does, it proceeds by exploring the edges in the graph to find all the vertices in G for which there is a path from S. The remarkable thing about the BFS algorithm is that it finds all the vertices that are at distance k from S before it finds any vertices that are at distance k plus 1. So one good way to visualize what the BFS algorithm is doing is to imagine that it's building a tree one level of the tree at a time. And what the BFS algorithm does, it adds all the children of the starting vertex before it begins to discover any of the grandchildren. As we go along and explain the BFS algorithm and the example code, we're going to keep track of its progress through coloring. So BFS is going to color all the vertices white, gray, or black. All the vertices are initialized to white when they are constructed. A white vertex is an undiscovered vertex. So as we go through the graph, if it's white, it means we haven't discovered it yet. When a vertex is initially discovered, it's colored gray. And when a BFS has completely explored a vertex, then it's colored black. This means that once a vertex is colored black, it has no white vertices adjacent to it. A gray node, on the other hand, may have some white vertices adjacent to it, indicating that there's still additional vertices to explore. And we'll actually see this basically diagrammed out later on in this lecture. So what the BFS does, it begins at the starting vertex S, and colors start gray to show that it's currently being explored. Two other values, the distance and the predecessor, are initialized to 0, and then none, respectively, for the starting vertex. And then finally, start is placed on a Q data structure. The next step is to begin systematically exploring the vertices at the front of the queue. So then what we do is we explore each new node at the front of the queue by iterating over its adjacency list. As each node on the adjacency list is examined, its color is checked. If it's white, the vertex is unexplored, and then 4 things are going to happen. If the vertex is unexplored, we have 4 things that are going to happen. The new unexplored vertex, which we'll call NBR for neighbor, is then colored gray. The predecessor of neighbor is set to the current node, current vert, or current vertex. The distance to neighbor is set to the distance to the current vertex plus 1, since you had to go an additional edge. And then the neighbor is added to the end of the queue. Adding neighbor to the end of the queue effectively schedules this node for further exploration, but not until all the other vertices on the adjacency list of that current vertex have been explored. So let's take a quick look at what some example code may look like. So you have a new unexplored vertex, NBR, that could be colored. So we'll start from the very beginning here. We have BFS, it takes in a graph and a start. You can say start set distance, start set predecessor, and we'll look at that. Those are just additional methods on the vertex that we're using to essentially visualize what the BFS is doing. So we begin at the starting vertex S, and then the colors start gray to show that it's currently being explored. Then the 2 other values, the distance and the predecessor, have been initialized to 0 and none respectively for the starting vertex. And then finally, the start is placed on a queue. So you have start and queue over here. The next step is to begin to systematically explore the vertices at the front of the queue. We explore each node at the front of the queue by iterating over its adjacency list. As each node on the adjacency list is examined, its color is checked. Then if it's white, which happens at this step, we do a couple things. The new unexplored vertex neighbor is colored gray, so we set color gray. The predecessor of neighbor is set to the current node. The distance to the neighbor is set to the distance of the current node plus 1. And then the neighbor is added to the end of the queue. Again, by adding neighbor to the end of the queue, you've effectively scheduled this node for further exploration, but not until all the other vertices on the adjacency list of the current vertex have been explored. So this is just a quick example code. I know we didn't actually go and create a few of these methods, but just keep in mind, it's just to help you out what the code would look like for the diagram and explanation we're about to see. So now let's take a look at how that BFS function would construct basically the breadth first search tree corresponding to the graph here. So what we're going to do is start from full and take all the nodes adjacent to full and add them to the tree. So if we go ahead and visualize that, we start with full, take all the nodes that are adjacent to full and add them to a tree. The adjacent nodes here include pool, foul, and cool. Or foil, excuse me. So pool, foil, foul, and cool. Each of these nodes are added to the queue of the new nodes to expand. So here you have a queue of the new nodes to expand. So here we are on the in progress tree along with the queue after this step. In the next step, what the BFS does is it removes the next node, which is pool in this case, from that front of the queue and repeats the process for all of its adjacent nodes. However, when BFS examines the node cool, it finds that the color of cool has already been changed to gray. This indicates that there's a shorter path to cool and that cool is already on the queue for further exploration. The only new node added to the queue while examining pool is then poll, P-O-L-L. And the new state of the tree and queue is then shown here. And what may be helpful is to open up this graph picture and see it along as we go through the BFS search. But after this is the second step. Basically, the next vertex on the queue is foil, F-O-I-L. So what does that mean? That means the only new node that foil can add to the tree is fail, F-A-I-L. And as BFS continues to process the queue, neither of the next two nodes adds anything new to the queue or the tree. So here in this figure, we see the tree and the queue after expanding all the vertices on the second level of the tree. So now what I encourage you to do is continue to work through that algorithm on your own so that you're comfortable with how it works. So what you should really be doing now is definitely checking out that MIT video I linked earlier, and then trying to see if you can continue with this algorithm until you get to Sage. And what it should look like is this figure right here. So I encourage you to take this figure and see if just basically mentally you can build this out as your path, as you construct the tree in your mind using BFS. And if you want further explanation of BFS, then you can definitely reference that video that I mentioned at the beginning of the lecture. So it's a bit of a complicated topic to formally write out, but the idea is actually kind of simple. So let's quickly recap what the BFS is actually doing. It starts at a vertex S, and then if we go ahead and jump to that code listing, so here we take in G and a start. So we start at a vertex S, and then what we're going to do is then color that start variable gray to show that it's currently being explored. So remember, we have three colors here: gray, white, and black. All the vertices are initialized to white when they're constructed. So that means a white vertex is an undiscovered vertex. When a vertex is initially discovered, it's colored gray. And then when a BFS has completely explored that vertex, then it's colored black. And again, once a vertex is colored black, it has no white vertices adjacent to it. And then the gray node, on the other hand, may have some white vertices adjacent to it, indicating that there's still some additional vertices to explore. And so in this coding list, the distance and predecessor are initialized to 0 and none for that starting vertex, and then we place that start vertex on the queue. Then the next step is to begin to systematically explore the vertices at the front of the queue. And we explore each new node at the front of the queue by iterating over its adjacency list. So again, refer to the adjacency list lecture for what's actually happening when we iterate over it. But basically, as each node on the adjacency list is examined, we're going to check its color. If it's white, that means that vertex is unexplored, and 4 things are going to happen. That new unexplored vertex is then colored gray, because we're there now. The predecessor of that vertex, that NBR, that neighbor, is set to the current node, which is the current vert or current vertex variable. The distance to neighbor is set to the distance of the current vertex plus 1, and then neighbor is added to the end of the queue. By adding neighbor to the end of the queue, we've effectively scheduled that node for further exploration, but not until all the other vertices in the adjacency list of that current vertex have been explored. That way, if we reach the end, or the target, we'll reach it first. So what's the amazing thing about the BFS search solution is that not only have we solved the fool to sage problem, so given that graph, find that path, but we've actually solved many other problems along the way. Now we can start at any vertex in the BFS search tree and follow the predecessor arrows back to the root to find the shortest word ladder from any word back to fool. So up next is the Knight's Path problem, and that's going to be our introduction problem to depth first search, or DFS. So what should you do now? You should definitely go through that MIT lecture, listen to it. It's about 40 minutes long, so it is quite a time commitment, but you'll be able to jump right in, understand what they're talking about, and get a chance to see how this topic is taught in basically the best technical university in the world. And you'll be surprised at how well you'll be able to jump in, and you'll know pretty much all the terms that they're talking about, as well as the notation. Then, once you're done watching that, come take a look through this presentation, and make sure you really understand BFS and see if you can follow through those diagrams. Okay. Thanks everyone, and I'll see you at the next lecture where we discuss that Knight's Path problem and get an introduction to DFS, or depth first search. Thanks, I'll see you at the next lecture. Hello everyone, and welcome to the lecture on the Knight's Tour problem. So in this section in this lecture, we're going to explain the Knight's Tour problem, what that puzzle is. We're going to see how we can use graphs to set up the solution. We'll view a solution in Python, and then continue on to get a more general view of depth first search. Now just keep in mind, as far as the breadth first search and depth first search, so BFS and DFS, in the previous lectures we saw some basic puzzle, that word ladder puzzle, as just an introduction to an idea of why we would want to have BFS. In this lecture, we're going to see the Knight's Tour graph problem as an idea of why we need DFS. After this lecture and the next one, what we're actually going to do is have 3 lectures in a row where we fully code out and do a live code walkthrough with explanation, again of a graph implementation, an implementation of BFS, and an implementation of DFS. So while you will see code as just an image throughout these slides, keep in mind that we're actually going to live code all the algorithms in the graph overview again later on in the section of the course here. So don't worry about having to code everything that you see right now. This is just basically to give you some ideas of why we need DFS. So let's go ahead and continue on. So what is the Knight's Tour puzzle? Well, the Knight's Tour puzzle is played on a chessboard with a single chess piece, the knight. And the object of the puzzle is to find a sequence of moves that allow the knight to visit every square on the board exactly once. And you don't need to know too much about chess to get this puzzle, but what we're going to do is solve the problem using 2 main steps. One is to represent the legal moves of a knight on a chessboard as a graph. And then we can use a graph algorithm to find the path of length, rows times columns, just -1, where every vertex on that graph is visited exactly once. So let's go ahead, and check this out. So in case you're not super familiar with chess, a chess again is an 8x8 board. This is just a subsection of that board, and you have this knight. And the knight piece can move in an L fashion. So all the dots here are legal moves for the knight. So you'll see it has, here's an L, so 3, then 1, 3, then 1, 3, then 1, and that's how the knight can move. So those are all the legal moves for the knight in this particular subsection of the board. And you can see that we can represent this as a corresponding graph. So now we want to know really how we can build out this full graph. And we can actually use that using this function here, the knight graph function. So what this is going to do is the function makes one pass over the entire board, and at each square on the board, the knight graph is going to call a helper function called generate legal moves, or gen legal moves, which is actually on the next slide if you want to check that out at the same time. But basically what it does, it just creates a list of legal moves for that position on the board. Then all the legal moves are then converted into edges in the graph. Another helper function, which is called position to node ID or POS to node ID, converts a location on the board in terms of a row and column into a linear vertex number, similar to the vertex numbers shown earlier in this slide. And then if we just take a quick look at that generate legal moves function, basically what this does is it just takes the position of a knight on the board and generates each of the 8 possible moves. And then it has another helper function, legal chord or legal coordinate, and it just makes sure that particular move that is generated is actually still on the board. So you have board size here, so 8 by 8 or whatever, and you just want to make sure that the legal move doesn't bounce the knight off the actual chessboard. So again, these are in the Jupyter notebook that goes along with this lecture, but don't worry too much about them. It's just for this specific puzzle. And what we're going to do later on is actually generate, or implement, I should say, in Python, a very specific DFS and BFS after these next 2 lectures. So continuing on, if you want to know what all the possible board moves look like after you built the graph, it looks something like this. And this is something we'll revisit later, but this basically just shows the complete graph of all possible moves on an 8 by 8 board. So there's exactly 336 edges in this graph. And what you should notice is that the vertices corresponding to the edges of the board have fewer connections, right? Which are legal moves. So example, these are the vertices of the edge of the board, and they have less legal moves, which makes sense because your knight would then bounce off the board. So you can only really do 2 legal moves from the corner, which makes sense. And once again, you can see how sparse this graph is. So the graph is fully connected. If the graph was fully connected, meaning every node was fully connected to every other node, there would be 4,096 edges. But there's actually only 336 edges. That means if we were to try to use an adjacency matrix to fill out this graph or represent this graph, it'd only be about 8% full. So definitely, for larger graphs, the adjacency list is the way to go. So that's just a little reminder and throwback to that old lesson we had. So continuing on, what we're going to do is the search algorithm we're going to use to solve the Knight's Tour problem is called depth first search, or DFS. And whereas BFS algorithm discussed in the previous section builds a search tree 1 level at a time, the DFS algorithm will create a search tree by exploring one branch of the tree as deeply as possible. So in this section, again, we're going to look at 2 algorithms that implement that depth first search. The first algorithm we're going to look like is directed really particularly to this specific puzzle, the Knight's Tour problem, and it explicitly forbids a node to be visited more than once, which is exactly what the Knight's Tour puzzle was, right? We wanted to visit every position on the board exactly once as a knight. Later on, we're going to discuss a more general DFS, which we'll do in the next lecture. So the depth first exploration of the graph is exactly what we need in order to find a path that has exactly 63 edges. We will see that when the depth first search algorithm finds a dead end, which is a place in the graph where there are no more moves possible, it's going to go back up the tree to the next deepest vertex that allows it to make a legal move. And this is for the particular algorithm for solving the Knight's Tour puzzle. So the Knight Tour function, which is actually here on the next slide, but it's going to take 4 parameters. N, which is the current depth in the search tree, takes in path, a list of vertices visited up to this point, U, which is the vertex in the graph we wish to explore, and then limit, which is the number of nodes in the path. And you should note that the Knight Tour function, in this case, is recursive. So let's go ahead and explore it here a little further in depth. So you'll notice what happens is that our function again is using colors to keep track of which vertices in the graph have been visited. So unvisited vertices are colored white, and visited vertices are colored gray. And again, if all the neighbors of a particular vertex have been explored, and we have not yet reached our goal length of 64 vertices, then we've reached the dead end. And when we reach a dead end, we have to actually backtrack. So backtracking happens when we return from Knight Tour, that Knight Tour function, with a status of false. So if you return with a status of false from the Knight Tour function, meaning done was never set equal to true, it means you have to backtrack. And so in the BFS, the breadth first search, we use a queue to keep track of which vertex to visit next. And since depth first search is recursive, we are implicitly using a stack to help us for backtracking. So when we return from a call to night tour with a status of false, which happens in this line, right here when you say done is equal to that recursive call of night tour. So when you return from a call to night tour with a status of false, you're going to remain inside this while loop because you're saying and not done, right? And you're going to then look at the next vertex in that neighbor list object, which is right here, NBR list. Remember, that's just a list of getting the connections. So let's go ahead and look at a simple example of the night tour in action. And I'm going to show you some figures of what you can check out. So let's go ahead and jump to the figures. And if you downloaded this resource PowerPoint presentation, everything I just said is in the next couple of slides. So we're going to go ahead and jump forward to right here, this night tour example. So we're going to do is start at node A, and the nodes adjacent to A are B and D. So we can see this is a directed graph already. And since B is before D alphabetically, the DFS is going to select B to expand next. So let's go ahead and show that. So we've selected B to expand next to. And then exploring B happens when that night tour is called recursively. B is adjacent to C and D, so then night tour will elect to explore C next, which will be the next one. So now we're exploring C. However, as you can see, node C is a dead end with no adjacent nodes. So if you look at where the edges are pointing, it doesn't point outwards from C. So we've reached the dead end here. So now that we've reached the dead end, what we have to do is backtrack. So what we then do is set C back to white, and the call to the night tour function will return a value of false. The return from the recursive call effectively backtracks the search to vertex B. And the next vertex then to the list to explore, since we already did C, is going to be D. So then we go ahead and explore D, and we do that with a recursive call to node D. And from vertex D on, what the night tour function is going to do is continue to make recursive calls until we get to node C again. So it makes another call here. E, F hasn't been explored, so we go to F. And then finally we've reached C. And by this time, this last time that we reach C, what we'll notice is that N marker is going to be less than the limit, meaning we've already exhausted all the nodes in the graph. And that at this point we can return true to indicate that we've made a successful tour of the graph. And when we return the list, the path is going to have the values A, B, D, E, F, C, which is the order we need to traverse the graph to visit the node, each node exactly one time. So what does that actually look like if you were to try it on an 8x8 board? Well, it would look something like this. So this is the path that a knight would have to take in order to visit each part of the board exactly one time. So there's actually many possible tours, and some are actually symmetric. And with some modification, you can actually make circular tours that start and end at the same square. So there's many solutions to this problem, but you can see that using a graph, especially a recursive searching algorithm through that graph, is a great choice for trying to solve this puzzle. So that's the basic idea. Up next, what we're going to do, we've gotten this brief overview of that special use case. We're going to try to discover what general depth first search looks like, and afterwards we're going to do a full live code walkthrough of all the implementations of a graph, breadth first search, BFS, and then depth first search, DFS. Okay, thanks everyone. Go ahead and review this lecture, but this is basically just to get you a general idea of what you can use this for. Alright, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the General Depth First Search lecture. So in this lecture, again, we're just going to get a general overview of DFS, and then afterwards we're going to do a full live code walkthrough implementation of a graph and node class, a BFS, and a DFS. We haven't seen BFS and DFS live coded out yet, we've just seen images of example code. In the next lectures following this one, we're going to actually live code them out, explain all the steps you need, and then those are going to be your interview questions as well, as to implement each of those. So previously, we discussed the Knight's Tour, and the Knight's Tour is actually a special case of a depth first search. where the goal is to create a deepest depth first search tree without any branches. So that makes sense because for the Knight's Tour, we wanted to visit each node exactly one time without going back to any other nodes. So that would be your deepest DFS tree. The more general depth first search is actually a little easier. Its goal is to search as deeply as possible, connecting as many nodes in the graph as possible and branching where necessary. So it's actually even possible that a depth first search will create more than one tree. When the depth first search algorithm creates a group of trees, we're actually going to call this a depth first forest. And as with BFS, our depth first search makes use of predecessor links to construct the tree. So in addition to that, the depth first search will make use of two additional instance variables in the vertex class. That's going to be the new instance variables discovery and finish times. So this is just for the code that we're going to see later on in this lecture, that these two instance variables are going to be useful to us when we're trying to implement DFS. The discovery time variable tracks the number of steps in the algorithm before a vertex is first encountered, and the finish time is the number of steps in the algorithm before a vertex is colored black. So this is essentially what the code looks like. Here we have the entire DFS graph function or class object, and we have two methods in it. Besides the initialization method, we have DFS and DFS visit. Don't worry too much about this code itself. We'll actually implement this later on, or a version of this later on. But what I want to do is just briefly explain what this code would do as an example of a DFS. So we have these two functions or methods inside the class, DFS and DFS visit. And this implementation is basically an extension of a graph. So notice that it's inheriting a graph here. So this implementation extends the graph class basically by adding a time instance variable and then the two methods DFS and DFS visit, which we see here. So looking at this line right here, so for a vertex in self, which is zoomed in here, for a vertex in self underneath the DFS function, you'll notice that the DFS method iterates over all the vertices in the graph, calling DFS visit. So DFS visit is essentially a helper function for DFS. And the reason we iterate over all the nodes rather than simply searching from a chosen starting node is to make sure that all the nodes in the graph are considered and that no vertices are left out of the depth first forest. So it may look a little unusual to see the statement for a vertex in self, but remember that in this case, self is an instance of the DFS graph class, and iterating over all the vertices in an instance of a graph is actually a natural thing to do. So don't worry about this kind of unusual statement of for in self. Okay, so moving on, we'll check out the DFS visit method a little closer. The DFS visit method starts with a single vertex called start vertex, and then explores all the neighboring white vertices as deeply as possible. If you look carefully at the code for DFS visit and compare it to the breadth first search, or BFS, what you'll notice is that the DFS visit algorithm is actually almost identical to BFS, except for that on the last line of the inner for loop. So DFS visit calls itself recursively to continue the search at a deeper level. So if we take a look here, it's going to be recursively called DFS visit right here. So it's being recursively called, and it's going to try to do that to continue the search at a deeper level. Whereas BFS adds the node to a queue for later exploration. And it's interesting to note that where BFS uses a queue, DFS visit uses a stack. And you don't see a stack here in the code, but it's implicit in the recursive call. So I know it's a little complicated, but don't worry about it too much. We're going to walk through the full implementation later on in a future lecture. This is just to give you an idea of what it may look like if you're trying to implement this as code. So to get a better understanding of what's actually going on, let's go ahead and try to diagram this out with a sequence of figures. So this sequence of figures we're going to see is going to illustrate a DFS algorithm in action for a pretty small graph, just A through F here. And in these figures, the dotted line indicates edges that are checked, but the node at the other end of the edge has already been added to the depth first tree. And in the code that we previously just saw, this test is done by checking that the color of the other node is non-white. So let's take a look at this. The search begins at vertex A of the graph right here. And since all of the vertices are white at the beginning of the search, the algorithm visits vertex A, that very first node. The first step in visiting a vertex is to set the color as gray, which indicates that the vertex is being explored, and then we set discovery time to 1. Since vertex A has two adjacent vertices, B and D, so we can see the edges here connecting B and D, each of those needs to be visited as well. And then we can just actually make an arbitrary decision that will visit the adjacent vertices in alphabetical order. So then vertex B is going to be visited next. So its color is set to gray, and then its discovery time is set to 2. Vertex B also adjacent to two other nodes, C and D. So we're going to follow the same alphabetical order and then visit node C next. All right. So visiting vertex C brings us to the end of a branch of the tree. Because if we look at this, we have a directed edge, another directed edge, and then no more directed edges coming out of C. So we've come to the end of one branch of the tree. After coloring the node gray and setting its discovery time to 3, the algorithm also determines that there's no adjacent vertices to C. This means that we are done exploring node C, so then we can color it black and set the finish time to 4. All right. So again, when we visit C, we realize that it goes from gray to black because there's no other vertices coming out of it. We've reached the end of a branch. And since vertex C was the end of one branch, we can now return to vertex B and continue exploring the nodes adjacent to B. The only additional vertex to explore from B is D, because notice how the edge goes out to C and out to D. So vertex D is then explored, and we continue our search from vertex D, which then quickly leads us to vertex E. And vertex E, sorry I jumped a bit there, vertex E has two adjacent vertices, B and F. Normally we would explore these adjacent vertices alphabetically, but since B is already colored gray, the algorithm recognizes that it should not visit B, since doing so would put the algorithm in a loop, right? You would just constantly be going BDE, BDE, BDE. So it recognizes, okay, B is gray, meaning it's explored, so I'm going to go ahead and check out the white node here. And then we note that vertex F has only one adjacent vertex, C. So since C is colored black and there's nothing else to explore, the algorithm has reached the end of another branch. And then from here on, you can see that the algorithm works its way back to the first node, setting the finish times and then coloring each vertex black, or each vertex that it visits black. So it'll keep setting the finish times as we continue on and setting them black as you basically go in reverse. So these starting and finishing times for each node display a property called parentheses property. And this property means that all the children of a particular node in the depth first tree have a later discovery time and an earlier finish time than their parent. Okay, so I know that was a lot to take in. Again, you can check out the MIT Algorithms course video playlist for a further discussion of DFS. What we're going to do next is basically go back to our roots in Python and implement all of these graph nodes, the breadth first search and the depth first search, in a way that would be acceptable in an interview setting. So you can go ahead and explore these topics independently on your own if you're interested in graph theory a little more. But the basic 3 questions you're going to be asked in an interview, at least at a basic level, is going to be to implement a graph, to implement BFS, and then to implement DFS. So those are the 3 real key interview questions. So that's what we're going to cover, at least how to implement them in the next 3 lectures. And then your interview questions are just going to be asking you to repeat those independently. Okay, thanks everyone, and I will see you at the next lecture where we're going to actually implement everything we just learned. Hello everyone, and welcome to the implementation of a graph overview lecture. So in this lecture, we're going to implement just a simple graph by focusing on the node class. And you can refer to this lecture for the solution for the future interview problem where you're asked to implement a graph. Now keep in mind, we've actually already implemented a graph earlier in this section of the course. So if you really understood that and you felt comfortable with it, you can go ahead and feel free to skip this lecture. But in this lecture, we're just going to implement the code in this Jupyter notebook and explain it along the way, where we have a graph that's directed and the edges can hold weights, and we have three classes: a state class, a node class, and a graph class. And we build it this way just because sometimes in interviews they want you to fill out some code based off a node instead of an edge. So this is what we're going to build out. You'll notice it's going to look really similar to what we did previously, and we're going to take advantage of two built-in tools, the order dictionary and enum for enumerate. And they're basically going to allow us to, as far as the order dictionary, if we go ahead and zoom in here, there's links to the documentation at Jupyter Notebook for you. But the order dictionary, what it does, let's go ahead and look for it here. Order dict. So what an order dictionary does is basically allows you to run a dictionary, but it also remembers the orders that the keys were inserted in. So you can imagine that's a pretty useful tool for building out your graph. So it operates just like a dictionary, except that it also remembers the order that the keys were first inserted in. Okay, and the other thing we're going to be taking advantage of is enum, which is support for enumerations. And it's going to be a very basic class syntax. So we're going to say enumerations, just created using that class syntax, and it allows us to create really basic enumerations. And we're going to use that for this state class where we have unvisited, visited, and visiting 1, 2, 3. So we can call those instead of white, black, and gray like we did in the lectures. And you can see, you can read more on the documentation how you would actually grab this, but basically you just say print the representation of color red and it would give you out 1 for the enumeration. Okay, so let's go ahead and jump to implementing this. So the first thing we're going to have to do is begin by starting with that state class. So let's go ahead and say from enum imports enum. And you'll notice you may get an error where you have no module named enum. If you do have that, it means you're using Python 2 and you need to go ahead and install it. So if you need to install it, you can do that by running !pip install enum34. And if you've done a Anaconda installation, you should be able to run this. So then you just click Shift Enter and then wait for that finish to install. So I'm going to go ahead and let that install so we can use enumerate. If you're using Python 3, you don't have to worry about this step. This will work without the installation. So it looks like we've just finished installing it, so it looks all good. I'm going to go ahead and delete that. Before I do, I want to make something clear. I have an exclamation mark here so I can run this as basically a command line prompt. So you could also have put this into your command line or your terminal. So I'm going to put Shift Enter here. Let's run this again, and now you can see it works. Great. So that's going to allow us to create this really basic enumeration where I inherit from enum and then say unvisited is equal 1, visited is equal to 2, and visiting is equal to 3. Now it really depends on your interview situation whether or not something of this detail is necessary. You'll have to feel out and ask your interviewer if they really want that level of detail. But let's go ahead and then begin the node class. So we're going to initialize the node with self, and then it's also going to take in, we'll say num for num, and that's just going to be the number of that node. Some people also like to call this like the ID. So we'll say self num is equal to num. So, and then we'll say self dot visit state is equal to state dot unvisited. And that's really where we're making use of this. So it starts off unvisited, and now we can actually keep track whether it's been visited, it's visiting, or visited. So that's actually really useful. Again, it really depends on your interview situation whether they want you to take that into account, but you'll definitely gain extra points for thinking about it. And then we'll say self.adjacent as the adjacent nodes, and we'll set that equal to an order dictionary. Note, last time we were doing this, we just set this equal to a normal dictionary. Here we're going to take advantage of order dictionaries, which you may find useful for the BFS and DFS search algorithms. But in this case, for our ordered dictionary, we'll set the key is going to be the node, and we'll have that value be the weight of that vertex that connects it. And then one more thing I'm going to do is add a special method, underscore, underscore, str, underscore, underscore. So if I want to print the node, it returns something. And in this case, I'm just going to return self.num, basically the number of that node. Okay, so there's our node class, and now we just have to build out the graph. So I'm going to say class graph. I'm going to say initialize it. And I'm going to initialize it with just self. And we'll say self.nodes is equal to an ordered dictionary. And I should have pointed out earlier that we need to actually import this first before we run this. So let's make sure we actually say from collections import ordered dict. So make sure this all runs. So we have that. Let's continue on with the node. I'm going to make a method to add a node, which is basically adding a vertex, a node to this graph. And I will say node is equal to node num, so making a little temporary variable there. And then I'm setting self.nodes, that ordered dictionary, at that num equal to node. Then I'm just going to return node, that temporary variable there. So notice how I'm not saying self.node here. I call self.nodes here, so I can set that key, which is the node ID and the value. So then I can just add an edge by saying self source destination and weights. We'll set it equal to 0. So this should look extremely familiar. If it doesn't, make sure you review the first time we implemented an adjacency list. But it should look extremely familiar because last time we did this, we had from, to, and then weight was also at 0. And in this case, we'll say if source not in self.nodes, we will add that node. We'll add that source, and we'll say if the destination is not in self.nodes, meaning it's not in the graph, right? I will say self.add a node to destination. So we did this exact same thing earlier when we were doing the adjacency list, but basically what I'm saying is I'm going to add an edge, give it its source node, its destination node, and the weight of the connection between them of that edge. And what's going to happen is if the source isn't in there, I add it. If the destination is not in there, I add it. Once I've added them, I'm just going to say self.nodes source dot adjacent, and then this is where it gets a little tricky, but what I'm going to say is that dot adjacent method. So if we scroll back up, remember we have dot adjacent, which is that ordered dictionary. So I call dot adjacent, and I also then want to call self.nodes destination on it and set that equal to the weight. Okay, and that should be it. So let's make sure it worked. So we'll call G as an instance of our graph, and then we can add an edge to it. So I'll go from 0 to 1 to 5. Notice that I didn't have to actually say add node because remember, our add edge takes into account if the source and destination nodes aren't already in there. So we have that. And then we can actually say, go ahead and, well, let's just say g.nodes, get all the nodes. And there we have our ordered dictionary with 0 and 1 nodes. And if we go ahead and say add another edge, if we wanted to, we could say g.add edge. And we'll go, let's say, from 1 to 2 with a weight of 3. And that's fine too. If we look at our nodes now we have 0, 1, 2. Okay, so that's really all there is to it. Again, hopefully this felt a little familiar to you. Should have been some things that are really familiar, especially in those adding the edges, adding the nodes instead of the vertices, etc. So hopefully that all felt pretty familiar, but that's just another way to implement a graph in Python. And it's a super common interview question, and it is going to be one of your practice interview questions. So I really suggest that you review this lecture as well as the lecture where we implemented the adjacency list. All right. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on the implementation of a DFS, or depth first search algorithm. So this algorithm basically explores possible vertices, remember, from a supplied route, and it goes down each branch before backtracking. And this property allows the algorithm to be implemented succinctly in both iterative and recursive forms. So below, what we're going to do, this is the notebook that's associated with this lecture. You can go ahead and check it out, but below, the listing of actions we're going to do upon visiting each node is mark the current vertex as being visited, and then explore each adjacent vertex that is not included in that visited set. With that being said, we're going to assume that the graph is in this simplified form. So let's go ahead and copy and paste that here. And let's go ahead and get started with just the basic implementation of depth first search. So what we're going to do is go ahead and start with just a basic function, call it DFS. It's going to take in a graph and then a starting node or vertex. And then we'll say visited is equal to a set, and then we will create our stack, and that's going to be a list with start as the first element in that list. And we're going to say while stack, we'll have vertex equal to popping an item off of that stack, basically that vertex that's in that stack, that node. Remember, we can use those interchangeably. I will say if that vertex is not in visited, then I will take visited, add that vertex to it, and then what I'm going to do is say stack dot extend, and I'm going to do vertex visited, and then I'm going to return visited. So let's make sure this works before we fully break it down. Pass in graph, and let's start at node A. So if we look at the connected components of A, that's going to be this. And there you have it. There's the entire graph. So we've done depth first search. Let's go ahead and go over everything we just did. So in this implementation, we're using basically a stack-like data structure, which is that list, and we're saying visited. So all the visited vertices, it's that empty set. We set our stack equal just to the starting node, and then we'll say while stack, go ahead and pop that vertex off of it. The vertex isn't in visited yet. We're going to add that vertex, and then we're going to say stack and extend it by this term right here, graph at that vertex, meaning if we look at our graph here, it's a dictionary. So at that vertex, that value, it's this set. So let's go ahead and show you what this does. So if I go ahead and say that set minus, let's say, B or something, you'll notice you get a type error. And that's because this is actually supposed to be a set. So remember, this is what we're actually doing. And that's because basically Python's overloading of the subtraction operator to remove items from a set, we're able to add only the unvisited adjacent vertices. So if we look at this again, this is what this line is essentially doing. So graph at that vertex is going to be all the vertices that vertex is connected to, and then we subtract visited. Remember, visited is a set, so it's a set with that particular vertex on it. And then we keep subtracting until we don't get anything, and then we've built out our entire depth first search. So that's really all there is to it. It's definitely a lot simpler than BFS, or breadth first search. There's a couple other like implementation methods and functions that you can go ahead and check out in the notebook. So for instance, there's a recursive implementation here you can check out. And there's also, if you wanted to show all the possible paths between two nodes, there's also an implementation for you to check out there. And there's a bunch of resources for you in case you want to read more into it. So definitely check out, especially this first resources. I find it really good. Just goes over DFS and BFS. It's just a little blog post and just goes over, again, basic graph data structure. It's a little more math oriented, but it's still pretty relevant to what we're doing. And then it gives you, again, code for both methods, for DFS and for BFS. So I encourage you to check that out, and then it goes over generalizing too. It's a great link, great blog post, and there's the official Wikipedia links there in case you're interested in that as well. That being said, that's really all there is to it for depth first search. You take in, if we go back here, your visited, your stack, and then take the vertex, pop it off of the stack. If you haven't visited it yet, add it, and then we can just do this extension operation until we keep going, until we've actually seen all those nodes. And that's all there is to a depth first search. Okay, go ahead and check out the full Jupyter notebook for all the notes and all the implementations, but that's all there is to it. I'll see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to this lecture where we're going to be implementing BFS, or breadth first search. So this algorithm provides us with the ability to return the same results as DFS, but with the added guarantee to return the shortest path first. So remember, this has to do more with that word ladder puzzle. So this algorithm is a little more tricky to implement in a recursive manner instead of using a queue data structure. So we're going to be documenting just the iterative approach, which is most likely what they're going to be expecting in an interview setting. So we're going to be coding out this. All right, so we'll assume our graph is in the form of this dictionary. We have your vertex and then the set of vertices it's connected to. So let's go ahead and implement this out. So what do we do with a BFS? Well, our function is going to take in that graph and that starting vertex. We'll have an object visited, and that's going to be equal to an empty set. And then we'll have a queue. And we'll treat this as just a list start. And you can actually use a queue from the collections module if you want to. We're just going to be popping it off with a specified index 0 to treat it as a queue. So basically what I'm going to say is vertex is equal to queue.pop at 0. So you could just, if you wanted to, from the collections module, you could import queue as we've discussed back in the queue section. Or build out your own queue. Maybe you're asked at an interview setting. But anyways, so while the queue is still there, pop it off at 0. So that's going to be that first one. Remember that first in line. You can go ahead and review the queue lectures. And if you say if vertex is not in visited, what we're going to do is take visited, add that vertex to it, and then we're going to use a queue to extend. We'll say queue dot extend, and then I'm going to graph that vertex minus the visited, and then just return the visited. So it's extremely similar to DFS, except you notice we're treating it as a queue, so we pop off at the beginning. So what's actually going on here? Well, the main thing you should notice is that the actions performed per each explored vertex are basically the same as the depth first implementation. However, what we're doing is replacing the stack with a queue. And with the queue, what's going to happen is we'll instead explore the breadth of a vertex depth before moving on. And this behavior basically guarantees that that first path located is the shortest path present, based on the number of edges being the cost factor. All right. So if you want to check out more explanation notes, you can always reference the Jupyter notebook here. So this is what we just coded out. But there's, again, code that will actually also tell you how to print out the possible paths. So that's also helpful to know. as well as just printing out the shortest path if it's there or not. And again, some really great resources for you to check out. That's all there is to it. Again, it's really quick if you already know how to do DFS. You're essentially just switching a stack for a queue here. That way you guarantee the shortest path is the one you hit upon first. All right. I definitely encourage you to really read about graphs and DFS and BFS on your own independently. Don't just take everything you've learned from this course, but really you should explore more and use the resources provided for you to really build out your understanding. It really help complete your computer science knowledge as far as graph theory. But as far as interview questions, definitely the most important ones to know is how to implement a graph, how to implement both BFS and DFS, and then another common interview question is basically filling out this function, which is to return all the possible paths. Sometimes they ask that, sometimes they don't, and sometimes they don't even ask graph questions at all, so just keep that in mind. But basically the ones that we ask in this course are definitely the ones that you should really, really know. Okay, well, thanks everyone, and I will see you at the next lecture. Hello everyone, and welcome to your first interview question for the graphs section. This interview question is simply to implement a graph class. Now we've already seen this done twice. Once as an adjacency list, and another time as an adjacency list, but with the node class instead of that vertex class. You can do either one, whatever you feel comfortable with. There's not going to be a solution lecture after this, or after any of the interview questions here, because they're all going to be implementation questions that we've seen implemented before. Again, there's no solution. You can go ahead and check out the references to the implementations we've seen before, but that's it. Okay, best of luck, and just implement a graph class. Thanks, I'll see you at the next lecture. Hello everyone, and welcome to your next interview question. This one is to implement a depth first search algorithm, or DFS. So again, for this you can assume the graph is in a simplified form of basically in a simplified adjacency list where you have the node and then a set of the nodes it's connected to. Okay, that's all there is to it. You can go ahead and reference the previous implementation lectures for the solution. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to your next interview question. For this interview question, I want you to implement a breadth first search algorithm, or a BFS algorithm. And you can assume that the graph is in this simplified form where you have the node and then the set of connected nodes here. So it's basically a very simplified adjacency list. Okay, that's it. Go ahead and refer to the BFS lectures in case you need to see the implementation. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the Riddles section of this course. In this section of the course, we're going to discuss riddles and brain teasers in general, and in this particular lecture, we're going to discuss how to approach riddles. So, a lot of companies actually have policies now banning brain teasers and riddle type questions. And this includes Google and Microsoft. And Google became famous back in the day for asking these sort of brain teasers. But then they realized they had really little to correlate with solving and being good at brain teasers with actual performance on the job. So now they have policies to ban them. However, some interviewers are still going to ask these type of tricky questions. So there's a few types of riddles and brain teasers. The three main categories are trick questions, estimation problems, and math puzzles. Trick questions usually rely on you having some sort of weird prior knowledge and are really the worst type of riddle and brain teaser you can be asked, and hopefully you're never asked a trick question in an interview. These are really unfair problems to be asked. We do have a sort of trick question in this riddle section, but I will make you aware that it's a sort of trick question so you don't spend too much time trying to solve it. The next type of riddle and brain teaser is an estimation problem. Estimation type problems are also being banned at some companies, but you should be aware of them. So for instance, common estimation problems are how to estimate how many McDonald's there are in the United States, or estimate how many happy birthday posts are there on Facebook in a given day, things of that nature. And keep in mind, for estimation problems, you may be required to estimate things that are relevant to your position. So if you're interviewing for the Gmail team at Google, you may be asked to estimate how much time is spent on Gmail in a given day for an average person, or how many people log into Gmail every day, things of that nature. Finally, you have math puzzles. These are puzzles whose background is rooted in some sort of logic or computer science, and you should be able to solve these. And that's what the main focus of the riddle section is, these sort of algorithmic and math puzzle type riddles and brain teasers. So, how can we approach these problems? Let's find out. First off, don't panic when you get a brain teaser. Interviewers want to see how you tackle a problem. They also don't expect you to immediately know the answer. Just start talking and show the interviewer how you approach a problem. In many cases, you're also going to find that the brain teasers have some sort of connection back to the fundamental laws or theories of computer science, the data structures and algorithms that we've been discussing throughout this course. If you're stuck, it's recommended to try simplifying the problem. Solve it for a small number of items or a special case, and then see if you can generalize it. Remember to check if you can relate the problem to some sort of fundamental data structure or algorithm. And remember to break down the problems. Okay, with that being said, best of luck on these riddles. They're presented as Jupyter notebooks. So the first Jupyter notebook will present the problem, and then the second one will present the solution. We'll walk through the solution for all of them after we present the problem statement to you. Okay, best of luck on the riddles. Hello everyone, and welcome to your first riddle/puzzle problem for this section of the course. Here's the problem statement. There's a group of 4 travelers that's coming across a bridge at night, so it's dark. The bridge can only hold the weight of at most 2 travelers at a time, and it cannot be crossed without using a flashlight. However, the 4 travelers only have 1 flashlight among them. Each traveler also walks at a different speed. The first traveler can cross the bridge in 1 minute, the second in 2 minutes, the third in 5 minutes, and the fourth person takes 10 minutes to cross the bridge. Here's the challenge. If 2 travelers cross together the bridge at the same time, they have to both walk at the speed of the slower traveler. So for instance, if the person that can cross the bridge in 1 minute walks along the bridge with the 10-minute traveler, then they both have to walk at 10-minute pace, and they both take 10 minutes to cross the bridge. Alright, so your question is, what is the least amount of time in which all the travelers can cross from one side of the bridge to the other? Remember, the bridge can only hold 2 people at once, and 1 person has to be carrying that flashlight. And if 2 travelers cross together, they walk at the speed of the slower traveler. Alright, best of luck to you. Definitely want to draw this out, so practice using a pen and paper or a whiteboard to try to draw out your logic of how you would have people cross the bridge for the least amount of time possible. Okay everyone, best of luck. Hello everyone, and welcome to the bridge crossing problem solution. So this is part of a common group of something called the river crossing puzzles, and it's known as the bridge and torch problem, and sometimes the times assigned to each person are different. And there's actually solution algorithms for just generalized times. The solution of this version is this, but before I show you that, let's go ahead and check out those links. So I have a link here for the river crossing puzzle. It'll take you to a bunch of versions, and the one we're looking at is the bridge and torch problem. In this case, we had a bridge and a flashlight. So here's another example of what you can do, and there's a semi-formal approach, so you can look at the variations of the problem on those links. As far as the one we're dealing with, it looks like this. First, you have the 1-minute person and the 2-minute person cross with the flashlight, or the torch, whatever you want to call it. That's 2 minutes. Then the 1-minute person returns, and that's another 1 minute. And here's the trick to the problem. Getting 5 and 10 to cross together, and then have 2 return with the torch, then have 1 and 2 cross with the torch. A lot of people think, just right off the bat, you might as well have the 1-minute person be the guide and do all of the crossings. But the trick is this step, to have 5 and 10 cross and have 2 return. That way you can get it down to 17 minutes. Alright, that's the solution. Check out the links in case you want more variations, or draw out this solution in case you're having trouble understanding it. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next riddle puzzle problem. Here's the problem statement. You have 8 coins and a 2-pan scale. All the coins weigh the same except for one of them, which is heavier than all the others. The coins are otherwise indistinguishable. You can't make any assumptions about how much heavier the heavy coin is. What is the minimum number of weighings on that scale needed to be certain of identifying the heavy coin? Okay, best of luck. This is actually a really common puzzle, so you may have heard it before. Alright, I'll see you at the next lecture. Hello everyone, and welcome to the solution to the coins and scale problem. So here's how we go about finding a solution to finding the heavy coin. You begin by dividing the coins into 2 groups of 3, and then you have 2 coins extra set aside. So you have 3, 3, and 2. So out of the 2 groups of 3, you grab them both and put them on the scale. One group of 2 has been left off. So if the 2 sides weigh the same, the 3 and 3, then you already know the heavy coin is in the group of 2, and then you just find that out with one more weighing. That's a total of 2 weighings there. On the other hand, if when you put the original 2 groups of 3 on the scale, if either side of the scale is heavier, then you know the heavy coin must be in that group of 3. So you can eliminate all the other coins, and then place one coin from this group on either side of the scale, leaving the third coin aside. If one side is heavier, it contains the heavy coin. If neither side is heavier and they're even, then the heavy coin is the one that you actually didn't place on the scale. So this is a total of 2 weighings as well. So you can always find the heavy coin in a group of 8 just using 2 weighings. Draw out the solution in case you didn't get it, but it's relatively simple. Key to this is by making sure you were thinking outside of the box a bit and not being caught on the fact that there's only 2 pans. So you can actually divide the coins into more than just 2 groups. That's the real key to this question. Okay everyone, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the next riddle. This one's called Egg Drop, and it's probably the most common brain teaser / riddle / puzzle out of the entire group. So really try to think using the algorithms we've learned about when trying to find a solution for this problem. Here's the problem statement. There's a tower with 100 floors on it, and you've been given 2 eggs. The eggs are strong enough that they can be dropped from a particular floor in the tower without breaking. You've been tasked to find the highest floor an egg can be dropped at without breaking, in as few drops as possible. This means if an egg is dropped from above its target floor, it will break. If it is dropped from that floor or below, it will be intact, and you can test drop the egg again on another floor. So, show algorithmically how you would go about doing this in as few drops as possible. So your answer should be the number of the fewest drops needed for testing 2 eggs on 100 floors and finding the highest floor you can drop it at without the egg breaking. Okay, best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the solution to the egg drop problem. This is a really good riddle because it actually has an algorithmic background. It's kind of based on a binary search solution. So let's go ahead and walk through the solution. So let's say you were just going to start from the 10th floor and go up the floors in multiples of 10. Then if the first egg breaks, say at floor number 20, you would know you just need to check all the floors between 11 and 19 with the second egg to see which floor it won't break at. In that simple example, remember we're kind of looking at sub-problems right now, that worst case number of drops is 19. If the threshold was 99th floor, then you would have to drop the first egg 10 times and the second egg 9 times in a linear fashion. So what's the best solution? We want to minimize this worst case number of drops. And for that, we'll generalize the problem to n floors. Again, another good tactic in an interview situation, generalizing problems. What would be that step value for the first egg? Is it still going to be every 10 floors? You know, if we have 200 floors, is the step value still going to be 10? The point to note here is that we're trying to minimize the worst case number of drops, which happens if the threshold is at the highest floor. So our steps should be of some value which reduces the number of drops of the first egg. So what we're going to do is assume we take some step value m initially. So if every subsequent step is m minus 1, then we have m plus m minus 1 plus m minus 2 plus so on, so on, so on, until you get all the way to 1 equals n. And this is actually just equal to m multiplied by m plus 1 divided by 2 equals n. So this is actually just simply a binary search, and that's really what this question is trying to get at. If n is equal to 100 here, then the letter m can be solved for, and it's going to be equal to 13.65 if you have 100 floors. Since you can't drop from a decimal of a floor, you'll have to round that up to 14. Which means the worst case scenario is when the threshold is in the first 14 floors with the number of drops being 14. Alright, so you can find plenty of other explanations by simply Googling the term 2 eggs, 100 floors, in case you want a better breakdown of how you can use the binary search in order to solve this problem. Okay, that's it for this riddle. Make sure you know this one. Again, look up other explanations in case you want a more detailed solution, but that's all there is to it. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next riddle. This one's called hallway lockers. You're in a hallway lined with 100 lockers, and you start on your first pass and open up all the lockers, so that all the open lockers now have their doors open outwards, so all 100 lockers have been opened on their first pass. Then, on your second pass, you begin by closing every second locker. Then you make a third pass, and this is what you do on your third pass. You go on every third locker, and you close it if it's open or open it if it's closed. And we'll refer to this as toggling the lockers. Then, you continue toggling every nth locker on pass number n. So on your fourth pass, you're going to go for every fourth locker and then check if it's closed, you'll open it. If it's open, you'll close it. You'll toggle those lockers. Then on your fifth pass, you'll go on every fifth locker and toggle those. After you pass 100 times in the hallway, so your 100th pass, and that includes your first pass where you opened all the lockers, on your 100th pass, you're only going to toggle locker number 100. So the question is, after that 100th pass, how many of the lockers remain open? Alright, this is a pretty hard riddle to solve, and it's really just a math puzzle. So keep that in mind, and best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the solution for the hallway lockers problem. This is probably one of the trickier ones out of the set of riddles, so let's go ahead and walk through the written solution in the notebook. So obviously you just can't brute force and count out this problem. Since there's 100 passes, there's just too many to count, so you'll need to think about this algorithmically. So let's begin by solving this problem, choosing an arbitrary locker, and see if we can then detect a pattern. So we'll start by choosing just locker 12, and then seeing if it's been toggled open after your first pass. So to start off, we know we won't have to toggle it on any pass greater than 12. So we just have to think of the passes that occur on 2 through 11. And we're actually going to be able to count these out. Remember, it's a good strategy to get smaller subproblems. And in this case, we're just looking at singular locker. So if we count these out, we know on pass number 2, we're going to toggle 2, 4, 6, 8, 10, 12. On pass 3, we toggle lockers 3, 6, 9, and 12. Pass 4, we toggle 4, 8, and 12. On pass 5, we don't toggle the number 12 locker. We just go 5 and 10. And then we've passed 12 already, so we don't toggle it. On pass 6, we do 6 and 12. On pass 7, we do 7 and 14. There's no toggle on that pass, etc. So hopefully now you're seeing a pattern emerging. We're only toggling the locker when the pass number is a factor of the locker number. And we can begin to make the generalization that all lockers started open after the first pass and alternate between being open and closed. So lockers are closed after the second, fourth, sixth, and so on times they are toggled. In other words, if a locker is toggled an even number of times, then it ends closed. Otherwise, it ends open. And you know that a locker is toggled once for every factor of the locker number. So you can say that a locker ends open only if it has an odd number of factors. So we've now been able to reduce the task to finding how many numbers between 1 and 100 have an odd number of factors. So we can think about this in the following manner. If we have a number I is a factor of n, we want to know what that means. It means that I times some other number, let's say j, is equal to n. So because multiplication is commutative, we can say I times j equals j times I. And that means that j is a factor of n as well. So the number of factors is usually even because factors tend to come in pairs. And if you can find numbers that have unpaired factors, you will know which lockers will be open. So multiplication is then a binary operation, so you have two numbers will always be involved. But what if they're the same number? So I equal j. In that case, a single number would effectively form both halves of the pair, and there would be an odd number of factors. And when this is the case, I times I equals n. So then we can say that n must be a perfect square. So go ahead and try a perfect square to check the solution's reasoning. So for example, for 16, the factors are 1, 2, 4, 8, 16. And those operations would then be open on 1, close on 2, open on 4, close on 8, open on 16. So as you expected, it ends open, since 16 is a perfect square, 4 times 4. So based on this reasoning, you can actually conclude that only lockers of numbers that are perfect squares end up open. And the perfect squares between 1 and 100, including 1 and 100, are 1, 4, 9, 16, 25, 36, 49, etc. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, continuously, until you get to 10 squared. So that means 10 lockers would remain open. Alright, I know we went through that kind of fast, but you have the solution notebook to read through. If you want to look at other solutions, it's the same standard solution but other explanations for it, you can just look up hallway locker 100 on Google, and you'll see that this is actually a fairly common puzzle. With that being said, make sure you read through the solution. I know we went through it kind of fast here, but really you should just take the time to draw it out and make sure you understand that you're just looking for the number of perfect squares between 1 and 100. Alright, that's it. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next riddle. This one's called Jugs of Water. It's kind of famous, but maybe you haven't heard it before. Here's a problem statement. You have two jugs, a 5-gallon jug and a 3-gallon jug, and you have an unlimited supply of water, but you don't have any measuring cups. So, using only these two jugs, the 5-gallon jug and the 3-gallon jug, how would you come up with exactly 4 gallons of water inside one of the jugs? Alright, best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the solution to the Jugs of Water problem. So this problem actually has a kind of a famous cameo in the movie Die Hard 3. So I've written out here the solution below, I'll walk through it, but if you scroll down in the solution notebook, you'll also see a reference to the movie here. Okay, so hopefully your interview is not as stressful as the Die Hard situation, but let's go ahead and walk through the solution. So, first action you take is fill the 5-gallon jug. So you have 5 gallons in the 5-gallon jug and the 3-gallon jug is empty. Then, fill up the 3-gallon jug with water from the 5-gallon jug. So now you have 3 gallons in the 3-gallon jug and only 2 in the 5-gallon jug. Then, you pour out the 3-gallon jug. Transfer the 2 gallons from the 5-gallon jug to the 3-gallon jug. Then, you fill up the 5-gallon jug. And then here's the trick. You transfer water from the 5-gallon jug to the 3-gallon jug. Since the 3-gallon jug was already full to 2 gallons, you know the empty space in it only had room for 1 more gallon left. So that 5 minus 1 becomes 4. And now you have 4 gallons. Alright, that's it for the solution. Walk through it. Make sure you should have understood logically that since you're being asked for 4 gallons, you should have immediately noted that the only jug that would have ended up with those 4 gallons is the 5-gallon jug. So you could have started logically based off that fact alone. Okay, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your next riddle. This one's called light switches. Now, a quick note before we begin this problem statement. This question has a bit of a trick to it, so don't spend too much time on it. It's more on the fun side of the brain teaser type questions. Now, I personally think this kind of problem is more of a gotcha problem, and it would be unfair to ask this riddle in an interview situation. So I wouldn't expect this sort of riddle to be asked of you. But it still might be fun to solve. So here's the problem statement. You're in a hallway next to 3 light switches, all of which are off. Each switch activates a different incandescent light bulb in the room at the end of the hall. You cannot see the lights from where the switches are, so you can't see into the room. Your task is to determine which light corresponds to each switch. However, you may only go into the room with the lights once. Okay, best of luck with this problem. Again, don't spend too much time on it because there's a bit of a trick to it. Thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the solution to the light switches riddle. So this is the one I noticed that it was a bit of a trick question, so hopefully you don't get asked this type of question in an interview, since it's not really math or logic based. The solution is to realize that you can leave an incandescent light bulb on for a while until it heats up. That's the real trick or gotcha to this sort of riddle. So I personally think it would be unfair to be asked this question in an interview setting. But once you figure out that fact, here's the solution. The solution is to turn on switch 1 and then wait for 15 minutes until that corresponding bulb in the other room is hot. Then turn it off and turn on switch 2, then head to the room. Then you know that the bulb which is hot and off corresponds to switch 1. The bulb which is on corresponds to switch 2, and the bulb which is off and cold, it corresponds to switch 3. So that was the real trick, realizing that you could keep a light switch on for a while, wait for one of the light bulbs to heat up, then turn it off, turn on the second switch, walk to the room, and then you can correspond to the switches. Alright, that's it for this problem. Again, I think it's an unfair question, but who knows, maybe you might be asked something like this in an interview. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to your last riddle. This one's called ropes burning. Here's the problem statement. You're given 2 ropes. Each takes exactly 60 minutes to burn. However, they're made of different material, so even though they take the same amount of time to burn, they burn at separate rates, and in addition, each rope burns inconsistently. So, how can you measure out exactly 45 minutes? So for instance, to give you an example, if you had to measure out 120 minutes, you would just burn one rope at one end, wait 60 minutes for it to fully burn, then once it finished burning, you would know to start the other rope at one end, burn it, and then you'd have measured out 120 minutes. But a much more challenging question is, how do you measure out exactly 45 minutes, given that they burn at separate rates and they burn inconsistently? Alright, best of luck everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the ropes burning riddle solution. The solution is actually quite simple, but there's kind of a trick to figuring it out. Here's the solution. You're going to take one of your ropes and burn it at both ends. Then, at the same time, you burn one end of the other rope. Once the first rope finishes burning, then you light the other end of the remaining rope. And then when it burns out, that's already been 45 minutes. The key to this problem is really understanding what were the possibilities of actions that you were able to take. You already knew you could only burn a rope, and the trick was realizing you could burn both ends of a rope. So just keep in mind, when you're facing a riddle like this, what can you physically do to solve the problem? So you know you can burn rope at one end, and then you should figure out you can burn it at both ends. So start trying different combinations and see how the timing works out. Alright, so that's it for the solution. Again, maybe draw it out if you still didn't get it, but that's it for the ropes burning problem. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the Introduction to the Mock Interview section of this course. In this lecture, we're just going to be going over some general non-technical questions, resources for you, and also the structure of the mock interview section of the course. So in this section of the introduction, you're going to have a list of general non-technical questions you may be asked, such as questions during a phone screen with a recruiter, so you can get that in the next lecture. And then you also get a list of questions that you should ask after the interview. So make sure you actually review those questions. Non-technical questions, we won't really discuss those in a mock interview. We're going to focus more on actual technical questions. Make sure you can answer several non-technical questions for the company that you're applying to. As far as the mock interviews themselves, you'll usually see two folders in your NB in the packet or on nbviewer.org. It's going to consist of interview problems and then another folder called interview problem solutions. So pay careful attention to the requirements. Sometimes they ask you to just use a pen and paper, and also note the simple format. You're not going to have a cell to test your solution. You're basically just going to be asked a question and be asked to make reasonable assumptions for your answer or your solution. So again, those mock interview questions are just going to be simple, usually just a few lines of a question, and that's it. Moving on. What you should really do is record yourself talking or explaining out loud. A lot of the mock interview section questions are going to ask as a requirement that you don't code out your solution, that you actually write it on paper and pencil or on a whiteboard. So practice with a friend or family member, give them the solutions, and you can have the interview problem yourself. It really helps for you to record yourself or practice with a friend so you can see how well you do and get the real life situation of talking to someone in a room and explaining your thought process. Again, make sure you have a paper and pen or paper and pencil or some sort of whiteboard, because a lot of the mock interview questions aren't going to be coded out. You'll have to do them by hand. Once you've attempted all the problems for a specific company's mock interview, then take a look at the solutions. So don't go one at a time. Do all the phone screen and on-site questions first, and then attempt the solutions. Again, the problems are going to feel much harder than the previous exercises and interview problems we've done previously in this course. And that's because they're not going to be attached to a certain section, so you'll have to think of what strategy works best. Practice the interview problems you missed again after reading the solution. So after you go through a mock interview, all the phone screen and on-site questions, and then check your solutions, for the ones you missed, make sure you practice that interview problem again, and hopefully recording yourself or doing it with a family member or a friend. So with that being said, best of luck. Let's go ahead and get started. In the next two lectures, you'll see that list of questions you should be able to answer, and after that, we'll get started with the mock interviews. Thanks everyone, and I'll see you at the next lecture. Hello everyone, welcome to the non-technical questions lecture. So in the next lecture, you'll see a list of questions, and what I want you to do is practice answering these for your dream companies. And I also want you to record yourself answering these questions, or answer these questions when you're in front of a family member or friend, so you can really get a feel for what it's like to practice answering these questions in a real situation with someone else. And recording yourself allows you to hear yourself and see how good of a job you're doing. Alright, that being said, go ahead. There's a huge list of questions, so just pick out 5 for each of the mock interviews to answer. Okay, thanks everyone. I'll see you at the next lecture. Hello everyone, and welcome to this lecture where we're going to be discussing about questions you should ask after or during an interview. So usually after an interview, you'll be asked, so do you have any questions for me? They'll give you about 5 to 10 minutes, depending on the company, as a period of time where you can ask them questions. And remember, you're interviewing the company just as much as they're interviewing you. And you should always have questions to ask after an interview. You can ask them during their interview if it's more conversational, but usually there's a set time to ask it after the interview. So the next lecture contains a huge list of questions for you sorted by category, but let's just discuss general concepts about asking these questions. So first we want to do is clarify your uncertainties. So your first step should be to ask anything about the position that hadn't been covered during an interview. though don't ask questions that you should already know the answers just by looking at the job description or the company website. So type of questions would be, what's a typical day look like? How will I be trained? What are the performance expectations over a certain period of time? Stuff like that. After that, you're going to want to remove their doubts. So ask questions that will allow you to talk about any strengths or accomplishments that you didn't get to cover during the interview. And then once they answer, you can clarify or reiterate why you're a good match for the position. So questions like that are, what are the skills or experiences you're looking for in an ideal candidate? Something like, what types of skills is the team missing that you're looking to fill with a new hire, etc. Then, and this is really important, you want to uncover red flags. This can be tricky to do tactfully, but asking questions about turnover, culture, and growth opportunities during the interview process can really prevent unpleasant surprises down the road. And these type of questions are especially important for small startups. So you can ask these questions in the form such as, what is the company culture like? Can you tell me about the team I'll be working with? Where's the last person who held this job moving on to? So you just want to be careful and really get a sense of what the company's truly like, what company culture is like. And you can go ahead and check out the next lecture in the list there. And we have plenty of questions that address these sort of concerns. After that, you want to get a view of the future. So asking questions about the growth of the company and its employees is a good idea for two reasons. First, it gives a good perspective on what their values are and how you may or may not fit with a company. Secondly, asking about the future of a company and the opportunities there for your own growth shows that you're committed for the long haul and you're eager to learn. These type of questions can be, where do you see this company in the next few years? What training programs are available to your employees? And what are the opportunities for advancement? All right, and then you may want to build a relationship. So you can always fall back to asking the interview about himself or herself. Remember, don't get too personal and pay attention to how the interviewer is reacting to your questions. So these type of questions can be like, how long have you been with the company? What did you do before? Why did you choose this company? And what's your favorite part about working here? Sometimes, as far as red flags, some people ask, what's your least favorite part about working here? But really gauge their reaction to make sure it's an appropriate question to ask. All right, with that being done, as far as wrapping it up, at the end of the interview, don't forget to ask about next steps. So reiterate that you're interested in the position, and you want to ask, what are the next steps in your interview process, and is there anything else I can provide you with that would be helpful? So really wrap it up and close that deal. Okay, so look at the list in the next lecture and browse through the questions you may want to ask during an interview. You have plenty of resources there, and I encourage you to check them out. All right, thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the e-commerce company mock interview. So, for this mock interview, you're going to have a phone screen and then 3 on-site questions. Both the phone screen and the 3 on-site questions are presented as Jupyter notebooks, which you can either see on NB Viewer, or you can have already downloaded them through the links provided earlier. So the solutions are presented after all the questions. You should make an attempt to answer both the phone screen and all 3 on-site questions before checking out the solutions. Make any reasonable assumptions you have to. After that, once you've done the solutions, check back and make sure you go over the ones you missed. Another resource at the end of this section is a transcription of an interview with Miriam Park, who is Amazon's Director of MBA and University Recruiting at the time of the interview. So go ahead and check that out. She answers a ton of questions about what Amazon looks for when interviewing candidates and other information about the company. All right, with that being said, best of luck with the interview, and make sure you go over the solutions and really understand the answers to the questions provided. All right, best of luck. Hello everyone, and welcome to the phone screen for the e-commerce company interview problems. So that's going to be under the mock interviews folder, e-commerce company interview problems. And then in that folder, you have phone screen. So this is your phone screen interview question. It's called the egg drop problem. We've already seen this before in the Riddles section, so you may already be familiar with this problem. But in case you aren't, the problem statement is this. You have a tower that has 100 floors. You've been given 2 eggs. The eggs are strong enough that they can be dropped from a particular floor in the tower without breaking. and you've been tasked to find the highest floor an egg can be dropped at without breaking. If an egg is dropped from above its target floor, it will break. If it's dropped from that floor or below, it will be intact, and then you can use that same egg to drop again on another floor. Your requirements are that you use a paper and pencil or a whiteboard for this problem. So don't code anything out. Practice doing this in front of someone else or record yourself doing this explanation. Alright, that's your phone screen task. Best of luck, and I'll see you at the next interview on-site question. Hello, and welcome to the on-site question 1 for the e-commerce company. Under e-commerce company interview problems, go ahead and click on-site question 1, and you'll have this notebook. So let's go over the question statement. You've been given a list of historical stock prices for a single day for Amazon stock. And the index of the list represents a sort of timestamp, so that the element at index 0 of this list is that initial price of the stock, and the element at index 1 is the next recorded price of the stock for that day, index 2 is the next recorded price for the stock for that day, etc. So you have this list, it has a bunch of elements of stock prices, and each index corresponds with a timestamp. So index 1 happened after index 0, index 2 was the next price, index 3 was the next price, etc. Your task is to write a function that will return the maximum profit possible from the purchase and sale of a single share of Amazon stock on that day. You're given that list of prices. So keep in mind to try to make this as efficient as possible. So let's show you an example of what we mean by this. Imagine you're given a list of stock prices called prices equals, and here we have the 5 prices that stock hit during that day. So it was $12, went down to 11, rose up to 15, dropped to 3, and then went up to 10. You want to pass this list into your function, and it will return the maximum possible profit, which in this case would be $7. So you buy at 3 and then sell at 10. Here are your requirements. Try to solve this problem with paper and pencil first without using any sort of coding IDE or Jupyter notebooks. Also keep in mind that you should be able to come up with a better solution than just brute forcing every single possible sale combination. One other note, you can't short a stock. You must buy before you sell the stock. Okay, that's it. So remember, your function should be able to take in this list and return the maximum possible profit. Alright, best of luck everyone. Hello, and welcome to on-site question 2 for the e-commerce company, mock interview. So the problem statement for this on-site question is this. Given a list of integers, write a function that will return a list in which for each index, the element will be the product of all the integers except for the element at that index. So for example, if you're given a list input of 1, 2, 3, 4, you would return 24, 12, 8, 6 as a list by performing the following operations. 2 times 3 times 4 at index 0, 1 times 3 times 4 at index 1, 1 times 2 times 4 at index 2, and then 1 times 2 times 3 at index 3. So note here that at each index of your output list, what you're doing is multiplying all the numbers and all the elements that weren't at that index. So at index 0, your number was 1, so you're going to multiply all the other numbers. At index 1, your element is 2, so you're going to multiply 1 times 3 times 4. At index 2, your element is 3, so you're going to multiply 1 times 2 times 4. At index 3, your element is 4, so you're going to multiply 1 times 2 times 3. Keep in mind that indexing starts at 0 for Python for lists. Alright, here are your requirements. You cannot use division in your answer, meaning you can't use the strategy of simply multiplying all the numbers and then dividing by each element for each index. So you wouldn't just be able to do 1 times 2 times 3 times 4, get that result, and then divide by each of these elements. So you can't use that strategy. Also, try to do this on a whiteboard or with a paper and pencil first, before you start coding it out to check your answer. Alright, that's on-site question 2. Best of luck. Hello everyone, and welcome to on-site interview question 3 for the e-commerce company mock interview problem. So in this problem, you're going to be given two rectangles described as dictionaries, and your task is to determine if these two rectangles overlap. The rectangles are defined as a dictionary, so they'll look like this. Here we have rectangle 1, a dictionary. You'll have keys x and y, and they'll correspond to the x and y coordinates of the bottom left corner of the rectangle. And then you'll also be given a width and a height of the rectangle. Height going along the y-axis, width going along the x-axis. So, your task is to determine, given two dictionaries of rectangles, if the rectangles overlap, return a boolean saying if they do overlap. Then, if they do overlap, return a dictionary which describes the overlapping section, and return it in the same form as the given dictionaries. So, requirements are, make sure the dictionary you output is in the same form as the input. So it has x and y keys, and w and h keys, corresponding to x and y coordinates, and then width and height of rectangles. So, feel free to use an IDE or Jupyter Notebooks for the code, but make sure you use paper and pencil or a whiteboard to draw out your plan and logic. Make sure you also understand this dictionary representation. So I encourage you to draw out this representation of a rectangle onto a grid that you draw out. So go ahead and plot these coordinates, these width and these heights, and it really helps to draw out this problem and then think about how you can algorithmically check for overlaps. Alright. That's the interview question, on-site question 3. Best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the solution for the phone screen for the e-commerce company mock interview. So, this was the egg problem. You should have seen this before in the riddle section, but just to reiterate what the problem statement was. Basically, you have two eggs, 100 floors. The eggs are strong enough so that they can be dropped from a particular floor in the tower without breaking. If you drop them below that target floor, they're not going to break. If you drop it above, they will break. So, how can you find out what the highest floor an egg can be dropped at without breaking in as few drops as possible? Let's go ahead and see the solution for this. So if you don't understand this solution, there's tons of different explanations online. You can just Google 2 eggs, 100 floors, and they'll basically go over different ways of showing you this same solution. But let's go ahead and get a basic idea of how we can go about this logically. So let's say you start from floor number 10 and go up to floors in multiples of 10. If that first egg breaks, say at the 20th floor, then you can check all the floors between 11 and 19 with the second egg to see which floor it will not break at. So in that case, your worst case for number of drops is 19. If the threshold was the 99th floor, then you would have to drop the egg at least 10 times and then the second egg 9 times in that linear fashion. So for the best solution, what we need to do is minimize the worst case number of drops. So for that, let's go ahead and generalize that problem to have n floors. And this is something you should definitely do in an interview, generalizing problems. That's huge. The interviewer will really like that you do that, and it's really necessary to solve this problem. So what will be the step value for that first egg? Is it still going to be 10? What if we have 200 floors or 1,000 floors? How do we figure that out? So the point to note here is that we're trying to minimize the worst case number of drops, which happens if the threshold is at the highest floor. So our step should be of some value which reduces the number of drops of that first egg. So let's assume we take some step value m initially. Then every subsequent step is m minus 1. So you have m plus m minus 1 plus m minus 2 plus dot 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 all the way to plus 1 equals n, that n number of floors. And so this is actually a series which you can describe as n times n plus 1 divided by 2 equals n. This is basically the trick to the problem. If you're able to convert this into this equation, you can probably get here by yourself, but realizing that it equals this is a little trickier. Alright, so now that we know we have 100 floors, if n equals 100, then you solve for m here, then you would get 13.65. And since 13.65 is a decimal of a floor, we're actually going to round it up to 14. So now we know the worst case scenario is when the threshold of 100 floors, the first 14 floors with the number of drops being 14. So this is actually just a simple binary search, and that's really what the interview question is getting at, if you're aware of how a binary search works. All right, with that being said, if you need to review anything for this problem, definitely review what a binary search is, because that's really the key to understanding this problem. All right, go ahead and review the solution. Make sure you know this problem pretty well. It's probably the most common riddle or brain teaser out there. All right, with that being said, let's go ahead and move on to the next solution. Hello everyone, and welcome to the solution for the e-commerce on-site question 1. So, as always, you can check out the solution notebook, which has the problem statement and then the entire solution as well as an explanation and some code. So this is what we're going to be working through here and explaining how it works. So let's just go ahead and reiterate what the problem statement was. You were given a list of historical stock prices for a single day of Amazon stock. The index of the list represents the timestamp, and then your task was to write a function that will return the maximum profit possible from the purchase and sale of a single share of Amazon stock on that day. So, for example, given this list of stock prices, your function is going to return 7, the maximum possible profit, which was buying at 3 and selling at 10. All right. So let's go ahead and discuss a few things before we start coding this out. Again, you should have tried to solve this with paper and pencil first. In this solution explanation, I'm actually going to code stuff out so the syntax is clear of what we're doing. But again, you should have done this with paper and pencil first, or on a whiteboard, since that's going to be the most common way to explain these problems in a real interview scenario. Okay, so let's go ahead and think of a few things before we start coding. One thing to think of right off the bat is that you can't just find the maximum price and the lowest price and then subtract the two, because the max could come before that minimum, and then you would have an incorrect solution. So brute force method is just to try every possible pair of price combinations, but that's going to be order n to the power of 2, which is pretty bad. And since this is an interview setting, you should already be aware that there's probably a smarter solution than just brute forcing it. However, if you ever get stuck on a problem, definitely at least do the brute force solution first, and then see if you can get a better solution. In this case, what we're going to do is use a greedy algorithm approach. And again, there's a Wikipedia link here in the solution notebook for you to check out the full definition of a greedy algorithm. But basically what's going to happen is we're going to iterate through that list of stock prices while keeping track of our maximum profit. And that means for every price, we're going to keep track of the lowest price so far, and then check if we can get a better profit than our current max. So let's go ahead and implement this. So I'm going to make a function called profit, and it's going to take in a list stock prices. And then we're going to start the minimum price marker at the first price. So in this case, we're going to create a variable called min stock price. And it's going to be equal to the first element, that first price. So we have a minimum price marker, and it starts at the first price. And then we start off with a profit of 0. Max profit, what we want to return at the end, equals 0. And then what we're going to do is say for price in stock prices, we're going to do a couple things. First, we're going to check to set the lowest stock price so far. So I'm going to say minimum stock price equals, and I'm going to compare using the min function, which returns the minimum given 2 arguments. So I'm going to say min stock price and price. So it's going to check the current price as we go through that list of stock prices and check it against the minimum stock price we've seen so far, and then set the minimum stock price to whichever one of these is less. Then we're going to check the current price against our minimum for a profit comparison against the max profit. So I'm going to make another variable, call it comparison profit, and I'm going to set it equal to the current price minus the min stock price we've seen so far. So here we have the current price we're looking at minus the minimum stock price we've seen so far. And that's going to be a profit, right? Because you have a price minus the smallest one you've seen earlier as far as stock price. This should get you the profit that you need to compare at. So let's go ahead and check that profit against our max profit so far. So I'm going to say max profit equals max between our current max profit and then our comparison profit that we're comparing to. And after that, you just need to return max profit. Okay, so let's go ahead and see if this works. Profit. Let's go ahead and just pass in a list. So we'll do, let's say, 23, 12, 310. So max profit should be 7. So buy at 3, sell at 10. All right, great, this is working. So we're currently able to find the max profit in one pass, which means order n time, and in constant space, order 1, since we're not making an entirely new list. So we're still not thinking of any edge cases. So for example, there could be situations where the stock price always goes down, or if there's less than 2 stock prices in the list. Before we take care of those edge cases though, and write an improved function, let's go ahead and make sure we understand our original function. So, we take in the list stock prices. Set a variable for the minimum stock price we've seen so far. We'll start that off as that first element. Then, we want to output our max profit, which we start off at 0. Then, we go along for each price in that stock list, take the minimum stock price we've seen so far by comparing the minimum stock price we start out with the current price we're looking at, and take the minimum of those. So now we have min stock price, and that's going to be the smallest price we've seen so far. Then we want to take a comparison profit, some sort of temporary variable to compare our max profit to, which is going to be the current price minus the minimum stock price that we've seen so far. Then, for the max profit, we just compare max profit to that comparison profit and take whichever one was greater. Once you go through all the stocks, you would have found the max profit possible, and then you can return that. Okay, so now we have 2 edge cases we want to consider. One is if there's less than 2 stock prices in that list, and the other is if the stock price always goes down. So, if we jump over to the solution notebook, we should see a function called part2. And instead of coding this out, what I'm just going to do is walk through the improvements here, since the function itself is really similar, just taking care of these 2 situations, these edge cases. So if there's less than 2 stock prices in the list, that's really easy to check. We just say here the length function, len. So we check length right off the bat. We say if length of stock prices is less than 2, we raise some sort of error. Need at least 2 stock prices for that day. The first one, the stock price always goes down, is a little trickier, but we can take care of that by returning a negative profit if the price decreases all day. That way we can know at least how much we lost. So how do we actually do this? Again, we start with a minimum price marker, set it as the first price. And here's where it's a little different. We start off with initial max profit, which is just the second element minus the first element. So index 1 minus index 0, that first possible profit. Then, for each price in stock prices, skipping that very first element, index 0, since we've already taken it into account in the max profit, we're going to do some reordering here in order to track a negative profit if it shows up. We take our comparison profit first, which we can do since we've already set max profit equal to the second minus the first element. Then we compare our max profit, and then we check the lowest stock price. And after you do those comparisons in that order, you return max profit. So, if you pass in a list of a single element, you'll have this error, or this exception raised, need at least 2 stock prices. If the stock prices always continue downwards, you can take care of that as well by returning best case situation where, in this case, it would be buying at 22, selling at 21 for the minimum loss, which is -1. All right, so make sure to keep edge cases in mind, especially if you solve the original question fairly quickly. And make sure you review this question. It's a pretty common one, so it's important to know about greedy algorithm approaches and how you can use it to solve this problem. All right, go ahead and review the solution. Hopefully you did well on that problem, and I'll see you at the next solution lecture. Thanks, everyone. Hello, everyone, and welcome to on-site question 2 solution for the large e-commerce company mock interview. So let's go ahead and review the problem statement and then check out the solution. Problem statement was this: given a list of integers, write a function that will return a list in which for each index, the element will be the product of all the integers except for the element at that index. So if you were given 1, 2, 3, 4, you return 24, 12, 8, 6, because you're multiplying by every other number that's not at that index. Okay, so we can't use division in the answer, meaning we can't just multiply 1 times 2 times 3 times 4 and then go about dividing by each element. So how do we go about doing this? Let's go ahead and think about our strategy first. So if you look at the list above with the multiplication, you'll notice we have repeating multiplications, such as 2 times 3 or 3 times 4 for multiple entries in that new list. So what we're going to do is take a greedy approach and keep track of these results for later reuse at other indices. We'll also need to think about what if a number is 0. In order to find the products of all the integers, except for the integer at that index, we're going to actually go through our list twice in a greedy fashion. On the first pass, we're going to get the products of all the integers before each index. Then on the second pass, we'll go backwards through the list and get the products of all the integers after each index. Then we just need to multiply all the products before and after, and then you have the final product answer. So let's go ahead and code this out so it's a little more clear. All right, so we have this function here with comments in case you want to check it out, but we're going to actually code this out ourselves. So first thing we're going to do is just start the function. We'll call it index underscore prod, and it's going to take a list LST. Let's go ahead and create an empty output list to start off with. So in order to do this, I'm going to say a list of none, and then multiply it by the length of the input list. And so now our output is a list of nones, just empty objects, but it has the same length as our output list, so we can go and switch out through indices on that output list. So I'm going to set an initial product and index for that greedy run forward. So I'm going to say product equals 1, and I'm going to set I equal to 0. And now here's what we're going to do. We're going to say, while I is less than the length of that list, we're going to say output of I, so output at that index, equals product. And then we're going to do a cumulative product, so I'm going to say then product equals LST I, that input list, that index, and then we just move forward. So that's our greedy run forward. So we set index as a cumulative product, multiply it by each index or element at that index, and then move forward through the list. So we're moving forward through the list until we've reached the length of that list. And then for a greedy run backwards, we're going to do the same thing. Reset product equal to 1. And now start index at the last. So instead of I equals 0, we're going to say I equal length of LST minus 1. So we're taking into account the fact that indexes start at 0. That's why we're subtracting 1 there. So our index is at the very last element of that list. And then we're going to say, well, I is greater than or equal to 0, since we're running backwards. What we're going to say is same operations as before, just backwards. So I'm going to say output of I is then equal to multiplying that product. Then product is equal to multiplying at that list. And then we're going to subtract from our I value. And then after these two greedy runs, we're just going to return the output. So let's go ahead and see if this works. Whoops. Index prod. Let's go ahead and get a list in. 1, 2, 3, 4, 5. And here we can see the results. So at the first index, we have 2 times 3 times 4 times 5. At the last index, we have 1 times 2 times 3 times 4. So in order to really understand what's going on here, it's important to review the solution. And one of the best ways to do that is to use print statements. So let's go ahead and run through this and add print statements so that we can see what's actually happening here. Remember, we're creating an empty list that's the same length as our input. So we have our output here. And then when we're running forward through it, we set our initial variable product equal to 1, and then set I equal to 0. And then we go through the list. So we have the I plus 1 statement here, and then I is less than length of the list. And then we say output of I is equal to the product. So your very first output is equal to 1. Then you take that product and multiply it by the index or the element at that index of the list and keep going. So you're just going forward through the list and multiplying everything. Then in that second loop, you're actually going backwards. You're taking that product set equal to 1, setting the index, and then subtracting from that high index as you move backwards. All right. So as far as adding print statements, it might be useful to perhaps add a print statement here. So you can go ahead and print output. Let's go ahead and print something, and I'm using Python 2 printing style. So I can say first forward pass, and then print the output. Whoops, there needs to be a comma there. All right, now let's go ahead and check what that looks like then. And so you notice in our first forward pass, what do we have here? We have 1, our initial, 1 again, since we started with a 1, and then 2, which is going to be 2 times 1, 6, which is 2 times 3, and then 24, which is 1 times 2 times 3 times 4 here. All right, so note what's happening here. On our first forward pass, we're getting everything before. And on our second pass, when we go backwards, we're getting everything multiplied in reverse. All right. So I encourage you to look through the solution and add tons of print statements so you really understand how your forward pass and backward passes are working. The key to understanding this is the print statements and understanding how that greedy run forwards and backwards will get you your final result that you want. Okay. Luckily here, we're just using on time and on space complexity. On space complexity because we initially create a list that's n. So if your list input is n elements long, then your output you created is n elements. So you're using on space. And on time because you're going one pass here in n, and another pass in n, which is going to be order 2n, but since 2 is a constant, you can drop it and just get order n time. All right. Again, make sure you review the solution, use print statements. Those are really helpful for understanding the solution. But remember, it's just a greedy pass forward. So on the first pass, you get the products of all the integers before each index. And then on the second pass, you're going to go backwards to get all the products of all the integers after each index. Then at the end, you just multiply all the products before and after to get the final product answer, which is what we're doing on this step. All right. That being said, hopefully you did well on this. Good luck, and make sure you review the solution, and I'll see you at the next lecture. Hello everyone, and welcome to the solution to the on-site question 3 for the large e-commerce company mock interview. Let's go ahead and review the problem statement. You're given 2 rectangles and you need to determine if they overlap. The rectangles are defined as a dictionary. For example, you have a rectangle 1, you're given x and y coordinates of the bottom left corner of that rectangle, and then you're given the width and height of the rectangle. So if the rectangles do overlap, you want to return a dictionary which describes the overlapping section. Something to note here is that this problem, even though it looks pretty unique, it's actually really common. A lot of times your rectangles are either user bases somehow, or the coordinates are defined in a different way, but at the end it's just this basic problem. You're given 2 rectangles and you need to determine if they overlap. Sometimes the rectangles can be plots of land or other dimensional objects, but really it's just 2 rectangles. So be careful if they ask it a certain way, you might be confused and start going down the wrong path. But try to remember, if sounds familiar to two rectangle problems, it's really just a simple case. So let's go ahead and look at the solution. We're going to think of a few things first. And this is a problem where it helps a lot to draw out your thinking. So go ahead and grab paper and pencil and draw some stuff out here while we explain some things. We want to think about, how can we determine if there's an intersection? What if a rectangle is fully inside another rectangle? And what if there is no intersection, but the rectangles share an edge? So the key to solving this problem is to break it up into sub-problems. And we can split up the problem into an x-axis problem and a y-axis problem. And this is basically the trick to solving this problem, the fact that you can split it by axis. So what we're going to do is create a function that can detect overlap in just one dimension. First on the x and then on the y. Then we split the rectangles into x and width. So you basically just have a line, right? An x coordinate and the line width. And then the y and height components, which is another line vertical. So x and width is going to give you a horizontal line. Y and height will give you a vertical line. Then we can determine that if there's an overlap in both dimensions, then the rectangles themselves intersect. So in order to understand this calc overlap function that we're about to do, what you should do is draw out on a piece of paper two flat lines and then follow along with the function and notice how it detects an overlap. So really right now what calc overlap is going to do, it's just going to take two lines defined by a coordinate point and a width, or a coordinate point on a y and a height, and then detect that there's an overlap. So we're really just checking now if two lines, given the coordinates and the length in that particular dimension, overlap. Let's go ahead and create this function. So jumping over to the e-commerce on site 3 solution empty notebook, let's go ahead and create this. I'm going to create a function called calc overlap, and it's going to take in 4 arguments. It's going to take in coordinate 1 and dim1. So that stands for the point at the coordinate, and dimension is just the width or the height, depending on which axis we're testing. And then coordinate 2, dim2. So it takes in 2 coordinates and their respective lengths in that dimension, which is just essentially 2 lines. So what we want to do first is find the greater of the 2 coordinates. So that means if we're dealing with the x-axis, the greater of the 2 is the one most to the right. If we're dealing with the y-axis, that will be the higher point. So let's go ahead and do that. So we're going to create a variable called greater, and it's just going to be the greater point. And it's going to take in the 2 coordinates. So this is either the x coordinates or the y coordinates, just that singular number, depending on which line we're testing. And so if you draw this out, it makes sense that the greater point is going to be that start of the overlap. So go ahead and draw those lines and make sure that statement is true. And conversely, the lower point is going to be the end of the overlap. So I'm going to say min chord 1 plus that first dimension. So this is just basically the line here. Then coordinate 2 plus that second dimension. And then we want to return a tuple of nones if there is no overlap. So we can check that if greater is greater than or equal to lower, we're going to return a tuple of nones, meaning that there was no overlap. Otherwise, there's an overlap. And in this case, we're actually going to return that. We're going to say lower minus greater. And the reason we're returning it this way is so that, like the problem said, we can return that dictionary. And then we're going to return a tuple of greater minus or an overlap. Okay, so now we have this function that can detect overlaps given 2 lines. And now we're going to create a function to detect if rectangles overlap. And it's actually quite simple now. We just need to check for both dimensions. So I'm going to say calc rect overlap. It's going to take in the dictionaries that we defined earlier, 2 of them, as 2 rectangles. And then let's go ahead and say x overlap and width overlap is going to be equal to that function we just made, calculate overlap, and then we grab it from that dictionary. In this case, we want to pass in that coordinate 1 and that dimension 1, which would be width. And then we also want to do it for the second rectangle. So here we're checking the lines along the x-axis. R2, again, width. Then we're going to do the exact same thing for the y-axis. So these are the lines of the rectangles in the y-axis. So in this case, we have y overlap and h overlap, because remember, we're just doing tuple unpacking here, since we're returning tuples on the calc_overlap function. And now we're going to do y, r1 of h key, then r2, taking y, and then r2, h. And now we know, given that we have this line here, that if either returned none tuples, then there is no overlap. And we can actually do this quite simply with if not overlap w or not h overlap. So if either of these is equal to none, width or height, you could also do this with x and y, it doesn't matter since you're returning a tuple. We're just going to print no overlap and then return none. Otherwise, if that doesn't happen, then we have another return at the end, and we're going to return that dictionary form. So we're going to say x, and that's going to be equal to x overlap. We're going to return y, that's equal to y overlap. W, which is the w overlap, that width overlap. And then finally, the height overlap. All right, and that's it. So let's go ahead and review this, make sure we really understand it. The real key to understanding this is this function right here, where we separate this problem into subproblems, and we solve it along dimensions. So we're just checking if lines themselves overlap. And then if the rectangles have overlap in both dimensions, then they themselves overlap. So it's important to draw this out to really understand it, but let's go ahead and review the function first. So what's this function doing? It has a variable greater. We check which coordinate, so imagine we're doing x and width. We check which x was greater, so which one's further to the right. Then lower is the minimum of the coordinate 1 plus that width dimension here. And we know that if greater is greater than or equal to lower, there was no overlap. Otherwise, we know the overlap is just lower minus greater. Okay, so really draw this out. Draw out what this function is doing so you really understand what's going on here. Then, for the rectangle overlap, it's really easy. We just check in both dimensions. If one of them failed and there wasn't an overlap, we return none. Otherwise, we can just return that dictionary. So I'm going to go ahead and copy and paste some code so we can check an example usage of this. So we have two rectangles here. We calculate the overlap. These do overlap, so we get a dictionary answer. All right, make sure to review the answer and practice writing it out by hand. Other than that, I'll see you at the next lecture. Hello everyone, and welcome to the Large Search Engine Company mock interview. For this mock interview, you'll have a phone screen and then 4 on-site questions, presented in the form of Jupyter notebooks, just short snippets of the question, make any reasonable assumptions you have to make. For the first 2 questions, it's almost a one question with 2 parts to it, since the first 2 on-site questions are pretty related to each other. Once you get all the questions, the solutions are presented to you afterwards. Again, go through all the questions first, and then review the solutions. The ones you missed, go back and try them again. At the end of this lecture, or this section, excuse me, you can check out a resource with an interview of Google's Director of Global Staffing Programs for answers to common questions about Google's hiring process. With that being said, good luck with the mock interview. Hello everyone, and welcome to the phone screen for the Search Engine Company mock interview. This phone screen will consist of a non-technical series of questions about you and the company, and then the second half is a simple technical question that's going to be coded out. So I just wanted to remind you, you should be practicing your non-technical questions. So in this case, for this phone screen, what I want you to do is answer some non-technical questions about a large search engine company. I think you know which one I'm talking about. So go ahead and give me some background about what you do. So just go over your resume, ask or answer why do you want to work here, what's your favorite programming language and why, answer where do you see yourself in 5 years, and then maybe give a few questions about the company. After that, go ahead and move on to the technical question. So, it's going to be a little different for this technical question than others. I don't want you to write this on a paper or pencil or on a full IDE text editor with syntax highlighting. Your question is going to be, write a function that computes the nth Fibonacci number. So, a function that takes in n and then produces that nth Fibonacci number. So, where and how are you going to do this? What you're going to do is download this notebook or open it from the downloaded file, and you'll have a markdown cell below here. Now, a markdown cell is just a text editor that doesn't have syntax highlighting. You can also use just a simple notepad or word processor on either Mac or Windows or Linux, depending what you're using. But it's important to write this out in code in a text editor or word processor that doesn't have syntax highlighting. That does not have syntax highlighting. The reason for that is a lot of times when you're doing a phone screen, you'll get a technical question and you'll get a screen share program that doesn't do syntax highlighting. So I want you to practice writing down and writing out code in either a markdown cell or a word processor or text editor or some sort of notepad where you don't have syntax highlighting, but you're still coding things out. All right, with that being said, just a reminder, there's lots of ways to answer this question on writing the function, lots of different methods. See if you can come up with at least 3 different methods. In the solutions, we'll discuss the various methods on how to compute the nth Fibonacci number. This problem should be a little bit familiar because we discussed it earlier in the course. All right, with all that being said, best of luck. Hello everyone, and welcome to the on-site question 1 for the mock interview for a large search engine company. Your question is as follows. Given a dice which rolls 1 to 7 with a uniform probability, write a function that will simulate a 5-sided dice. The requirements are you must do this on a pen and paper or on a whiteboard. Don't do any actual coding until you've solved it on a pen and paper. Alright, so again, to reiterate, you're given a dice which will roll a 1 to 7 with a uniform probability, meaning each number from 1 to 7 has an equal chance of being rolled. Given that dice, simulate a 5-sided dice. Okay, don't overthink this one. It's a relatively simple answer. On the next question, we're going to reverse this. Alright, best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the on-site interview question 2 for the large search engine company mock interview. In this question, we're going to do something really similar to the last on-site question. Given a dice which rolls from 1 to 5, simulate a uniform 7-sided dice. So, you're given a dice which rolls with uniform probability, meaning each number from 1 to 5 has an equal chance of showing up. And now I want you to write a function that will simulate a uniform 7-sided dice. You must do this on pen and paper or on a whiteboard. Don't actually code your solution out to test it until you've come up with a solution by hand. Alright, with that being said, best of luck. Hello, and welcome to on-site question 3 for the large search engine company mock interview. For this question, the question is, given a string, write a function that uses recursion to reverse it. The requirement being, you must use a pen and paper or a whiteboard to answer this. No coding allowed until you've solved the problem on pen and paper. So again, given a string, write a function to reverse that string, but it must use recursion. Alright, best of luck. I'll see you at the next lecture. Hello everyone, and welcome to on-site question 4 for the large search engine company mock interview. The question problem statement is as follows. Find the square root of a given number rounded down to the nearest integer without using a built-in square root function. In Python, that's the sqrt function. So, for example, square root of a number between 9 and 15 should return 3, and 16 and 24 should be 4. So, you're going to be given a number, just a single integer, and then you have to give the square root nearest to it rounded down. So your function should be able to take any number between 9 and 15, and it will output 3. Any integer, that is, between 9 and 15, it should output 3. And then any integer between 16 and 24 will output 4, since you're going to be rounding down to the nearest integer. Remember, you have to do this without using the square root function. As far as requirements go, feel free to code this out, either in Jupyter Notebook or an IDE of your choice, but as always, it's recommended that you use paper and pencil or whiteboard to simulate a real interview setting. Alright, thanks, and I'll see you at the next lecture. Hello everyone, and welcome to the phone screen solution for the search engine company mock interview. So just to remind you that you should be practicing your non-technical question answers. I gave you some non-technical questions here that you should be able to answer. Go ahead and review the list of non-technical questions earlier in the course to really get good practice on that. As far as the solution for those, there aren't really any correct answers here. Just make sure you prepare to answer with the following questions about the company you're interviewing with. Be honest, friendly, and ready to defend any statements you make with logical arguments to back them up. So if you say, like, Python is my favorite programming language, make sure you have logical arguments to back that up. Note, you should always have follow-up questions. Go ahead and review the follow-up questions list we have earlier in this course. Now, with that being said, let's go ahead and move on to that technical question. So, here was the question: write a function that computes the nth Fibonacci number. So there's lots of ways to answer this question, and in an interview setting, you might be required to solve it multiple ways and discuss some pros and cons of each way. So we're just going to walk through the various ways of doing it. I'm going to zoom in here so you can really see it. Okay, so we're going to go through about 5 examples here, using a looping technique, using recursion, using generators, using memoization, and then also using memoization as a decorator. All right, so let's go ahead and discuss each of these solutions. So we're not actually going to code anything out, we're just going to talk about this. So using a looping technique, what are we doing here? In this particular function, we're taking advantage of Python's tuple unpacking here. So we say a and b are both equal to 1, and then we say for I in range n-1, we're just looping through that range and resetting a equal to b and b equal to a plus b, that previous a. Then at the end, we just return a. So pretty simple, pretty straightforward. Using recursion, you may be in a situation where in an interview setting, they specifically ask you to do this using recursion to test if you know recursion or not. So let's go over the solution. Here we have our recursion sequence, and then we have a base case. Remember, recursion should always have base cases. So we say if n is equal to 1 or 2, in this case we're starting at 1 and 2. You may have 0 and 1 depending where you start your Fibonacci sequence. Here we're just returning 1. Otherwise, we do a recursive call on the function with n-1 and n-2. And here we're calling on 7. Here we have another example using generators. Here again, we're taking advantage of tuple unpacking, starting at 0 and 1 for this Fibonacci sequence. Say global AB, because we're doing a generator, we have to define it outside of that function. And then say while true, we're yielding it. Really similar to that looping statement, but in this case, we're doing a generator, so you'd have to keep calling next in order to see all the results. Okay, then finally using memoization, in this case without a decorator. So we have memo here, and we're going to take in fn and arg, and we're saying if arg is not already in memo, memo at that argument is equal to argument into that function. And then we'll return memo at arg. So notice how we're using keys here. So using memoization, we're going to pass in that function and the n number we want and set it equal to an object when we put in memoize. And then if we want to use memoization as a decorator, we can actually make a class really similar in function and scope. We say def init, we initialize with some function, set memo equal to empty here, and then we say again, if arg's not already in that memoization tracker, that dictionary, we set that argument equal to the argument passed into the function. So we're keeping track of things. And then you can use a decorator to pass it into or over that regular Fibonacci looping function. Okay. As far as depicted average relative performance, went ahead and ran this on a computer so you can get an idea here. So we're doing n equals 15,000. And what are the results? Let's zoom out so we can see a little more. Here, if you're using loops, recursion, generators, memoization, and memoization as a decorator, clearly recursion, probably the worst way to go. You should know that in your interview. And that makes sense because you're having to recalculate things over and over again. Remember, we discussed in the recursion section how you can use memoization to improve on just general recursion. Also, loops, pretty straightforward, but probably the better ways to go are taking advantage of recursion through memoization. All right. Again, hopefully you were able to answer at least one of these methods in the question. It's important to get a good idea of how to approach it one simple problem through multiple different methods and understand the pros and cons of each of those. All right. Thanks, everyone, and I'll see you at the next lecture. Hello, everyone, and welcome to the solution for the first on-site mock interview question for the large search engine company. Just to reiterate what the question was, given a dice which rolls 1 to 7 with uniform probability, we wanted you to simulate a 5-sided dice, and then preferably write your solution as a function. So, what's the solution here? So this is a new problem we've never seen before, at least in the course, and many times this question is asked in the form of functions. So given a function random 7, you have taken it as an input and create random 5. The key to solving this problem is to make sure you focus on the requirement that the final distribution of the rolls be uniform. Also, you're actually not given any requirements on time and space. In that case, the solution is really simple. You just keep re-rolling if you get a number greater than 5. So to code this out, won't do any live coding, so it's pretty simple. Here we use from random import rand int. That's just a random integer generator with uniform probability. And your solution is, you start the roll at 7. It just needs to be larger than 5. And while the roll is greater than 5, you roll. And if your dice roll is above 7, you just keep doing it, or excuse me, above 5, you just keep doing it again and again until you get a roll of 5 or below. And so here, you're just converting 7 to 5 by throwing out anything that's above 5. Next problem is going to be a little trickier. It's the reverse conversion of the rolls. But this question should serve as a reminder for you not to overthink the solution to a question. Keep in mind that this solution here has the potential to keep running for infinity if you keep rolling 6s and 7s. Although that's highly unlikely, you can actually prove it mathematically. Alright, now in the next solution we'll discuss the reverse of this. Simulate a 7-sided die given a 5-sided die. I'll see you there. Hello, and welcome to the second on-site question solution for the large search engine company mock interview. So, in this question, you had the reverse of your first one, which was given a dice which rolls from 1 to 7, simulate 1 to 5. In that case, we just threw out anything above 5. Here it's a little harder, because you're given a dice which rolls 1 to 5, simulate a uniform 7-sided dice. Alright, let's go ahead and think about this and walk through the solution here. We're not going to be coding anything out live because it's actually a pretty simple idea. But let's go ahead and explain it. So, because the 5-sided dice can't produce 7 possible outcomes on a single roll, immediately we know we have to roll the dice at least twice to do this. If we roll the dice twice, then we have 25 possible combinations, 5 times 5. While 25 is not divisible by 7, we know that 21 is. So that means we can implement our previous strategy of throwing out rolls not in intended range. But it's also important to note that we can't expand the solution to implement more rolls in order to not throw any out. So for instance, there's no number times 5 where, no exponent of 5 that will be divisible by 7, no matter how high you go, because they're both primes one right after the other. So we'll need to define our range as a section of the 25 possible combination of rolls. So a good way to do this is by converting the two rolls into a unique outcome number in the range 1 through 25. Then we can create this number by taking the rolls, then we take the first roll, and after subtracting 1 from it, we multiply it by 4. Now the first roll corresponds to a value between 1 and 20. Then we take the second roll, add it to the result of the first manipulation, giving us a range from 1 to 25. So let's go over that one more time. Our main strategy is this. We're going to roll the dice twice. On the first roll, we're going to multiply it, whatever value we get, by 4. So since the dice can roll between 1 and 5, 1 to 5 times 4 gives us a corresponding range from 1 to 20. Then we take that second dice, roll it, or roll the same dice again, and add it to the result of the first manipulation, which would be 1 through 20 plus something 1 to 5. And now we have a range from 1 to 25. So our final solution is to roll the dice twice, check the manipulated range from 1 to 25, and if it's greater than 21, just like we did in the last problem, do a reroll. So let's see how this would look like coded out. Here we have a function which produces that random integer between 1 and 5. So dice 5 returns a random integer between 1 and 5. And now we have our conversion function. So we have a while true, and this is so we constantly keep re-rolling if we roll out of range. Then we roll the dice twice. We'll call roll 1 our first roll, roll 2 our second roll. Alright, I have a print statement here that you can check out yourself. It's commented out, but this might help you understand what we're actually doing. Then we're going to convert these two rolls into something on the range of 1 to 25. So how do we do that? We're going to take our first roll value, subtract 1 from it, and then multiply that by 5. That gives us a range from 1 to 20. Then we're going to roll the second dice once, and that automatically gives you a range from 1 to 5. And then you can print that converted range by summing them together, 1 to 25. So here you have 1 through 5, and here you actually have 0 through 20, because if you roll a 1, you're going to subtract 1 from it, and 0 times 5 is 0. So this portion on your first roll is converted to a number that falls between 0 and 20, and this one gets converted to a number that falls between 1 and 5. Summing those together, you have a range of 1 to 25. Since we're only considering 1 to 7 simulation, we'll say if the number is greater than 21, re-roll, just like we did in the last one. And then we can finally just use mod 7 plus 1 to get that conversion. Since 1 through 21 is evenly divisible, since 21 is evenly divisible by 7, we can just mod by 7 and add 1 to basically break up 1 through 21 into chunks. Okay, so make sure you check out this solution. It helps if you write it out by hand or added print statements in here, but that's really all there is to it. Alright, make sure you review it and understand it, and I'll see you at the next solution. Thanks everyone. Hello everyone, and welcome to On-Site Question 3 solution for the Large Search Engine Company mock interview. This question was, given a string, write a function that uses recursion to reverse it. So, hopefully you remember this problem. You've already seen it in the recursion section of the course, but let's go ahead using Python slicing, so we're not going to code anything out. Since you're having to use recursion here, you should always be thinking, what's my base case? So, in this case, we're saying, if the length of the string is less than or equal to 1, just return that string, which makes sense. That's your base case when you've only had the last element or letter of that string left. As far as the recursive case, you're going to return the call on everything of that string from index 1 forward, plus the first element of that string. So notice how we're reversing it here. You're popping off that first one and then reversing everything else. And then as you continue doing this, you're recursively reversing the string. So go ahead and review this problem. Go back to the recursion section in case you need to review anything. But that's really all there is to this question. Make sure you always remember about base cases when someone says you need to do something recursively. Alright, that's about it for this. I'll see you at the next solution. Thanks. Hello, and welcome to the solution for the fourth on-site interview question for the large search engine company mock interview. So, just to reiterate what the question was, we needed to find the square root of a given number rounded down to the nearest integer without using any built-in square root functions. In Python, that's sqrt from the math library. So, for example, if you're given any number between 9 and 15, your function should return 3. Any number between 16 and 24, your function should return 4. Alright, so how do I actually go about solving this? Well, we need to know a little fact, and that fact is this line right here. The square root of a non-negative number n always lies between 0 and n divided by 2. And so that becomes a fact that we can use so that the straightforward way to solve this problem is just to check every number, let's say k, that comes between 0 and n divided by 2 until the square of k becomes greater than or equal to n. If k squared becomes equal to n, then we just return k. Otherwise, we return k minus 1 because we're rounding down. So let's go ahead and implement that in a function and explain the logic that's going on. So I'm going to make a function called solution. And I'm going to say, if num is less than 0, then we have issues with trying to take the square root of a negative number. We're not worried about imaginary numbers in this case, so I'm just going to say value error. So return some sort of exception there. After that, I'm going to check if my number is 1. In that case, I know just to return 1. Square root of 1 is 1. And this is where we start our algorithm. So I'm going to say for k in range, and I'm going to go from 0 to num divided by 2. Since indexing starts at 0, I'm going to say num divided by 2 plus 1 to do this in Python. And then I'm going to say if k squared is equal to num, return k. And then I can say else if k squared is greater than num, then return k minus 1. And then return k. Okay, so that was actually pretty straightforward. We're just going through and checking every number k between 0 and n divided by 2, squaring that k value until it becomes greater than or equal to the n we're checking. And then if k squared becomes equal to n, then we just return k. Otherwise, since we're rounding down, we're going to return k minus 1. Alright, so we can go ahead and check that out. Solution, put in a number, let's say 14, and we get 3. And that makes sense. If we keep going to 15, we should still get 3. And then finally at 16, we should break that barrier and go to 4, since 4 times 4 is 16. The complexity of this approach is O(n). So because we have to check n divided by 2 numbers in the worst case. So this linear algorithm is actually pretty inefficient, and we can use some sort of binary search to speed it up. So remember, we've used binary search in other interview problems, so it's going to come up here as well. Since we know that the result is between 0 and n divided by 2, we can first try n divided by 4 to see whether its square is less than, greater than, or equal to n. If it's equal, then we simply return that value. If it's less, then we continue our search between n divided by 4 and n divided by 2. Otherwise, if it's greater, then we search between 0 and n divided by 4. So we get this binary search pattern by keep cutting things in half. In both cases, we reduce the potential range by half and continue. This is the logic of that search. So this should sound familiar from that egg drop problem. Here, we're not performing regular binary search, though. It's going to be a little modified. We want to ensure that we actually stop at a number k, where k squared is less than or equal to n, but k plus 1 squared is greater than n. So let's go ahead and implement this more efficient solution. So we'll call this better solution. Pass in num. And let's go ahead and zoom in here so we can see our function. Again, I'm going to start by just checking if it's less than 0, and I'll raise an error. You can raise any exception here. I'm just raising a value error. And then again, if my number is equal to 1, I'm just going to return 1. Okay, so let's implement this better solution, kind of a modified binary search here. I'm going to say I'll have a variable called low is 0, and I'll set my high equal to that top of the range we discussed earlier, which was num divided by 2 plus 1. I'm going to say while low plus 1 is less than high, here's what we're going to do. We're going to take, since we're doing a binary search, the middle, and we're going to say the middle is equal to low plus high minus low divided by 2. Then I'm going to say square is equal to that middle number squared. And here's where we start doing our checks. You can check if that square is equal to my number, then I'm going to return mid. Else, if my square is less than num, I'm going to say low, let's go ahead and scroll down here, is equal to mid. And then finally, else, I can say high is equal to mid. Then once that's all done, I'm just going to return my low number. So let's go ahead and test out that better solution. Test it on 13. You notice we're going to get the same results. Let's try it on 14. Whoops, that was 114. Let's try it on 14. And finally, let's go up to 16, and we get 4. All right, excellent. So, one difference here from a regular binary search is the condition of that while loop. It's low plus 1 is less than high instead of low is less than high. So look at this here. We have low plus 1 instead of just low. We also have low equals mid instead of low equals mid plus 1 over here. And we have high equals mid instead of high equals mid minus 1. And these are modifications we make to the standard binary search. The complexity of it, though, is still the same. It's logarithmic, order big O log n, which is actually much better than our naive linear solution, just checking them all. And there's also a constant time solution, which involves a clever math trick. And I'll go ahead and show you it. If we hop over to the Jupyter Notebook for the solution, you can take advantage of this trick right here, where the square root of n is equal to n to the power of 1/2 or 0.5, which using log base 2, you can convert into this, 2 to the power of 1/2 times log base 2 of n. And this solution exploits the property that if we take the exponent of the log of a number, the result doesn't change, it's still the number itself. So we can first calculate the log of a number, multiply with 0.5, take the exponent, and finally take the floor of that to value to round it down. And this way we can use voiding the square root function by using a log function instead. Now whether or not you'll be allowed to use that interview setting is tricky, and they may not actually expect you to know this math trick. But it's important to know it in case they ask. So, then the logarithm of a number rounded down to the nearest integer can be calculated in constant time by looking at the position of the leftmost one in the binary representation of that number. So it's actually a lot quicker, and it's a constant time solution. Alright, so thing is, the solution doesn't always give the same result as above algorithms though, because of the rounding effects. And depending on the interviewer's perspective, you may either have this approach be regarded as elegant and clever using this, or as tricky just because you're cheating with the log function. So you should let your interviewer know that you're capable of this shortcut and you're aware of it, but they're probably looking for this implementation here of the better solution that we went over. Alright, so what should you go over here? You should definitely go over binary search. It's important for this question, and you've seen it before on the egg drop problem, so it's something a lot of interview questions kind of have embedded inside of them. Alright, with that being said, make sure you understand the solution and practice both of them. Understand why one is a little better than the other, and we'll go ahead and continue and see you at the next lecture. Alright, thanks everyone. Hello everyone, and welcome to the Rideshare Startup Company mock interview. For this mock interview, you'll have a phone screen and 3 on-site questions, presented in the form of Jupyter Notebooks with the questions, and then afterwards you have Jupyter Notebooks and video solutions for the walkthrough for all the question solutions. So, go through the questions, try to answer them, then check out the solutions and go back over the ones you missed. At the end of this section, you can check out a resource with sourced questions and advice on general hiring practices at Uber, a rideshare startup company. With that being said, best of luck on the interview. Hello, and welcome to the phone screen for the rideshare startup company mock interview. Your phone screen problem is this. If you were given a list of n integers and knew that they were sorted, how quickly could you check if a given integer was in the list? So elaborate on your reasoning and search methods in general. Remember, you already know that they're sorted, so how quickly can you check if a given integer is in the list? The requirement here is that you just explain your solution to someone or record yourself and see if it makes sense. Don't code out anything for this problem. Alright, with that being said, good luck. Try to remember the sorting algorithms we went over previously in the course to fully answer this question. Hello, and welcome to the on-site question 1 for your rideshare startup mock interview. The question in this problem is this. Given a list of integers, find the largest product you could make from just 3 integers in that list. So, the requirements are that you can assume that the list will always have at least 3 integers, so you don't need to check for edge cases where there's less than 3. Also, use paper, pencil, or whiteboard only. Don't code this out until you've solved it as far as you can by hand. So again, if you're given a list of integers, how would you go about finding the largest product possible from just 3 integers in that list? Thanks, and I'll see you at the next question. Welcome to your second on-site question for the rideshare startup company mock interview. Your problem statement is this. Write a function that, given a target amount of money and a list of possible coin denominations, returns the number of ways to make change for the target amount using the coin denominations. So your function will take in 2 arguments, a target amount of money and then a list of possible coin denominations. So for example, you might have a target amount of 46 cents and a list of possible coin combinations as 1, 5, and 10, representing a penny, a nickel, and a dime. So then your task is your function to return the number of ways to make change for the target amount using the coin denominations. So write this out on paper and pencil or whiteboard before you see if you can code up your solution. Alright, best of luck. Hello, and welcome to your third on-site question for the rideshare startup company mock interview. Your problem statement is this. If you were given a binary tree, how would you go about checking whether it's a binary search tree or not? So the requirements are to use paper and pencil. Don't code this out in Jupyter Notebook or any IDE until you've done it out manually. Also, don't use any built-in Python libraries to do this, but you can mention them if you know about them. Alright, that's it. Best of luck, and I'll see you at the next question. Hello, and welcome to the phone screen solution for the rideshare startup company mock interview. The problem statement is this. If you were given a list of n integers and knew that they were sorted, how quickly could you check if a given integer was in the list? Elaborate on your reasoning and search methods in general. So this is a problem where you didn't have to write anything down or code anything out. You just had to explain your solution. So the solution to this problem is, hopefully it sounds familiar, it's using a binary search to search for an integer since the list is already sorted. This means that we can find the item in order log n time and order 1 space. So if you go ahead and click that link, you'll see the complexity link for the Big O cheat. So remember, you have this resource here where you can always check data structure operations and algorithmic sorting operations for their time complexity. So this is a really great resource for you to check out, and make sure you always have it in your back pocket when you're studying your algorithms and data structures. Going back to this solution, what you should do is really revisit the lectures on binary search. and its implementation to fully get the reasoning behind the solution of the problem. Binary search, as you know already, having done some other mock interviews, it's embedded in a lot of interview questions, real interview questions. So it's a really important topic to understand binary search and how to work it. Another question that you can practice for practicing binary search interview questions is the 100-level egg drop problem. All right, with that being said, hopefully you got this question right. If not, don't worry about it. Go ahead and revisit lectures on binary search so you can get it the next time. All right, thanks, and I'll see you at the next lecture. Hello, and welcome to the solution for the first on-site interview question for the rideshare company mock interview. Let's go over the question statement one more time. So given a list of integers, find the largest product you can make from 3 integers in that list. And you can assume the list will always have at least 3 integers. So you have a solution notebook here available for you. And let's go ahead and discuss our strategy for the solution and then go ahead and code it out. First thing to note is that we can actually solve this problem in O(n) time with O(1) space. And we should also be able to take into account negative numbers so that a list like -5, -5, 1, and 3 is going to return 75 as its answer, since 2 negative numbers multiplied together will be a positive number. And then hopefully something that's really important for you to realize is that this question has a lot of similarity between other questions we've seen before, such as that Amazon stock problem from the e-commerce company mock interview. So again, you could brute force this problem just by checking every single combination, but that would be n to the power of 3 time. So that's really not good. So we're going to use a greedy approach and keep track of some of the numbers. So in the stock problem, if you remember, we kept track of the max profit so far, as well as the minimum price we've seen. So for this problem, we're actually going to keep track of several numbers. We're going to keep track of the following 5 numbers. We're going to keep track of the highest product of 3 numbers so far, the highest product of 2 numbers so far, and then just the highest number so far. And since we want to keep negative numbers into account, we're also going to keep track of the lowest product of 2 and the lowest number. So that will help us find answers like this: -5 times -5 equals 25. So once we iterate through that list and reach the end, we're going to have the highest possible product with 3 numbers. And at each iteration, we can take the current highest product of 3 and compare it to the current integer multiplied by the highest and lowest products of 2. So that's why we are keeping track of the highest products of 2, so we can multiply them by the current integer in that list as we move forward through that list. So let's go ahead and code this out. First thing we're going to do is start with our function. So we're going to say def solution. It's going to take in a list. We'll call it LST. And then what we're going to do is say a variable high, and this is going to be the highest number so far. So remember, we're keeping track of 5 variables. So the highest number so far, we're going to go ahead and start at index 2 at the 3rd element and assign the highest and lowest based off the first 2 elements. So when we're actually moving throughout the list, we start at index 2, which is the 3rd element. As far as the other numbers that we're going to keep track of, we'll use the first 2 elements to base those off of. So that means we're going to take the max of the first 2 elements, and then our lowest number is going to be the min of the first 2 elements there. And it's important to remember these built-in max and min functions. All right, so what's next? We also want to initiate the highest and lowest products of 2 numbers. So I'm going to make a variable called high_prod2, which is going to stand for the highest product of 2 numbers. And in this case, since we only have 2 numbers to start off with, we're just going to choose those 2. And we're also going to do the exact same thing for the lowest product of 2 numbers. It's going to be the first element multiplied by that second element. So the index 0 and index 1. And then we want to initiate the highest product of 3 numbers. So we want to say high_prod3, and that's going to be equal to the first 3 elements combined. Okay, so we have our 5 numbers that we're keeping track of. And we've started off with looking at the first 3 elements for the highest product of 3, and then the first two elements for the other numbers. So we have our highest number so far, our lowest number so far, the highest product of two numbers so far, lowest product of two numbers so far, and the highest product of three numbers so far. So now let's iterate through the list and see what we can do. Hopefully this is starting to feel really similar to that stock problem, just with more variables to keep track of. So we're going to iterate through our list, and we're going to start at index 2, that third element. Let's go ahead and zoom in here so we can clearly see what's going on. Oops. All right, so we're saying from the third element onwards, we're going to do a bunch of comparisons. First comparison we need to do is check if we have a new highest product of three numbers, the thing we're actually searching for. And so we're going to compare a couple things here. First, we're going to compare our highest product of three. So that makes sense. Compare our current highest product of three against the current number times the high product of two, as well as the current number times the high product of 3. And just remember, I'm using tab here in my Jupyter Notebook to get those drop-down options. So as we go throughout this list, I'm taking the current number, multiplying it against the highest product of 2 so far, and whoops, this is actually incorrect. It should be the lowest product of 2. So let me restate that in case there's any confusion. So I want my highest product of 3 to be the max of our current highest product of 3 times the current number multiplied by the highest product of 2 times the current number times the lowest product of 2. Then I want to check for possible new highest products of 2 numbers. So I want to say high underscore product of 2 is equal to max. I'm going to compare it to the current highest product of 2. And then I'm going to compare it to the current number times num high versus the current number times low. And then we're going to do something similar for the lowest product of 2 numbers. In this case, we're searching for min. So again, compare it to the lowest product of 2 numbers, and then none times high, none times low. So that should get us the larger negative numbers there. And then we check for a new possible high. Max is that's just going to be high compared to the current number. And then low is just going to be minimum of low compared to the current number. Let's make sure that's touching its function here. And then after all that, as we go through a list, we can just return the highest product of 3. Okay, so again, let's break down what we're actually doing here. Again, we're going to use a greedy approach on this problem and keep track of the numbers. So we're keeping track of several numbers. We're keeping track of the highest product of 3. And let's go ahead and zoom out so we see the whole picture. We're keeping track of the highest product of 3 numbers so far, the highest and lowest product of 2 numbers so far. We're also keeping track of the highest number and the lowest number we've seen, and then the highest product of 3 numbers. So, what are we actually doing here? We're iterating through the list until we reach the end. And then at each iteration, we take the current highest product of 3 and compare it to the current integer multiplied by the highest and lowest products of 2 numbers. So, let's do this step by step. We're going throughout the list, taking our current number, taking our current highest product of 3 numbers. Remember, ultimately that's going to be our output in the function. Taking that current number and multiplying it by the highest product of 2 numbers and the lowest product of 2 numbers. So that's going to allow us to take advantage here of a negative times a negative. Then we're going to check to see if we have new high product of 2 numbers and new low product of 2 numbers. And for those comparisons, we take our currents and then multiply our current numbers by the high and low numbers we have so far. Then we check if we have a new high and a new low, and then we would just return the highest product of 3 numbers. So this greedy approach allows us to do this in O(n) time. So you should always keep this sort of approach in mind when you have to iterate through a list, and you can see that clearly there's a brute force solution, but it's on the order of an exponential. So this should be really reminiscent of that stock problem. So again, for this problem, we're just taking track of everything as we go throughout the list. The trick to this problem is realizing that you had to keep track of these highest product of 2 and the lowest product of 2. So go throughout the solution, make sure you understand it, add print statements as needed for you to fully understand this problem. But just remember, we're just keeping track of a greedy approach to this problem, keeping track of certain variables, in this case 5 of them, in order to find the highest product of 3 numbers. Again, you can always read out the full explanation in the solution notebook. All right, well, that's it for this solution. I'll see you at the next lecture. Thanks, everyone. Hello, everyone, and welcome to On-Site Question 2 solution for the Rideshare Startup Company mock interview. So, for this problem, you had to write a function that, given a target amount of money and a list of possible coin denominations, returns the number of ways to make change for the target amount using those coin denominations. So this is a classic interview problem, and it's classic enough that you've probably already seen it before, and we did a really similar problem in the recursion section. So make sure to review that problem before reading the solution here. And in this solution, we're going to use a bottom-up algorithm. I put a link here to the Wikipedia page describing what software development process for top-down and bottom-up and how the key roles they play. Might be good to know for an interview situation. Then we have our solution. So to explain what's actually going to go on here, since it's not that many lines of code, we can go ahead and check out an explanation of it. So what we're going to do is imagine you have the target number and the list of coins. And you want to get all possible sets that elements are equal to, let's say, A, B, or C, and we'll label those our coins that sum up to X. So since that's our target, we want to get all the possible sets for the coins that sum up to X. We're going to take all such sets that sum up to X minus A, and then add an extra A to each one. So A is just some arbitrary coin value. Do the same thing for B, another coin value, coin denomination, and do the same thing for C. And then we're going to add an extra C to each one. So that means the number of ways you can get X is the sum of number of ways you can get X minus A and X minus B and X minus C, which is what we're going to do here. And here the array is called ways. We're just going to call our array ARR. All right, and then the rest is just simple recurrence. So let's go ahead and check out our solution notebook and program through it. So we're going to go ahead and jump to our solution, and we're going to go ahead and write it out. So let's go ahead and start with making the function. We're going to have def solution. It's going to take in our target number. Let's go ahead and add that O there. And then a list of coins. We're going to set up an array first for just tracking results, and we'll call it, start off with 1, and add a 0 times n. And then here's where our algorithm is going to come into play. We're going to say for coin, in coins, so for every coin denomination, send for I in range from the coin denomination value all the way to n plus 1. And that plus 1 is just for the range. Let's fix that. The range in Python, since we need that add 1 since indexing starts at 0. And all we're going to do here is in our array, which is keeping track of the number of ways, we're going to add an array at I minus that coin value. So that was that X minus A, X minus B, X minus C we were seeing before. And then we're just going to have an edge case check. So if n was equal to 0, we'll just return 0. Otherwise, else, we're just going to return the array at that value. Okay, and that's all there was to it. It's pretty simple code, but the idea is sometimes tricky to understand. So again, check out the full solution notebook for an explanation. And also, you might want to Google the terms dynamic programming plus coin change problem, and you should get a ton of explanations for this particular problem since it's such a common interview problem. So that's it for the solution video here, and I will see you at the next lecture. Again, you can go ahead and review the entire solution in that notebook. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the on-site question 3 solution for the rideshare startup company. This problem, you've actually already seen it before in the tree section of this course. It was given a binary tree, check whether it's a binary search tree or not. So, you're given it that it's binary tree, but you need to know if it's a binary search tree. Now, there's actually two solutions here we can check out. Again, we already went through this in the trees lecture section, but we're just going to go over the solution again here. So let's go ahead and jump to our solution, and we're going to start off with a few things to understand first. First, we have to understand the main difference between a binary tree and a binary search tree. So we know a binary tree is a tree data structure in which each node has at most 2 child nodes, thus binary meaning 2. And a binary search tree, BST, is based off a binary tree, but it has additional properties, basically 3 main properties. The left subtree of a node contains only nodes with keys less than the node's key. And then the right subtree of a node contains only nodes with keys greater than the node's key. And then both the left and right subtrees must also be binary search trees. So this is a really common interview question. It's actually really good because it really tests your understanding of the definition of a binary search tree. So how do we go about solving this problem? A lot of people make this mistake that what they're going to do is at every node check whether its value is larger than or equal to its left child and smaller than or equal to its right child. However, that approach is actually wrong because it doesn't check whether a node violates any condition with its grandparent or any of its ancestors. So you can't just check nodes to trees. What you have to do is keep track of the minimum and maximum values a node can take. And at each node, we're going to check whether its value is between the minimum and the maximum values it's allowed to take. So we can actually do this by kind of typing out a class node and then working for a function to check that out. So let's go ahead and make a class node and just initialize it with self. And we'll just have it take on a value of none. And we'll have self.left equal to none, self.right equal to none, and then self.value equal to value, which by default is none. Okay, so then what we're going to do, now that we have our node class so we can build out trees and nodes, we're going to do this. We already know that we want to keep track of the minimum and maximum values a node can take. And at each node, we're going to check whether its value is between the min and max values it's allowed to take. Then the root can take any value between negative infinity and positive infinity. In case you're not familiar with Python too much, we can actually pass in infinity and negative infinity as floats. So I can say, let's just make it really obvious to put it in all caps, infinity, and have it be float, and you can pass a string infinity here, and that will be valid, and then we can do negative infinity like this. This is kind of just a trick with Python to pass these in as strings. See if that works. Alright, great. So what we're going to do is, we know the root can take any value between negative infinity and positive infinity. So we have those set up, and we also have our class node set up. At any node, its left child should be smaller than or equal to it than its own value. And then similarly, the right child should be larger than or equal to. So during recursion, what we're going to do is we send the current value as the new max to our left child and send the minimum as it is without changing. And then to the right child, we send the current value as the new min and send the max without changing. Let's go ahead and see how we do this. So here is our solution function. We'll call it isBST for is it a binary search tree. We're going to pass in a tree, pass in our minimum value of negative infinity, and then pass in our maximum value right now of infinity. Then we're going to say if tree is none, return true. And then we're going to say if not min val. So here we're going to actually be checking the tree val to make sure it fits in between these. So as long as our tree val is greater than or equal to, as long as our tree val is not greater than or equal to min val or less than or equal to max val, since we're using an if not here, we're going to return false. So we kind of have our base case checks, and then we're going to say is BST, here's our recursive call, tree.left, min val, and then tree.val. And we want to return is BST on tree right, tree.val, that current value, and then max val. Okay. So note the ordering there, and note how we're changing up the minimum and maximum values as we go along. Now that's one solution. If you're not worried about space in your big O, there's an equally good alternative solution. If a tree is a binary search tree, then traversing the tree in order should lead to the sorted order of the values in the tree. So this is actually kind of a nice, simple way to do it. You can actually perform an in-order traversal and then check whether the node values are sorted or not. So that one is usually makes sense to people. It's just a little more direct as far as how you're thinking about it. So let's go ahead and do that solution. And if you're having trouble remembering as far as in-order traversals or what a binary tree is, definitely make sure you check out the tree section of the course for a refresher. Okay, whoops. Let's go ahead and make this function, and it's going to take in a tree, and it's also going to take in an argument last node, and we'll call it negative infinity here. Then we're going to say if tree is none, return true. And I need to put a colon there, tab it over. And then if not is BST2, and we'll pass in the left of the tree and then the last node. We're going to return false. And then continuing on, we're going to say if that tree value is less than that first element of our last node list, we return false. And then we're going to build out that last node. That first element there is equal to the tree value. And then finally, we return is BST2 and pass in the right branch of that tree, tree right, and then the last node. Okay, so what are we doing here? We're just saying if a tree is a binary search tree, then doing an in-order traversal. So you can go ahead and check what an in-order traversal is back in the tree section in case you're not getting how we're implementing it here. So as I mentioned, an in-order tree traversal, if it's a binary search tree, that should actually lead to a sorted order of the values in the tree. So we can perform this in-order traversal and then check whether the node values are sorted or not. All right, so that's it for this question. Remember to check out the tree section and the tree lectures for a better breakdown of this. We went kind of quickly through it here because we're assuming that you've actually seen it in the tree section where we explain it in a little more detail than this. All right, well, with that being said, that's it. Hopefully you did well on it, and good luck in the rest of your mock interviews. Thanks, everyone. Hello, everyone, and welcome to the Social Network Company mock interview. For this interview, you'll have a phone screen and 3 on-site questions, all presented in the form of questions in Jupyter Notebooks. Afterwards, you'll have solutions presented for all the questions, so go through the questions first, then check out the solutions, and then go back and try the ones you missed again. Afterwards, you can check out a resource at the end of the section for a write-up on the Facebook interview process by a Facebook engineer. Okay, good luck with the interview, and I'll see you at the next lecture. Hello, and welcome to the phone screen problem for the social network company mock interview questions. So, the problem statement is this. Remove duplicate characters in a given string, keeping only the first occurrences. So, for example, if the input is the string tree traversal, the output will be TRE space AVSL. So notice that since you have an E already occurring, the second E in tree gets removed, as well as the E in traversal. And then the TR get removed because they're already in tree. Okay, so write a function again that removes duplicate characters in a given string, keeping only the first occurrences. So your requirements for this problem is to complete the problem in a text editor that does not have syntax highlighting, such as a Google Doc, or any word processor or text editor. Again, as we've stated before, a lot of phone screens will just have you screen sharing on a normal text editor that doesn't have syntax highlighting. So it's important to practice writing out code without syntax highlighting or automatic indentation. Now, again, don't worry if it's perfect, it doesn't have to run, but at least get the general concept of what you're trying to do, and then you can go to either Jupyter Notebook or any other IDE and test out your code. Alright, with that being said, best of luck, and I'll see you at the next lecture. Hello, and welcome to the first on-site question for your social network company mock interview. Your problem statement is this. Given a list of integers and a target number, write a function that returns a boolean indicating if it's possible to sum two integers from that list to reach the target number. Some requirements for this is to try pen and paper or a whiteboard before coding out your solution. Another requirement is that you cannot use an integer element twice, and you want to optimize for time over space. So again, to give you an idea of what this problem's like, you're given a list of integers. Let's say the list is 1, 2, 3, and then a target number. Let's say the target number is 5. So you want to write a function that returns a boolean indicating if it's possible to sum two integers from that list to reach the target number. In this case, you would return true, since 2 and 3 can be summed up to equal 5. Again, you're given a list of integers, a target number, and you want to see if it's possible that from two numbers or two integers from that list, you can sum them up to create that target number. Now you can't use an integer element twice. So you can't use, for instance, if your list was 1, 2, 3 and your target number was 4, you couldn't say add 2 and 2 again because it only occurs once in your list. Alright, with that being said, best of luck, and I'll see you at the next lecture. Hello, and welcome to the second on-site question for the social network company mock interview. Here's your problem statement. Given a list consisting of account ID numbers in the form of integers, which contains duplicates, find the one unique integer. The list will be guaranteed to only have one unique non-duplicated integer. Some requirements: do not use built-in Python functions or methods. However, you can go ahead and feel free to code this out in a Jupyter Notebook or in an IDE of your choice. So to give you an example, you may have a list that goes 1, 1, 2, 2, 3. So you have duplicates of the integer 1 and the integer 2, but the integer 3 is unique. So your function should be able to take in that list and find that one unique integer, 3. Keep in mind you want to do this efficiently, so keep in mind big O and how that can affect your function. Alright, with that being said, best of luck, and I'll see you at the next lecture. Hello, and welcome to your third and last on-site question for your social network company mock interview. Your problem statement is this. Create a function that takes in a list of unsorted prices in the form of integers and the maximum possible price value, and then return a sorted list of prices. Here's your requirement. Your function should be able to perform this in less than O n log n time. Also, you can't use any built-in methods in Python to do this. So, again, your function will take in a list of unsorted prices in the form of integers. So for example, a list containing 3, 7, and 4, and a maximum possible price value. In this case, that would be 7. And then return a sorted list of prices. So the key to this problem is that you're given a list of unsorted prices, and you also know the maximum possible price value. How can you take advantage of that fact to return a sorted list of prices in less than O n log n time? Alright, this is a pretty tricky problem, so best of luck, and I'll see you at the next lecture. Hello everyone, and welcome to the phone screen solution for the social network company mock interview. So for this problem, you had to remove duplicate characters in a given string, keeping only the first occurrences. So for example, if the input was tree traversal, your output would be TRE space AVSL, as you remove duplicate E's, T's, and R's. Okay, so let's go ahead and get started with the solution. So as we're going through the string, we're going to need some sort of data structure to keep track of the characters we've seen so far. And we also need one that can perform efficient find operations. So in this case, a set data structure perfectly suits our purpose. It stores keys and then provides constant time search for each existence. So we're going to loop over the characters in the string, and at each iteration, we'll check whether we have seen the current character before searching the set. If it's in the set, then it means we've seen it before, so we ignore it. Otherwise, we include it in the result and add it to the set to keep track for future reference. So let's go ahead and code this out so it's a bit easier to understand. Let's go ahead and call our function remove duplicates. And we'll input, let's just put input s. And then we're going to say results equals an empty list. And the reason for that is at the end, what we're going to do is join that list. So in Python, I can do this here. There's no space in between these single quotes, and it's basically going to join every item in that list together without a space in between. I could put anything I want here, and that would put that whatever symbol or letter or character you put. So if I wanted to join everything with a comma, but in this case, since I just want a single string, I'm just going to join them with no spaces. Then I'm going to create another variable called scene, and I'll set that as an empty set. And then here's what we're going to do. We're going to go for every character in the string, if that character is not in scene, then I'm going to add it, scene.add that character. And then I'm going to take my results and append that character. And that's really it here. So the time complexity of this algorithm is O(n), where n is the number of characters in the input string. And because set supports an order 1 or big O1 constant, insert and find. So this is really the optimal solution, and it's a really common string interview question. So this problem hopefully feels pretty familiar. There's a similar one asked in the array section of the course. And remember that a lot of basic interview question ideas overlap, just the presentation is different. So again, this was a pretty basic problem. That's why it was just a phone screen. The main trick or key to this problem was figuring out that a set is a really good way to go in this case. You just go for every character in that string. If you haven't seen that character yet, so it's not in that set, you just add that character to the set and then result.append that character. And then at the end, at least for Python, you can join everything in that list together as a string with this join command. Alright, that's really it for this phone screen solution. I'll see you at the next lecture with another solution. Thanks everyone. Hello everyone, and welcome to the first on-site question solution for the social network company mock interview. For this problem, you were given a list of integers and a target number. Then you were assigned to write a function that returns a boolean indicating if it's possible to sum two of the integers from that list to reach the target number. And you had a requirement here: you cannot use an integer element twice, and you had to optimize for time over space. So for this problem, we're actually going to take advantage of a set data structure. We just took advantage of a set in the last phone screen problem, and we're going to do it again. Really want to iterate here that the set is a very, very useful data structure, and sometimes it doesn't come to mind as much as, say, a list or a straight dictionary. So sets are really, really useful, and we're going to make use of it again in this particular solution. What we're going to do is make a single pass through that list of integers and then treat each element as the first integer in our possible sum. Then at each iteration, we're going to check to see if there's a second integer which will allow us to hit the target number. And then we're going to use a set to check if we've already seen it in our list. Then we're going to update our seen set by adding the current number in the iteration to it. So this should be really similar to what we just did as far as using a set as an already seen holder. So what we're going to do is take in that list, lst, and then have our target. Then we're going to create a variable called seen and have it be an empty set again. So this should be really familiar to you from the last problem we just did, and this is really what a set is super useful for. If you ever have an interview problem where you're thinking, hey, how can I keep track of integers or elements that I've already seen? A set should definitely come to mind. All right, so now we want to go throughout the list. So say for num in list, I'm going to find out if there's a second number that sums up with the number to reach the target. And in order to do that, I'm just going to use a simple subtraction here. I'm going to say num2 equals target minus number. Then, if num2 has already been seen, I'm going to return true. After that, if that if statement doesn't happen, I'm going to add that number to seen. And then if it never gets hit, I'm just going to return false. All right, so let's think about what's actually happening here. It's pretty simple code, and the idea should be pretty straightforward. I have this seen variable, and it's an empty set. And then I'm going along and saying for every number in that list, I want to find a second number which makes me reach that target number. So I have my target minus the current number in that list equal to num2. And if I've already seen that num2, if it's already in seen, I'm going to return true. And then if that doesn't happen, if this if statement doesn't become in seen, I won't return anything, so I'll keep going and add that number to seen. Otherwise, if I go throughout this entire list and never see it, I'm just going to return false. And so this is why I mentioned we're optimizing for time over space. Because in space, we're actually keeping track of every number that we've already seen, which isn't so great for space efficiency. But as far as time efficiency, what's nice is that we're only doing one run through this list. Okay, so that's it for the solution. Again, we're just taking advantage of a set data structure, making a single pass through the list of integers, and treating each element as the first integer of our possible sum. Then, at each iteration, we will check to see if there's a second integer which allows us to hit that target number, which is what this is. And we're going to use a set to check if we've already seen it in our list, which is what's happening here, here, and then num2 in seen. Then we're going to update our seen set by adding the current number to the iteration, which we do here if we don't end up returning true. If we go throughout the entire list and that num2 was never in that seen set, we're just going to return false. All right, that's it. Again, remember to keep that set data structure in the back of your mind, especially if you're trying to keep track of something. Okay, thanks everyone, and I'll see you at the next solution lecture. Hello everyone, and welcome to On-Site Question 2 solution for the social network company mock interview. So the problem statement was, given a list of account ID numbers, which were just integers, which contains duplicates, find the one unique integer. And as a caveat, the list is guaranteed to only have one unique non-duplicated integer. So hopefully this problem felt pretty familiar if you went through the array section of the course. What we're going to do here is use an exclusive OR operation. And in case you're not familiar with an exclusive OR, you can click this link and it will take you to the Wikipedia page. But basically what an exclusive OR operation does is that it will take two sets of bits, and for each pair it will return a 1 value if one but not both of the bits is 1. So in Python that's the caret symbol, but let me show you what I mean by an exclusive OR. So you can see here on the Wikipedia link, we have an input A and B, and we're only going to return true if one but not both of the values are true. Otherwise, we return false. So let's go ahead and see how we can do this and use an exclusive OR for our solution. So for our solution, we can simply do an exclusive OR on all the integers in the list. We start with a unique ID set to 0. And then every time we do an exclusive OR, a new ID from the list, it's going to change the bits. And then when we do that with the same ID again, it's going to cancel out the earlier change. And then by the end, we're going to just be left with the ID that was unique and only appeared once. So let's go ahead and see how this works. Here I've copied our solution, and we have def solution takes in the ID list. We initiate with a unique ID. And then for every I in that ID list, every ID there, we're going to do the exclusive OR operation. And we can update unique ID in this manner. So if we run that solution function and test it out on this list, here the unique ID is 3. So if we go ahead and run our solution, you'll notice we get out 3. In case you're having any trouble understanding this, we can actually just print out a few things. So let's go ahead and print out this is I, and we'll go ahead and print out this. So we'll actually print out this is the current ID being checked, comma I, and then let's go ahead and print this is the current unique ID, and we'll put in unique there, ID. And then finally, we're going to print this is the results of the exclusive OR. And then let's go ahead and put in unique ID. And then do an exclusive OR check. Let's go ahead and try that. So we just cleared this box right here. So I'm going to run that. So now we have an updated solution, and let's go ahead and see the steps. So these print statements are going to be really useful for us to understand. So current ID being checked. Let me actually fix this since I spelled being wrong. There we go. Current ID being checked is 1 against the current unique ID. So 0, 1, that's going to return a 1. And you notice current ID being checked against the unique ID due to the features of the exclusive OR. Since we have a 2 and a 1, we're going to return a 3. And then a 3 against a 3 is going to then return a 0. 0 against 2 returns a 2. And then finally, 2 against 1 is going to return the only unique ID in the entire list. All right, so the key to understanding this is really understanding how the exclusive OR operation works. So if you didn't get it, go ahead and make sure you read the exclusive OR operation here on the Wikipedia page. And keep in mind, this is a bitwise operator, so you'll have to remember your binary representation of numbers in order to fully understand these sort of 2s versus 1s or 3s versus 3s. So if you didn't get that part, just check again how a bitwise operator works and how a binary representation of a number works. Okay, that's it for the solution. Thanks everyone, and I'll see you at the next lecture. Hello everyone, and welcome to On-Site Question 3 solution for the social network company mock interview. For this problem, you were assigned to create a function that takes in a list of unsorted prices, which are integers, and a maximum possible price value, and then return a sorted list of prices. So this problem is actually perfect for a counting sort, and if you're unfamiliar with counting sort, you can click this Wikipedia link. It'll take you here. Go ahead and check it out, and in order to fully understand the algorithm, come down to this algorithm section and walk yourself through the pseudocode. Okay, so once you've done that, then come here and check this out. So we have our solution implementation, but basically just keep in mind that the most general form of this problem is a list of unsorted integers and a maximum possible integer value, and you have to sort them. Here we're using prices, but it could be anything. It could be scores for a video game, etc. So let's go ahead and try to walk through our solution. So first thing we're going to do is take in the unsorted prices. That's going to be a list of unsorted prices, and then we have a max price. Again, this could be anything, but it's an unsorted list of integers and a maximum possible integer. Then I'm going to create an object called prices to counts. And that's going to be basically a list of zeros that go from 0 to max price. So I'm going to multiply it by max price, and because indexing starts at 0 in Python, I'm going to do max price plus 1 here. Next, I'm going to populate prices. So I'm going to say for price in unsorted prices, prices to counts, at that price, I'm going to add 1. Okay, so then what we're going to do, I'm going to create an empty list, which will be our sorted prices. And this is actually what we're going to return. So right now it's empty, but at the end I'm going to say return sorted prices. And then for each price and price counts, what I'm going to do is this. I'm going to say for price, and then let's say count, and enumerate prices to counts for the number of times the element occurs. So I'm going to say for time in range of the count, just add it to that sorted price list. So take sorted prices and then append that price. Okay, so let's go ahead and see how this works.